What's that?
You see the overflow. So there's going to be additional rooms for people look at it.
Either, not both.
Yeah.
Okay.
You can just select one.
Okay.
So something I think someone should actually go and, do you know if anyone is actually going to the overflows?
That's a good question. We could try. Oh, we have a microphone.
We have a microphone, yeah. The other thing we should do is what else? This actually works. Hey, okay, great. I'm speaking. Good. So I'll keep this off.
Do we know which the platform called that?
No.
Okay. Okay.
This one I never tried.
Test. Okay.
So that should be used only by the chair, I think. Hello. Oh, amazing. Tiny button here.
Oh, okay. So is this the microphone we're going to be using for asking questions?
Yeah. That is good.
Okay.
And the other thing is this thing here. The speakers can use to like.
Okay. Okay. Cool. Okay. Yeah, I think at some point you've submitted to it first. Thursday or something. Or do we need to? Okay. By the way, should we try to use the when you show? Okay. Okay.
Almost a serious conference.
Yeah.
Almost there.
Yes.
Anything else?
Let's check your list, right?
Hey.
Hey.
Well, actually, everything is working.
Okay, perfect.
The only problem is that the first teacher is getting a project.
Credits, get more credits.
It's
Getting coffee. Oh, it's officially. It's here. Thanks.
Hey, PW, you're Paul Wilson.
Yeah, that's me. Hello.
Hi. Oh no.
Wait, I don't hear you.
What is not working?
Or the output, but I think it's just like not configured. I wrote down like configuration to put in the email. So how do you output on Zoom?
Hi, Paul. Can you speak again?
Yeah, can you hear me?
Wonderful. Yeah.
Cool.
Echo? Is there echo coming back when you speak?
Let me see. I'll speak some more. No, it seems okay for me.
Okay, good. It's too loud?
Yeah, I think it's too loud. Let's.
All right. You're still a question. You're presenting online, right? So
So can you say something again?
Yeah, sure. Don't really have anything prepared for mic testing, but okay. Cool.
right. Yeah, so we should be ready in a while.
Shall I share my screen? Make sure that works.
Yeah, please. Hey, David.
Yeah, go ahead. Let's test this.
Okie dokes. I mean, it should, but you never know. Oh yeah, that seems to be working, right?
I'll get back to you in a moment.
Cool.
Paul, could you try and say something like this?
Yeah, I can't hear you very clearly, but
okay. Can you? Well, we can hear you at least.
Okay.
Okay, so yeah, it's my great pleasure to introduce Paul Wilson, who's going to talk about categories of differential polynomial circuits in machine learning. Please.
Cool. Thanks very much. Well, so first of all, thanks to all the organizers and everyone making this a success, which I'm sure it will be. This is some work together I did with Fabio Zanasi at UCL. And I want to start with some quick motivation. So there's kind of two views of motivation I want to present. So first is this kind of narrow view, which is basically just a list of things that are in the paper. And then the second view is kind of what, why are we doing any of this? So more of like a contextual view, like, and maybe a bit of speculation as well. So kind of, what do we want to do longer term? Like, how does this sit within broader aims? So first with the narrow view, it's basically these four things. So we define this category polycirc sub S, and this is going to sort of, it's going to work as a model class. So that what we mean by that is the morphisms of this category are going to be machine learning models. So you could sort of think of this analogously to neural networks as the morphism will be the architecture of the neural network. It's not like a trained model, it's like the thing that you then train. So that's the first thing. The second thing is we give a graphical account of reverse derivatives. Now these are defined not by us, but by a paper from 2019, which is very good. And it's like a categorical ingredient for doing gradient-based learning. What we do is to make this kind of more friendly for categories defined as presentations by generators and equations. And I'll obviously be more clear about what I mean by that later on. But the reason we do that is so that we can then have this theorem, which is the third thing, which lets us basically extend a reverse derivative category. Or if you have a presentation, you've got some generators and equations, and you want to add some new stuff to your syntax, you can, this recipe basically gives you a way to add that stuff and still have reverse derivatives. And then finally, we would like this base category, this model class, to be sufficiently expressive to model any real world problem that we might encounter. So this is the functional completeness, basically. So the idea is that if you get given a data set, then you can think of that as like an extensional representation of a function, and you want to learn some model, which is the kind of true function, but your model class needs to be powerful enough to handle any data set that it might encounter. So that's what functional completeness gets you. And just to be a little bit concrete, so we're not completely abstract on the first slide, this on the left here is a morphism of polycirc sub S, and we think of these little 2-to-1 white nodes as multiplications. These are additions, and this is the constant 1. So this corresponds to the functional polynomial on the right. And we're going to be, until quite late in the slides, we're going to be talking quite generally. So polycirc S is actually a prop, but we're not going to be talking about props until we actually get to the very point of definition. We have some like more general stuff, but that's not too important. We can just really think of these as polynomials for now. Okay, so in case it's not clear what I mean by a presentation by generators and equations, here's like a very quick summary of that. You have some widgets, so you can think of these as like operations. So this, for example, is in our setting, this is a copy, so it has one input and it copies it to its two outputs. And this is just swapping two values. We can put them together in two ways, so we can do normal composition, so we feed the outputs of this into the inputs of that, or we could do setting one atop the other, so the tensor product. And then we also have some equations. So here this is saying that if you copy something and then swap the copies, it's the same as just copying something. Okay, so now that's kind of the narrow view of the paper. This is hopefully some broader context. So I guess we have this like slogan of machine learning with string diagrams. And I always put this this diagram in to like every slide deck I do, because this is a diagram actually from mainstream machine learning, from a paper called One Model to Learn Them All, I think. And it's a really, really nice string diagram, which they put in their paper without ever using the word string diagram. I'm not sure if they, like, maybe they knew about string diagrams and they were like, that's nice, but I don't think they ever used this as like a formal syntax. And I just think this is a really cool illustration that people obviously want to be using string diagrams in machine learning, but maybe they're not aware of the extent of the kind of formal mathematical tools available for, you know, messing around with them, representing them, and so on. So we would like to make this syntax. You know, we would like to use string diagrams because it basically gets you everything a syntax does, and all these extra free theoretical tools. For example, we would like to represent terms, obviously, on a computer. And if we use presentations by generating equations, we get all this nice combinatorial structure. You know, they're like well-defined data structures and algorithms for doing composition, tensor product, and so on. We've done a bit of work on this, but also there's lots of other people who've worked on this. For example, the algebraic Julia people, who I think are also giving at least one talk at ACT, which I'm sure will be very good. So the point is that there's kind of a lot of stuff available if you use string diagrams as the basis of your model class. There's a lot of available tools now to sort of deal with them. And you know, you might want to do things like rewriting, which of course is very useful. You might want to optimize your model, so rewrite it down into a smaller form. Obviously, in machine learning, we need to evaluate the diagram, or maybe compile it. And actually, that's kind of one of our motivations, is to, by defining the syntax, we eventually want to compile our model into sort of weird targets. So maybe some kind of embedded setting or like an FPGA. And then finally, obviously, the visual aspect is very useful, but there's also some people in mainstream ML who do a lot of sort of, maybe debugging is not the right word, but introspecting into the sort of internal values of the neural network. So, for example, one thing they do is in an image model, they want to look at what are the intermediate features being learned. And so they visualize the kind of values happening on the wires of the model. So maybe if I skip back here, I guess the idea is you would want to zoom in on, I don't know, let's say the output of this plus here. I don't know if you can see this. You might want to zoom in on this and see how this is changing over time with training and see what it's actually learned. Or maybe visualizing the weights is better, but either way. So all that kind of free stuff that we get by using string diagrams aside, we also have a sort of immediate concrete application for defining this model class category. And that is to do gradient-based learning, but without using real numbers. So this is like the world's quickest and least accurate recap of gradient-based learning. But in 5 bullet points, the goal is to learn this function, as we said earlier, from say like an A tuple of reals to a B tuple of reals. So the way we do that is to define a model M, and this basically, it indexes a space of functions from Ra to Rb, and by choosing a particular parameter vector, a p-dimensional parameter vector, you fix a specific function. So the way you do that is to like partially apply the parameters to the model. And so you make some initial choice of parameters, say theta, and then you wobble around in parameter space until you find some good set of parameters, which, you know, approximates the function you want well. So the way you do that wobbling around is to move in the direction of best improvement, which obviously corresponds to the derivative. And in our case, that's going to be the reverse derivative. So in this paper, we're saying like, well, we don't really want to use real numbers. Can't we just, you know, generalize this to an arbitrary semi-ring? And some motivation for why you would want to do that in the first place. Well, you can't work with real numbers really on a computer. There's too many of them. So you have to use a finite representation. You could use something like the computable reals, but what people normally do is just choose floating point, for example. So you're kind of approximating the true answer. The trouble with this in, for example, embedded situations is that floating point is quite expensive, relatively speaking. So a multiplication of floating point is a lot slower than say like an integer multiplication. And sometimes you don't even have floating point units on your CPU. So that's not good, because if you simulate it in software, it's even slower. So we want to basically say, if we're dealing with a finite approximation or representation of numbers anyway, why don't we pick an actual finite semi-ring and work directly in that? So an extreme choice to do here is just to use a single bit for each number. And we kind of looked at this already a couple of years ago. So choose like Z2 as your semi-ring. And then gradient descent is now quite weird. We usually think of this sort of smooth, sort of moving around smoothly in this parameter space, but now you have to flip a whole bit. There's sort of an all or nothing change in each parameter. Nevertheless, it kind of sort of still works, which is a bit weird. And the nice thing about the Z2 semi-ring is that it's already functionally complete, so you can express any Boolean function using these like polynomials over Z2. But now we want to generalize it basically. So instead of just this one choice, we want to go to any semi-ring. There's some weird properties of this one that make it quite an odd choice. So let's generalize. Okay, so just to quickly summarize, we want our category to have this reverse derivative structure, so we can do gradient-based learning. We would like it to be presented by generated simulation, so that we can, get all this free theoretical tools, computer representations, and so on. And finally, we would like it to be functionally complete, so expressive enough to model any sort of machine learning task that might come up. Okay, so that's motivation. Hopefully that's motivating. Now I'm going to talk about reverse derivatives. So this, I'll very briefly touch on the original formulation, but not in detail. And then I'll talk about how we sort of re-axiomatize it. Then we'll define polynomial circuits, and then we'll talk about functional completeness. Okay, so I'm going to also cover gradient-based learning again very quickly, and show sort of why we need the reverse derivative, what's it actually doing. Then we'll talk about our axioms, and finally this extension theorem, which we talked about earlier, where you can add new stuff to a presentation and still have your reverse derivative structure. Okay, so this is the paper where these categories are reverse defined. Actually, I think some of the authors are giving a talk on Wednesday as well, where they generalize these things to monoidal categories. So in a reverse derivative category, as you'll see in a minute, you need Cartesian structure. They seem to have relaxed that requirement this year, so that's probably a good talk as well. Anyway, so what they get you is this combinator R. So for each morphism F, this combinator R maps F to a morphism of this type. Now I've added the primes here. These are not, they're not really there. These are just here to indicate to you what the roles of each of these variables are. So the reverse derivative, I think of it as basically taking, for a given input to F and a given desired change in output, how should I change the input in order to achieve that change in output? And now there's some axioms that you have to obey to be an RDC, and there's some other base structure. Cartesianness is a part of that. But that's the general idea. These are the original axioms. Okay. So how does this get used in gradient-based learning? Well, now earlier we were dealing with like tuples of reals. Now we're going to be dealing with sort of generic objects in our category. So we have a map from A to B. We have a model which goes from P times A to B. So this is indexing this space of functions with some parameters. And we need to do this nudging in the direction of best improvement. And that's going to obviously be what the reverse derivative does. But what we want is something roughly of this shape. So M prime takes your current parameters and an input example A. It takes an output error. So this is how different your prediction was from the true example output. And it's going to give you a parameter update. So you basically add this to your current guess of parameters. And unsurprisingly, the reverse derivative more or less gives you that. It also gives you a way to change your input example, but obviously in most cases that's not super useful. So normally we just throw this away. So that's kind of what the reverse derivative is for. That's why we want it. This is sort of the key part of the learning process. But there's also some sort of base structure that we have, or sorry, that's required to have an RDC in the first place. The first part of that is Cartesian structure. So there's this theorem by Fox which says that if you have all these widgets and equations, then you have a Cartesian category. And basically, this is saying this is a copy widget. This is discard. So this takes its input and copies it to two outputs. This takes its input and just throws it away. It's a co-commutative comonoid, and also it's got these naturality axioms. I don't want to say too much about this, but we need this in order to have Cartesian structure. Then we're going to need left additive structure. If you have both Cartesian and left additive structure, you can just add in the left additive structure by adding this monoid, commutative monoid for each object A. So we now have this widget, which is the sort of opposite of the copy. It's going the other way. So it takes its two inputs and it adds them together. And this is the intuition I'm giving, just because that's how we're going to use it in polycirc. So it's literally taking elements of the semi-ring and summing them. And then this is the zero constant in the semi-ring. And again, we have these kind of expected equations. So it's commutative and associative and so on. Okay, so that's Cartesian left additivity. That's actually, oh, sorry, this here is actually the alternative definition of Cartesian left additivity given in the original paper from 2019. The kind of, I guess, mainstream definition of it is actually that you can add morphisms and that there's a zero morphism. So this is saying there's like a plus operation on the Hom sets, and it obeys these axioms. This slide is basically just showing how this is equivalent to that. So you define addition of morphisms like this. You copy your inputs, you apply each function to them, and then you sum the outputs. And then the zero morphism is just the discard of the zero. And then you can recover these axioms here straightforwardly just by using the naturality axioms of Cartesian categories. Okay, so now we're going to actually list out the axioms of reverse derivative categories, but this is our alternative axiomatization. And this is equivalent to the original one. It's just more convenient for dealing with presentations. So the first axiom, so we've called ours ARD1 to ARD4 instead of RD1 to RD7. So this first one is basically defining the reverse derivative on the required base structure, which is Cartesian left additive structure. So it's these comonoids and monoids. So we're basically just defining R on all of the structure that we have to have, and on composition and tensor product. So that's the first axiom. It's basically when we come to add in new generators, we actually don't need to worry about this axiom because obviously it's fixed on the structure that's already there. So the second axiom is additivity of change, and this is basically saying, well, if we go back to our previous intuition for the reverse derivative, saying this takes a point and a change in input and it produces, sorry, a change in output and it produces a change in input. This is saying if you sum two changes in output, then the resulting change in input would be the same as if you did those independently and then summed the changes in input. I hope that made sense. The easier one to understand is, of course, the zero. So it's just saying if you want to achieve a zero change in output, you should have a zero change in input, which makes more sense. And you can see how that kind of relates. In fact, I think in the extension to monoidal reverse derivative categories, they actually frame this axiom like this as well. That's quite nice. Then the last two axioms are basically just to do with higher derivatives and linearity of change. They're not actually different from RD6 and RD7 in the original paper. They're just like graphical versions. So I don't want to really talk about them here, especially because I then have to talk about the forward derivative structure. So every reverse derivative category also has a forward derivative structure defined in terms of the reverse derivative. But we don't use it at all, so I'm not going to mention it again. Okay, so those are our four new axioms for reverse derivatives. ARD1 to ARD4, they're equivalent to the original axiomatization. And Now we're going to use this re-axiomatization to show how we can throw in more stuff to an RDC and still have RDC structure. Okay, the gist is basically, if you have your category C, which is a presentation, and it's an RDC, then if you want to add in a new generator, call it S, and some new equations, in this case, let's just say there's one equation, L equals R, so left-hand side equals right-hand side. Then first we define our reverse derivatives. We have to pick one based on intuition, which is going to work. Then we have to check it's well defined so that the left-hand side of the equation equals the right after we apply R, which obviously we have to do that. And then finally, we have to check that the newly defined R satisfies equations 2 to 4. Because obviously equation 1, sorry, ARD1, axiom 1, defines the structure only on, sorry, defines the reverse derivative on the base structure only. So it doesn't involve our new generator. Our new generator S. Okay. So now we redefine the axioms. So now they're kind of presentation friendly. We've got this extension theorem, which is going to let us stuff new stuff into the presentation. So now we're going to build up polynomial circuits by adding, we're going to sort of incrementally add stuff bit by bit and use this extension theorem to continue having reverse derivative structure. So we'll do that in this definition part. Then I'm going to talk about its relationship to this category poly sub S, which is basically tuples of polynomials. And this comes from the original paper, the 2019 paper of reverse derivative categories. Yeah, I mean, I just want to link them. And then we'll have some examples of particular semi-rings and polynomial circuits. Okay, so the definition, we do it bit by bit. We start with the Cartesian left additive structure. We add in a multiplication. Then we add in constants and equations of those constants. Oops. So the left additive structure we've seen already. It's the copy, discard, addition, and 0. We need all of the equations. And the reverse derivative, we can't define, it's fixed by the first axiom. So far we haven't forced ourselves to use a prop here. So actually these are just arbitrary objects. We don't yet care what the objects of the final category are. So this is kind of slightly more general than polynomial circuits at the moment. Okay, now we're going to add in the multiplication. And again, kind of just for intuition's sake, we think of this as just multiplying elements of the semi-ring S. So this sort of logic gate, well, not logic gate, this little operation here multiplies its 2 inputs and produces their output here. And this is a constant 1. So again, it's a commutative monoid. And we also have to have these additional equations down here. So distributivity and annihilation. Distributivity is, the very expected equation that if you multiply something by a sum, then it distributes over the sum. And this here is saying that if you multiply something by 0, you get 0, which you actually need in a semi-ring. Although you can actually derive this one in a ring, but not semi-ring. Okay, so the reason we named this structure Cartesian distributive category, which I'm not sure is that best name actually, but the reason we named it is because the same reason as before, we haven't yet fixed ourselves to working the prop. So actually this is kind of more general. You can add this structure on top of an RDC, and using that extension theorem from earlier, we can actually define the reverse derivative. So we can add in this multiplication and still have our reverse derivative structure. And the way you do that is by defining your reverse derivative like this. I realize now that this looks a bit mysterious, like why is this defined this way? But it basically comes directly from the definition of the reverse derivative for poly sub S. It just turns out to like generalize a bit. I'm sorry I haven't explained that really. So we can add in this Cartesian distributive structures. That's the second thing. And now the last thing we have to do is add our constants and constant equations. So to actually get polycirc as well, we're now fixing ourselves to working as in a prop. So polycirc sub S has objects that are natural numbers, or one generated object. And we're going to add in, for each element little s of the semi-ring big S, we're going to add in an element of this type. And we also need to add equations that say when you add two elements, you get the sum of those elements. This is basically just importing the addition and multiplication from the semi-ring big S. And obviously this is, in some cases, quite a lot of axioms. So if you take polycirc sub natural numbers, this is an infinite number of axioms, which is not the best. But actually, often there's a finite axiomatization of polycirc sub S for some semi-rings. I'll show you some examples of that in a minute. So the way we turn this into an RDC, because we still have to define our reverse derivative, well, we just do it like this. So the reverse derivative of a constant is just discard, and the reason for that is because this is the only morphism of its type. If you think about the type of the reverse derivative here, it's a 0 to 1 morphism, so it goes to a 1 to 0 morphism, and so there's only one of those, which is discard. Okay. So I promised there would be a finite axiomatization of polycirc sub n, and in fact, it's the free Cartesian distributive category on one generation object, which means it's polynomial circuits, but you don't need to do any of this. It already has the constants, so the constant for a natural number is just repeated addition of 1, basically. So we can define repeated addition like this. So it's just, so n-fold repeated addition is just n copies and n additions. And then to get the constants, we just slap a 1 constant on the front of that. So yeah, that's nice. It has no additional equations. We can see another example that actually does have one additional equation. So it's still a finite axiomatization. Well, if you allow like polymorphic generators. So in this case, it's just the equation that says like 1 plus 1 is 0, or like repeated addition once is the same as 0. And you can do this more generally for like modular arithmetic. So n-fold repeated addition 0 for polycirc z sub n. Okay. Now finally, I'm just going to relate this to tuples of polynomials. So if we talk about a morphism from m to n in polycirc S, so these are natural numbers now because we're working the problem. This I claimed earlier was an n tuple of m variable polynomials. So if I skip down to this example from the introduction, this is a 1 tuple of 2 variable polynomials, and that's exactly the polynomial on the right. If this little circuit here had 2 outputs, there would actually be 2 polynomials, so it would be a 2 tuple of polynomials. And these two categories are actually isomorphic, but you can think of poly sub S as being like kind of a normal form for these diagrams. So you have to use the Cartesian structure to turn it into just like a list of functions, one for each output. The problem with using poly sub S here is that we don't in general have enough here for machine learning. We don't have functional completeness in general. So we are going to want to add some more stuff, and it's a lot easier when we have this like extension theorem, everything's a presentation, we can just throw in one new operation and check some sort of limited conditions. So that's what we're going to do. So I guess I'm just going to go through these 4 points. Quickly recap why it's useful in a bit more detail. Going to give the formal definition, which I guess is not super useful in a talk because it's fairly obvious what it's for. And then I'll give examples of where we already have this for some choice of semi-ring. And then finally, we're actually going to extend our category of polynomial circuits to be functionally complete. Okay, so if we think of this category, polycirc sub S, as a sort of syntax for machine learning model, then when we actually want to evaluate them, we're kind of interpreting them as functions. So again, M and N are natural numbers here. So if we interpret an M to N morphism, it's really going to be a function from an M tuple of inputs to an N tuple of inputs. And we want our syntax to be powerful enough so that any such function can be expressed. And that's what we call functional completeness. There's a kind of neural network analog to this, which is these universal approximation theorems, which say, if I can remember right, something more or less like, a neural network can approximate any function to some degree. And from now on, now we're fixing finite semirings. So everything up to now was arbitrary semirings. Now it's finite. Okay. So just to be a bit more clear, when we do this interpretation, there's a functor from polycirc sub S to this category Vincent sub S, which is just a prop where the morphisms are functions. And polycirc sub S is functionally complete when that interpretation functor is full and identity on objects. So here's examples of where we already have functional completeness. The first one is polycirc Z2. So we already said that earlier on when we were working with this category, this paper a couple of years ago. It's functionally complete, which is nice. The idea is we have addition as exclusive or multiplication as and this is kind of well known that you can build any combinational circuit out of these two logic gates. What's not an example of a semiring that is functionally complete is this one. So if you, instead of exclusive or, if you take or, then you no longer have functional completeness. You could throw in a NOT gate to make this function complete. We're going to do something different. Specifically, what we're going to do is add something which will map to this function, so the comparison. So this takes two inputs, x and y, and it returns 1 if they are equal and 0 otherwise. And the way the reason this gets you functional completeness is because it allows us to encode the function table of any m to 1 function. So the reason it's enough to do an m to 1 function is because we have Cartesian structure. So if we want to do an m to n, we can just do n m to 1 functions. But the point is, we're going to encode a function table. So for example, this one, which has 2 inputs and, well, obviously 1 output. And for a given pair of inputs, we're going to basically compare our input against each row of the table and output the correct answer. The question is, how do we encode this with just comparison, addition, and multiplication? It's like this. So this here is basically an encoding of the whole function table for f. So this f, use of f here is just syntactic. These will all turn into constants because obviously this, if we expand out this sum, it doesn't involve the input x anymore. So just to do a concrete example of what this is actually doing, if we have the function x plus 2 in integer modulo 3, there's a single input here, then we compare x to 0. If it's 0, we multiply by 2. Sorry, if x is 0, then we multiply by 2. And the point is that only one of these compares will ever be 1. So only one of these lines will ever sort of turn on. And then when we multiply 1 with something, obviously you get the thing. So this should be the function f. Okay, so then the kind of theorem we get out of that is, if that monoidal interpretation functor from earlier, if in its image we have these things, so constants, addition, multiplication, and comparison, then that category is functionally complete. There's a cool example of where we already have this. So we saw that for Z2 it's already functionally complete. We kind of just appealed to it's already well known. But actually you can prove it for any prime P using Fermat's little theorem, which is quite fun. So this expression evaluates to 1 when a is greater than 0, and it evaluates to 0 when a is 0. So this is the non-zero indicator function. So using this, we can build the 0 indicator function, which is the function that returns 1 if a is 0 and 0 otherwise. So we do that like this. And then using the zero indicator function, we can build a comparison function like this. So that gets us for any prime p, we have modular arithmetic. Modular arithmetic modular prime is functionally complete for our purposes. I don't know, I just think it's quite a neat example. Okay, so now we have to extend polynomial circuits with our with some syntactic widget, which is going to map to the compare function. And so we just throw in a comparator gate. Sorry, I sometimes say gate when I mean generator, but same thing. And we add in these equations, which say if two constants are equal, when you put them into the comparator, you get a 1, and when they're not equal, you get a 0. Fairly standard. So now we need to make this a reverse derivative category, so we can use it for machine learning, obviously. So we have to define R and check the A, that it's well defined, and B, that it satisfies its axioms. Obviously, I'm not going to do that here, but we did do it. And we choose as our reverse derivative this thing, which says basically you copy the change in output to the change in inputs. This seems like quite a weird thing to do. It's not immediately obvious that this is at all reasonable. And I don't have a nice math justification for this, but I do have an appeal to empirical machine learning literature, because this is something people actually do already, weirdly enough. So there's often, in some neural network architectures, they have things like thresholding functions, which return 1 if an input x is greater than 0. And the problem with using these is in the backwards part of the network, where the derivative part, the derivative of this is basically 0. So if you use its actual derivative, you lose all the information from downstream in the network, and everything upstream in the network just has zeros, which, as we saw from the earlier axioms, is going to end up being 0. So we sort of lose lots and lots of information if we just use that derivative. On the other hand, if you just pass through the gradient information directly, it seems to work well. And they call this the straight-through estimator. So this is actually basically what we're doing here with the comparator. We're using the straight-through estimator. And it's just kind of nice that it seems to satisfy the axioms of reverse derivative categories. And yeah. Okay, so we defined our category polycirc as a presentation, and that means that it's easy to throw in new stuff to this syntax. We did this sort of re-axiomatization of RDCs, so they're a bit more friendly to presentations. We had this extension theorem, which let us extend polycirc with this comparison operation, and we've ended up with a class model, which is hopefully useful for machine learning, at least expressive. Cool. That's it from me.
Hey, thank you very much. Are there any questions in the room or online? One question out there. Sorry, let me pass you the microphone support. I have to hear you.
Can you hear me through the mask, or should I take the mask off?
Sorry, I can't hear very well.
That's the question. So I've got essentially 2 questions. The first one's about this. When you were defining it, you said you needed a copy operator. Is this only for the parameters, or also for the kind of other degrees of freedom?
So you're talking about when we defined polycirc sub S?
Yes, and if we go back a few slides, I think you had a definition of reverse derivative, and you said you had P cross A goes to B or
You're talking about here?
these kind of things. Is the copy only required on the P space, or is it also required on the A space?
Oh, so the copy is on every object. So
Has to be on every object, and you use it on every object in your proofs.
So you need. So the reason I've written A here, sorry, I guess it's kind of overloaded. This in your category, every object A should have a copy. Oh, whoops, sorry, a copy like this.
Yeah. Okay. And the second question is about your extreme case that you gave. It reminds me a little bit of Monte Carlo simulation or simulated annealing. Have you thought about that at all?
Sorry, which case?
You gave an extreme case, which is where you just bit flipped as your updates.
Yeah, this one, right?
Yeah. Have you thought, that reminds me a bit of Monte Carlo simulation or simulated annealing. Have you thought about that at all?
No, not at all. I'd love to hear how that like relates. That seems like I guess I kind of see how that. Yeah, I don't know if you want to like talk about that more afterwards. I guess I don't really see.
Yeah, I can send you an email and
Yeah.
I'm probably at the same state as you, that this vaguely reminds me of this, but I need to think a bit more.
Yeah, I kind of see what you mean with that, but no, I haven't thought about it to actually answer your question.
Okay, thanks.
Okay, I think we have time for one more question.
Morning. Sorry if this is a really ignorant question. I can see how this, I'm not a mathematician, by the way, I'm a machine learner who snuck in to learn this stuff. I can see how you can use this to express machine learning models. But what we really, really need in the field is a way of comparing different models. At the moment, people count layers and we all count them differently. Or we count parameters, but you can't do that with different architectures. Can you use this to solve this problem for us?
Well, I think Fabio might have a better answer to this question. I don't know if he's around, but I think what you want basically is like distance between morphisms, kind of, right?
Yeah, something like that.
Yeah. I haven't thought about that at all, but I think Fabio might have. I wish he was around. Yeah.
It would settle a lot of other arguments down the pub as to which model is better. So please do work on it.
Okay, I think we have to move on in the program. Thanks very much, Paul, for a great talk. Right. So maybe if the second speaker could share the screen. Yeah.
Yeah.
We can hear you.
Just a minute. Yeah. Can you hear me?
Yep, we can hear you.
Okay.
And we can see your screen.
Okay.
Okay. So the next talk is by Sidiney, who's just blocked his last name. Sidiney Montanhano is giving a talk about characterization of contextuality with semi-module Czech cohomology. Please.
Okay. Oh, thanks for the organizers and the opportunity to present. I'll present to you one of my works about the relation between contextuality, that is a kind of non-classicality, and the use of topological tools in spatial Czech homology to identify such behaviors, non-classical behaviors. Okay, so the idea here is that I will present you a crash course of one of the approaches to describe contextuality and the use of Czech homology to identify it, and the generalization that I propose to characterize it to correct some failures. Okay, so just as a crash course in the sense, contextuality is a kind of classicality that is defined in a categorical sense, especially with using the sheaf theory. Is defined as something like that. We start with a set of measurements, X, and a set of contexts, and that defines a site with the inclusion as morphisms. So, as example, I give it here is usually in literature the using of a bundleless diagram that defines where the vertices are measurements and the contexts are the hyperhedges here. And we have a well-defined inclusion of these measurements into context and subcontext into context per se. So this is the basis, and we usually impose simplicial complex structure on this side. Okay, and we define for these structure, the side sheaf of events that gives for every context and every measurement a special this set of possible outcomes that one can get when we do that measurement. And here, just to say what means a context. A context can be understood as a set of measurements that can be made together in the same time. This is the idea; they are compatible in a sense, and so we can access the outcomes. We can get one of the outcomes for each context at one time. And with this sheaf of events, we can, with the restriction of the events as morphism, the sheaf structure imposes the usual condition that says that if a local event can be understood as the restriction of a global one, is the main idea, and we have a consistency between intersections of contexts. Well, contextuality is usually appears in quantum theory and post-quantum theories, and the main idea is to describe a distribution on the outcomes, and we are searching for a global description of these outcomes, such that the context becomes just a limitation when we do some measurement per se, and not something fundamental. The idea that a theory that depends on the contexts, and the contexts are non-classical. This is the idea; cannot be described as with classical tools. So to do that, we usually work with distribution on a semi-ring, usually the booleans to deal with the logical paradoxes that appears with non-classicality, or the probabilistic semi-ring as quantum theory uses it. And to do that, to codify it, we define a press sheaf D with a semi-ring R that give us a distribution for each set of outcomes definable in the context. So we can just compose this press sheaf with the sheaf of events, and we can play a little bit. So we have a distribution for each context, and we can only access each one of them. So in a sense, it's a problem of marginalization. Well, we need to impose a condition known as non-disturbance that, for example, quantum theory satisfies and other theory satisfies, with a condition that says that the distribution must agree between the intersections. When we put intersections in, intersect by restricted to the intersections by different contexts, we need to agree what the distribution are in this restricted area. And we say that these empirical models, we call that is the set of the side plus the sheaf event and the press sheaf. It is non-contextual if you can write out each distribution for each context as depending only on the combination of the distribution for each measurement, plus some hidden variables, lambda distribution on hidden variables that we need to take into account. Some sense of the intuition is that when we are, for example, in thermodynamics, we needed to coarse graining or ontic states to get some results. Here, the idea is almost something the same, that we need to coarse grain the hidden variables to get the usual distribution that we have access to. to each context. In the sense, we don't need it to, the context is just a special limitation. And to define this non-contextuality, we needed to impose that these hidden variables are independent of the context itself. That's the common common classical description of it. And if we impose that this distribution over the outcomes are deterministic, so there's a property called outcome determinism, then these hidden variables can be understood as the global sections of the Schiffer events. So it's a theorem proved by Abramsky and Bonderberger in this paper. And the main idea here that you can understood is that the distribution for a non-contextual theory, a non-contextual empirical model, we can restrict, we can find out a global distribution, defined on the global events, such that the distribution on each context, on the events of local events for each context, can be described just as a restriction of this global one. This is the main idea. In some sense, it's the marginalization problem. We want to find out the global distribution given a set of local distributions. Okay, I just talk a bit about Czech homology, and I will use the language that I said before, just to keep the idea. In Czech homology, we usually start with a nerve that describe the intersections, the non-empty intersection between contexts here. And this nerve forms has a simplicial complex structure. Then we can play a bit with topology into it. And we can define the map like that. It's just the map that takes an object of the nerve and takes erase one of the contexts on its definition. That's related with the border operator on this simplicial complex. And we need to define a pressure that we will work with that takes and the nerve to the category of abelian groups. And we suppose some conditions. And the first condition is that the pressure of any element is non-empty, so it's non-trivial. So we have, if you have some information in the nerve, we need to have some information in the abelian group. The pressure is called flask beneath the cover, and the main idea of this property is that all the information of that lies in the intersection must live in the context itself. So we can access all the information of a subcontext, for example, intersection with the restriction. And any compatible family induces a unique global section in the sense that we can access, giving a local description, we can access a global one if you have compatibility. So with this, we can define the set of cochains with this pressure, and we can define the co-border map, co-border operator, as usual, is related with a description of the usual topology, algebraic topology, and we can define a complex of extended complex of cochains. And one can show that this co-border operator, when we compose them, we get the trivial operator. Thus, we can define and play with cohomological groups as usual, defined on the kernel and the image of it. if co-border operator define a moment. So this is the idea of Czech homology, and we use this Czech homology to create tools to identify contextuality. So that is called cohomological contextuality. That was first used by Abramska again, and Mansfield and Barbosa, and its relation with not just contextuality but locality also. That is a special kind of contextuality, as they proved in this paper. So we use here the relative cohomology. We start with our pressure, but we fix one context that necessarily gives us the pressure of the intersection of the fixed context with the one of the argument. And we can define a map that does it, that between these two pressures. And with this map, we can find an exact sequence that defines with the kernel of this map P another pressure that's, I will call here the relative pressure. And this is the one that we will work with. This is especially codifies all the information that lies out the context. So the recipe to get the information from this cohomological construction is to fix a section. We'll fix a local section defined on the context of this pressure F. And because we impose non-disturbance condition, one can readily show that this section, this local section has sections that agree in the intersection, in the sense locally, in the context next to it. So we can find out sections that satisfy this condition here. And with it, we can define a family with this condition that defines this family here that lives on C0 of the original pressure. And we can apply the co-border operator to it and find out this is object Z. That one can prove, it's a theorem that it lives in the set of coborderies, cocycles of the relative pressure. Then the idea is just to define this object as the obstruction. So the obstruction is the cohomological class of this object Z that lives in this, using the usual tools of this cohomological group. So the main idea here is that we fix a section and we can define a family with it, and we can use the relative pressure to investigate if we have an extension to outside that context. Information makes sense outside the context that originated it. And the obstruction is the object that measures it in the sense. And this is exactly the proposition that was proved by these guys, that if you have connected simplicial complex, so the site of contexts, and taking a fixed context and a section of it, one can show that if you have trivial obstruction, and this is equivalent to existence of a compatible family, in the sense that one of the sections, the section that lies on the original context, is exactly the one that we fixed. Sorry. Okay. This is the idea. In the sense we can identify contextuality once that contextuality is the violation of the extension of the distribution with this object, and one can really find out some examples of it, but there are examples that this cohomological tool fails to deal with. For example, this example here. we have the empirical model. So we have the site here and the simple possible outcomes. And here we have all the possible outcomes. So here I'm using the Boolean summary. And one can see that these diagonals here, if you try to extend it, we cannot find a path that closes it. So this is the idea that we have contextuality. These diagonal sections here cannot be extended to a global one. So it's the example of contextual empirical model. But if you use the cohomological contextuality and you use this cohomological tool, as we are working with groups, the group structure allows us to use inverses, the negatives. So we can, it's a possibility to define the object as this diagonal, and I think you are seeing my cursor. So, we can pass for this diagonal and come back from this section and back to the diagonal. So, using the cohomological tools here, these sections that must show contextuality can be used twice, and we find out a fake global section in the sense of the original pressure that is not captured by the pressure using groups. So the structure of groups violates it. And the point is that all the point of this is that what we are doing is to pass a problem, define the category of SEM rings, the rig, right? The rig category to the category of rings. So we are losing some information in this simplification to use the tool. So the main idea is, okay, the group structure, think of, don't get it, so we need to maybe keep track of the SEM ring structure from the beginning and try to use cohomology, but keeping the SEM ring structure. So this was the idea of my work. So to use cohomological tools, but with SEM models that are defined with the SEM rings. So as was defined by Pachicoria, I think it's like that. That we defined not a billion groups, but now SEM models. And well, the main problem is that we cannot define the coboundary operator. But we can define coboundary operators in a separate sense. So we need to take into account the positive and negative parts, but they are separated here. And defining things like that, we lose a lot of structure, the nice structure of that appears in cohomology. And as an example, we can of course define analogously the well-known definitions that appears in usual cohomology. But for example, if we try to define the cohomology semi-model, here we needed to define an equivalence relation to do that. And there's different equivalent relations that we can use here, and they are not non-equivalent. There's no equivalence between them. This equivalence appears when we restrict this semi-model approach to models. So they became the same. So we lose this structure. What means that we cannot work with 3 SEM models at the same time in this sequence. So we need to only work with 2 of them. And to do that, we need to define something new to deal with it. Okay. To translate it to the Czech cohomology on SEM models that was introduced by June, we do the same recipe. We start with a press shift, but now of SEM models, or SEM models, where we fix the SEM ring, satisfies the same conditions. And we can construct the cochains and the two co-border operators. And the point here is that we cannot deal with these three elements. And so, well, the cohomological contextuality uses the obstruction and especially the co-border operator. And what it measures with the co-border operator is the difference between positives and negatives, in the sense that it measures the difference when we restrict from one context and another to get this obstruction, gluing everything together to get a global distribution, global section. And well, we can do that, but we need to generalize a bit. And once we don't have the negatives and the verses, so we need to put some models to send fields. It's not a big problem physically, once that our semi-rings are still there. And we can define an application that codifies the difference between the two operators. So in a sense, we are restricting our work with only two cochains. So once we don't have access to three of them, well, we can find out that we have equivalence relation between these operations. So there are representatives codifying the information between these two co-border operators, and nice properties related to identity. So we can define the notion that this map is there's an operator between these two operators are trivial in the sense that they take the same information. And I call this operator the difference operator, that are getting this information between these two co-borders. So again, the idea is to use relative cohomology. So the proven, in a sense, the idea follows the construction before. We start with the relative cohomology, so we can define the map P between these two pressure shifts, and define the pressure shift, the relative pressure shift, and define the map P. But now we need to take into account what it does in this pair of objects. So we need to take into account what it does with the difference operators. And the receipt is the same to play with it. So we start with a section of a context. We define a family using non-disturbance again. And and we can define obstruction, but now the obstruction does not use the co-border operator. We need to take into account this difference operator here to relate it such that it is trivial when it's equivalent to the identity. And so define the obstruction like that, we can write out the same theorem before. So let's connect it, let the side be connected, and taking a context and a section of it. So the obstruction is trivial if and only if there is a compatible family, such that we can find out the original section as an element of it. So again, the obstruction here measures how we will, if you have any problem to extend the initial section. And as we keep track of all this, all the semi-ring stuff, in a sense, one can show that that appears on my work, that we have given an empirical model. It shows contextuality if and only if there is a section such that we have a non-trivial obstruction of it. So this is the idea. So in this sense, this construction, this kind of cohomological tool, really characterize this non-classical behavior. And well, there's relations between different approaches, especially to the cohomology with of effect algebras. There is more details discuss about it, but I think that for now is enough. So thanks.
Thank you. There is a very quick question. Please ask it. No, then I think it's time to move on to the next. Oh, Ross promises a quick question.
Hiya. Can you say anything about the complexity of finding the obstruction if it exists?
I'm not hearing.
Can you say something about finding the complexity of finding the obstruction if it exists?
The complexity of finding the obstruction. I don't know if I understood it. No.
Okay. Ross says he might contact you afterwards online. Yep.
Okay, thanks.
Okay, let's move on to the next talk. Is that a in-person talk? Is that right? Yeah. Yes. Do I share the whole screen? Oh. Full screen.
Is this correct?
Yeah, let me see.
This is the one. I guess this is the second you said.
Yeah, this is the one. Yeah.
If you put this on, put that in your pocket. Here? Can I say something?
Okay. Yeah. Is it good? Can you hear me? No? Is it? Okay, good.
Okay, so the next and final talk for this session is entitled Simplicial Distributions and Quantum Contextuality, and is given by Cihan. Okay.
Thank you very much to the organizers for giving the opportunity to present this work. So this is joint work with my postdocs, Aziz, Kharoof, and Selman, Ipek. So what we do is to introduce a new notion, new objects called simplicial distributions, and apply it to another notion from quantum theory that Sidiney mentioned, quantum contextuality. So the basic idea is to represent measurement statistics of some measurement. It can be quantum or classical in a topological way. So I will be, of course, more precise about the topological way here. Everyone probably has a different idea. So it will enter in a particular way into the picture. The idea here is about the experiments to keep in mind is that there are two people, two parties performing measurements, Alice and Bob. There are inputs, which are the measurements labeled by XY, and there are outputs labeled by AB. So these are usually binary, and they will be binary in the talk. And then this example is important, so I will revisit this example after giving the proper definitions. So here, Alice and Bob are given two measurements each, and the outcomes are still binary. The measurement statistics means essentially that for each outcome, you have a probability table. And so Sidiney mentioned about context. In this picture, context are the boxes that appear here, 4 boxes for each pair of possible measurements. So the outcomes are 0, 0, 0, 1, 1, 0, and 1, 1 for these two measurements. And then you just arrange your probabilities in this way into these 4 boxes. In general, we are interested in these tables, but they have an extra condition called the non-signaling condition. Outcomes of measurement statistics of quantum theory satisfies these conditions. And they are actually given by these equations, but you can think of it as follows. Within a fixed row or a column, if you sum the numbers, probabilities in each box, they're supposed to match. So that's what it means. So these equations. I will revisit this example. So this is a very famous scenario called the CHSH scenario. It's a particular type of Bell scenario. After giving the proper definitions, the simplicial distributions and so on. So what do I mean by a space? It's quite a categorical notion of a space. It's called simplicial sets. So it's simplicial sets. They're functors from a certain category called the simplex category, which I will define, opposite of that category to category of sets. And the morphisms are just natural transformations. So this is the category of spaces that I'm going to be working in. Well, intuitively, we have these basic basic units, which are triangles, or they can be edges or points, depending on the dimension you're working on, or they can be like tetrahedrons or higher dimensional simplices. So you essentially start from those and then glue them to obtain a space, like in the picture. So the simplex category is the main thing here, which encodes how the simplices are related to each other. So it's very well, simple to define. So its objects are natural numbers, which you can think of as sets from as like sets of this form, which has this natural ordering. And then the morphisms are order preserving functions. So that's it. So that's the spaces. And these are very useful in modern homotopy theory. So we will include probabilities into these simplicial sets, and then they're going to be modeling distributions on spaces. So these are going to be the simplicial distributions, which will generalize these non-signaling distributions that people work with. But before that, of course, I should give it. How do you think about spaces? So one way to think about them, I mean, I think category theorists would think differently, but if you want to think about it in a constructive way, so you have this delta n, which is the basic n simplex. So I would like to introduce it as follows. So I just tell you a generating simplex in certain dimension. So this is representing, say, in dimension 2, this whole thing, and then applying the phase and the degeneracy maps. So these are coming from the structure of delta. So delta has two kinds of morphisms, the simplex category. They are called the cophase and codegeneracy maps. If you dualize them, you get the phase and the degeneracy maps. So in this picture, if you start from this simplex, which is essentially the string from 0 to n, you can generate all the other simplices by deleting the ith index or duplicating copying the jth index. So if you look at the phase maps, you just omit the indices here to lower the dimension, as you see. And to get the degeneracies, you just duplicate the indices. So it's quite straightforward. And then you get all the simplices in various dimensions. I'm going to be focusing on the phase maps because they're going to be encoding the non-signaling conditions. Degeneracies are important as well, but they're a bit harder to motivate. From the topological point of view, phase maps tells you how to glue simplices, and the degeneracies, while this combinatorial description has some degeneracies, you have to collapse some stuff to get to the real spaces. So that's the role of the degeneracies. But I will be focusing on the phase maps mostly. Sidiney mentioned about this functor. So this is R distributions. I will be focusing on non-negative reals throughout the talk. So given a set U, you can talk about distributions on this set. This is essentially a function of finite support which whose values sum to 1. You can elevate to a functor by pushing forward a distribution on U to V using this the sum of the probabilities in a preimage of a certain element at V. That's the formula. And once you have this functor, well, okay, so there's another piece of information. So there's a natural transformation from the identity functor to this functor dr, which gives us deterministic distributions. So at a specific set U, you're sending an element to this delta distribution, which is peaked at the element U and 0 elsewhere. So, okay, so that's the starting point of the scenarios. So if you remember the non-signaling description, the first picture I gave you, what is the component? So there's a set of measurements and set of outcomes. So these are sets. And then you can define this probabilities associated with the outcomes. So in this simplicial setting, we want to elevate these sets to spaces. So you start from a space of measurements and a space of outcomes. They're modeled by simplicial sets. The n simplices of X, they correspond to contexts, but they have also a dimension attached to them. And the outcomes here are also come with a dimension. Well, we have the dr functor. You can just compose it with Y, which was also a functor, to get the space of distributions on Y. So this is the definition of dry. So it is quite straightforward to see that dr actually upgrades to an end-of functor on simplicial sets. And there's also a similar natural transformation, this time from the identity functor on simplicial sets. So what's the simplicial distribution? So that's the generalization of non-signaling distribution. Given a scenario, a simplicial distribution is simply a simplicial set map. You can think of it as a natural transformation from this functor x to this functor dry. Or if you are explicit, then to an n context sigma, it associates a distribution p sigma on the set of n outcomes, which is compatible with the phase in the degeneracy maps. This amounts to satisfying these two equations, first for the phase maps and the second for the degeneracy maps. Okay, so now comes the definition of contextuality. So for that, we need a comparison map. On the right-hand side, we see all possible simplicial distributions. So these are simplicial set morphisms from x to dry. On the left-hand side, we have the distributions on the set of simplicial set maps from x to y. So there's a natural map. How do you define it? If you're given a map R, simplicial set map, you just compose it with delta. That was the natural transformation, of course, at y. I'm missing the subscript here. And then you get a simplicial distribution. So that's the map delta. Theta, this is induced by that. So you have to kind of extend it to the probabilistic mixtures. So it works. So now the definition of contextuality, which generalizes this, the notion that Sidiney mentioned, or more precisely the sheaf theoretic notion. So a simplicial distribution is called contextual if it does not lie in the image of theta. So this map here, just to remind you. So this part, the image here is called, it's kind of the classical stuff coming in. So contextual if it does not lie in the image of theta, otherwise it's non-contextual. So okay, so I said that. This generalizes this notion. Okay, so now examples. The canonical choice of outcome space throughout the talk will be this nerve of Z mod 2. This is a famous space in algebraic topology. You can define group cohomology using this space. So it is a special case of nerve of a category. So you think of the group as a category with a single object. Well, I'm not going to define it properly, but because I'll tell you what it is in the picture. The reason for choosing this space is, so in this sheaf theoretic approach, I said there's a way to embed this into our framework. There are actually multiple ways of doing this. The canonical one actually takes these sets of measurements and outcomes as zero-dimensional objects, but we want to shift the dimension by 1, and that's essentially the reason for choosing this particular space here as the outcome space. So if you have delta 2, this is the triangle. A simplicial distribution is a morphism like this. Well, in pictures, what it amounts to actually, if you unravel this, you have this one of the boxes in the first picture, right? So there are 4 numbers here. You actually rearrange them into this on this triangle like this. But there's an extra information you obtain. Here, you only see the XY measurements. Here, there's a third measurement, which is the XOR of X and Y. So the XOR is obtained by taking the modulo 2 summation of the outcomes. So if you arrange the probabilities in this way, the sum of the 2 here is going to give you the marginal on this edge for the outcome 0. And this way you get the measurement Y, and this way you get the measurement XOR. So that's just naturally arises. The reason it arises because of the choice of the outcome space, in fact. But anyway, so instead of thinking about what this is, you can just think about it in this picture as this triangle. So D maps here are the phase maps. These are just encoding the marginals. Well, as expected, every simplex is supposed to be non-contextual. For the triangle, you can just take these 4 numbers and put them as coefficients in front of your deterministic distribution. But if you start gluing triangles, you get something non-contextual, and that's kind of the topological stuff coming in. This CHS8 scenario here, we have a triangle for each. You start putting these triangles here, and then the edges, they correspond to measurements like x0, y0, x1, x1 repeated here. So I have to glue these two. Y1, x0, x0 repeated here. So I have to glue there. At the end, these 4 triangles arranged into a punctured torus because this middle part is missing. So that's a topology. That's what I mean, how topology enters precisely. Well, this is a very famous theorem from 82, Fine's theorem for CHS8 scenarios. It says that a distribution is non-contextual if and only if it satisfies the CHSH inequalities. Something I forgot to say, simplicial distributions on this scenario is actually precisely the non-signaling distribution. So such maps are the usual stuff that people work on. So here the distribution on CHSH scenario is the same thing. But there will be something that we gain out of this new approach. So yeah, the CHSH inequalities, as you see, are given by these 8 inequalities. And the only probabilities appearing are the XORs. So already you see something happening. You make a statement about a distribution on the torus, punctured torus, by, you know, it is determined by just restricting it to the boundary. So the XORs appear on the boundary, as you see. So this is the Fines theorem. If you look at the proof of this theorem, it's quite a clever construction. It is short, but it's clever, and then you have to verify a lot of stuff. It's hard to verify, but if you can actually give a pictorial proof, the proof is quite close to Fines proof, but it's not the same. So you see here another way of realizing the CHSH scenario. Instead of the punctured torus, the topology has changed. So in this case, this is just a square. It's a contractible space. So you want to show that this is non-contextual if and only if CHSH inequalities. So there are 2 fundamental lemmas. One of them is the gluing lemma. The other one is the extension lemma. The CHSH guarantees an extension from this space to this larger space. And the larger space here is obtained by 2 tetrahedrons, the boundary of 2 tetrahedrons. So we want to show that this is non-contextual. The way you go is as follows. You by hand, you show that these 2 pieces, one of the pieces is non-contextual. The other one is also non-contextual. Gluing lemma tells us these 2 pieces non-contextual, then you can glue them as long as you're gluing a simplex along a simplex. So this is non-contextual. An extension lemma says that under certain nice conditions, this large thing is non-contextual, then this is non-contextual. That's how you prove the Fines theorem. But there's something extra. If you look at the other realization, which is the punctured torus, you get a new characterization which says that a distribution is non-contextual if and only if it extends to the torus. So this scenario. So I just filled in here. So you put here distributions as well. Okay, so I want to make a jump to the quantum part. Instead of working with non-negative reals, you can just work with projectors acting on a Hilbert space. By which I mean a complex finite dimensional Hilbert space. So it's supposed to be PHY here. So you can construct a functor PH, quite similar to distributions. These are called projective measurements. And then if you take a quantum state rho, which can be defined as follows, for any projector, this formula gives a probability, which is rho times the projector, and then you take the trace. So these are quantum states rho. And this association is functorial because I mean trace is linear, so it is just gives you a natural transformation from the functor pH to the distributions dr. So the upstairs, these are called simplicial projective measurements, and this BR means the Born rule. So you have this given a measurement, you get a simplicial distribution rho star pi. So now you can talk about quantum contextuality. A state rho is contextual with respect to a simplicial measurement if the simplicial distribution rho star pi is contextual. So that's a generalization as well of this. Well, it's a generalization. And the idea here is to also generalize the other paper, which is due to myself, Robert Sparklet and Robert Rosendorf. So here there's some group cohomology appearing, and you can also import that stuff into the framework. This extended framework. Okay, so I want to finish by formulating 2 foundational results in this framework. So this is quite categorical in the following sense. So there's a theorem by Gleason which says that if you take a Hilbert space of dimension greater than or equal to 3, well, it's formulated in this way. So you first have the outcome space S1, which is smaller than the nerve. You just take the 1 simplex and glue the endpoints. So projective measurements, and then you have the distributions on S1. And these S1 to delta, so these are the canonical maps. So you have a similar one going here, like the distributions. So any commutative diagram like this is given by the Simplicial Born rule, meaning that it's given by essentially a quantum state. So this is Gleason's theorem from 75. It is not a proof, but just a reformulation. And there's a corollary, which, well, it's proved earlier, but you can obtain it from Gleason's theorem, which says that the canonical map does not split under the same condition on the dimension. And you can say something about quantum contextuality if you take the identity map as your simplicial measurement, where this one is your space of measurements and S1 is the space of outcomes, then this theorem implies that every quantum state is contextual with respect to the simplicial scenario. And that's all. Yeah, thank you very much.
Time for one quick question again. The microphone coming.
Is the structure of contextuality and distributions of all of this compatible with the homotopical structure of simplicial sets? So are there statements about contextuality that transfer, for example, along homotopic equivalences?
Sorry, what is the last bit you said?
Are there statements about contextuality that transfer along weak homotopy equivalences of the space?
Yeah, so I mean, yeah, so there's not something that sees the homotopy type and then you can not really conclude about the contextuality, because as you see, I mean, a scenario can be realized in multiple ways with totally different topologies. So that is not the case. So the topology, the homotopy type of the underlying thing does not immediately say something, but there is ways to use simplicial homotopy to detect extreme points in the polytope of morphism. So the simplicial set morphisms is a polytope, so you can actually say something about the extreme points using some simplicial homotopy, but it doesn't really work, you know, with weak homotopies. Yeah.
Okay, coffee waits, so let's thank the speaker again. Right, we'll have a coffee break now, and we start again at 11 o'clock. If you haven't done the registration or conference dinner payment, then someone will be waiting outside for that.
How do I fill it out?
That's a good question. Not at all trivial.
Did you see that? Yes, there's the microphone. Yeah. This microphone is appropriately volumed.
Yeah, I wonder we can maybe we can make an experiment.
Yeah, we can do that.
Because the speaker was wearing it quite low, so maybe it's just a matter of. But it's working otherwise.
Yes, the air conditioning is also working.
I think it's getting colder. Yes, that's what I thought.
The air is rushing out of this room. So if the air conditioning is on,
right, it's mechanically ventilated. So I don't know what that means. Hi, Martha.
Hi, Frederick. Hi, Glasgow. Good to see
Hi.
you all.
I'll just make one quick announcement and then I'll
Sure.
hand over to you. Okay.
Sure, great, thank you.
People are still streaming into the room again, so
Sure.
give it one more minute.
Will do.
Okay, welcome back. One quick announcement before we start the next session. If you find this room far too hot, then blame global warming. And after that, blame Strathclyde Estate Services. Unfortunately, can't fix the heating in this room. So if it's too hot, we have some overflow rooms, the rooms over there, where you can still see the screen, but you can't ask questions, but they are nice and cool and air conditioned. So if it's too hot here, you can go to those rooms, but then you can't ask questions. Okay, and now I'm going to hand over to Martha Lewis, who's going to be chairing this session.
Okay, hi everyone, and thanks for coming to this second session of ACT 2022. So this session, we've got 4 20-minute talks broadly themed around linguistics and NLP. And it looks as if the first speaker is Bob. So Bob, when you're ready, go ahead with talking space inference from spatial linguistic meanings.
Thank you, Martha. Sound comes through. Yeah. So I use this one. Okay. Welcome, everybody. It's very nice to be here again. So I'm Bob, and some weird stories go around on my whereabouts. So I'll clarify this a little bit, so people get really confused. So officially now, I'm chief scientist at what's called Quantinium, and Quantinium is the result of the merger of what I used to be chief scientist of, which was Cambridge Quantum Computing, which then became Cambridge Quantum, and they merged with the part of Honeywell. So now the company Honeywell. They were building quantum computers, and that part of Honeywell merged with us. So we're an independent entity. We're not dependent directly on Honeywell. So we're just an independent thing, but which is the result of the merger of part of Honeywell and Cambridge Quantum. So to make it very, so that's the whole thing. I'll just, we're getting close to 500 people, just saying. Also, Ross is here. Ross is the head of software at Quantinium. He's here too. And at the same time, I'm the head of what is called the compositional intelligence team of Quantinium, and we are based in Oxford. So there's a lot of people here. They're all in Oxford, sort of many people here from Quantinium in Oxford, all formerly Quantum Group and all that. They all flew over to the other side. Anyway, so I'll say a bit more later, but just to clarify, I live in Oxford. I'm not living in Cambridge. I'm not anywhere else. I'm not in Denver, Colorado. I'm in Oxford. And we've got a beautiful building, and we've got a music studio in the basement, paid for by the company. So it's pretty cool. So now I've got 2 music studios. Okay, so I'm going back now a few years, just for, I mean, there's many new faces here. I know many people know that story, but just to be fully comprehensive. And there was this person, Mernisha Derzadeh. She was in Oxford then. Now she just recently became full professor at UCL, and she knew about the grammar mathematics. We don't go in detail there. It doesn't matter what it is, but there is stuff out there which is mathematics for grammar, which tells you when a sentence is grammatically well typed. It goes back to lambeq was a big pioneer in there, of course. Jim Lambeq, and Chomsky did a lot of that stuff too, like on the more sort of philosophical side. So this was an old field, and she knew about that. And then there was Steve Clark, and he knew about vector space meaning. Now we're talking 2008, so there was no deep learning revolution yet. So this was still kind of an academic discipline, thinking of meanings in terms of vectors. So Steve was then in Oxford faculty, then he moved to Cambridge faculty, then he moved to DeepMind. Okay. Okay. Okay, good. And then now he works for me. So I bought him out of DeepMind. So that's the things we do. We buy people from DeepMind. And then the question, of course, comes up. What is this? And then, of course, comes up. Oh, that's subtitle. That's subtitled. I mean, I've seen some very weird stuff showing up in the subtitles because the subtitle machine doesn't understand my accent. Anyway, what's happening? Why don't you want to move anymore? I think somebody has to come back because whatever happened, my slides are not moving anymore.
Oh, yes.
There we go. Okay, so we got these two things. We got like mathematics for grammar and we got a mathematics for meaning. And there was an open question how to combine those two. It was an open question. Nobody really knew how to combine these two. And of course, basically what we did is we used categorical quantum mechanics, which was around at the time, because categorical quantum mechanics basically has the string diagrams and all that, which completely match the grammatical structure in terms of pre-groups, which is something lambeq came up with in the 90s. And at the same time, they accommodate vector spaces, of course, because quantum states live in vector spaces. So you accommodate the two together. And if you think a bit about it, it's in a very canonical way. So basically, you use categorical quantum mechanics to combine to answer this question. And just to give some historical detail, I should have had a slide about that. But I remember I was giving a talk in 2005 at the McGill category theory seminar. And lambeq was in the audience. And I presented quantum teleportation. And lambeq said, hey, Bob, that's grammar. Anyway, that's the reason, not the next talk, but the talk after will be about software called lambeq. Okay, so we did this paper. I think it's quite well known in this community, and in which we combined meaning and grammar, just to show simply how it works. So the top level here, these are you have to think of them as vectors, meaning vectors. When you see more than one wire, this means you're doing tensor products of spaces. So these are meaning vectors, and the thing you see at the bottom is actually a representation of the grammar. And formally, this just lives in a compact closed category, just like categorical quantum mechanics live in a compact closed category. So you got meaning of words, and you got meaning, and you got grammar. You combine them, and then you can do things, which is what people want to do. You can, for example, say, okay, here I've got a sentence, Alice hates Bob. There I've got a sentence, Alice does not like Bob. And you want to then figure out how closely related they are by computing an inner product. So that was the stuff you could do. People did experiments. It all worked out very well. So now I'm going to move on to more recently. So there were a lot of shortcomings with that thing people refer to this discocat. And one shortcoming, and this was inherited by grammar theory, is that you can only reason about sentences, like how words together make sentences. Grammatically, it kind of makes sense to do that. But if you're talking about combining word meanings, using grammar into sentence meanings, then you also want to say, yeah, what about if you combine sentences into text? What's the meaning of a text? So that was the thing we were looking for then. So we call these text circuits. So basically, it's a little bit of topological deformation. So this is what we had. And the first step we do is like, create an inside structure in this hates verb, like with a spider. We've seen spiders before in earlier talks. So for us, they are sort of full-blown Frobenius algebra with all possible properties they can have. So they're not just monoid, comonoid. They're much more flexible. That's how they come about in quantum. And then we sort of pull them out. Boop. So they're now out. So this is still the same diagram. And what you can do now is you can compose different sentences. So here you got a sentence, Alice hates Bob, and Bob likes Bob. Because you see, you got actually a circuit, and these nouns, they just become like lines in the circuit, and then your verbs become things that entangle different nouns in a circus, and you can go on forever there. So basically, this gives sort of a hint of that how you move from sentence to text. And something else which is really cool is in most word embeddings used in machine learning and all that, word meanings are static and disentangled of any other word meaning. They're a vector in their own right. Now, when you see what happens here is, let's look at the same. So here I've got Alice and Bob. In the beginning, they're separable vectors. And then obviously they get entangled by hate. So they become one whole. So Alice and Bob are not isolated entities anymore. They're entangled with each other. Same with Bob and beer, they are entangled with each other. It's important. I mean, so which means that, if Bob vanishes, then there is a serious problem for the beer industry. Or if beer vanishes, then there's a serious problem for the Bob industry. So they're genuinely entangled. Okay. So this was the first paper in which we did is the mathematics of text structure, but that was just like sort of touching the surface. Anyway, so another thing which we discovered in there, and that's actually bringing me to the topic of this talk. So there's the subtitle. So this is like you can't even see the names of these people. And there's a bunch of Italians here in the audience. I know you know what this is.
Yes.
Of course. Yeah. So, yeah. 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 You can do that thing away, live recording, closed captioning.
Just drag the bar.
Yes. Oh, better. Okay, we can see it now. Okay, so what I want to say, okay, we can't move again. Okay, good. So this is like a text circuit for what could be like a screenplay of a movie, but then it's sort of it's very easy to see this also in images rather than in text or anything like that. So basically what it is showing is like this two-dimensional representation is also much closer to how we cognitively think than having all the words on a line like that we usually speak. And the way I think about that is we humans, the reason we actually put text on a line is because it's the only way we can speak. We can only say one word after another. And we also get confused if we listen to different people talking together. We can't process this. So we need, it's just how we work. Our vocal interface is one-dimensional, but our cognitive interface is much higher dimensional. I've got another example here. I mean, for people who play music and stuff like that. So this is a music score. There's lots of stuff going on in parallel. And if you play in a band, like you see a bunch of ACT type people in bands here, then you can easily process all these instruments in parallel with some training. It's very easy. So in a way, I'll go back to these cognitive. These circuits are much more to the cognitive stuff. Okay, let's move on to the space stuff. So the first observation is, and this is actually going back to garden forms, that in language a lot of words are spatial, like especially proposition in, next to, after, on, with. Most propositions are spatial. They're about how things are related in space. And then there's other words like chasing and stuff like that. And then we basically use also spatial, I mean, Italians, you know, so they use space to talk. And of course, space is where we exist. And I mean, one of the big lessons of the previous generation of AI was the importance of embodying that an AI should have a body and live in space. Otherwise, you can't get them to do anything. And I mean, you could go further than that. You could actually say that space is maybe the origin of language, because when we were taking down these things, I mean, it requires a lot of spatial coordination among these. So maybe that's really where the origin of language even is. So it may be a much deeper point. Anyway, so what we do in this paper, which is what I'm presenting, and as with Vincent Wang, is we tried to come up with a model which connects linguistic structure with spatial structure. Rather than saying vectors of meaning, no, let's take spatial features as meanings rather than the vectors of machine learning, because these vectors is just statistics, probability really, and we want to actually get spatial meaning in there. So these are examples of spaces. Just, I mean, this is like my naive depiction of where we walk, and then we can jump up and then we can dig down, or subway. This is Hong Kong subway, or weird spaces. Penrose is weird space, or a chessboard. So those are examples of space. And you could go much more heavier axiomatically, but we didn't need it. Basically, we're going to work with a monoidal subcategory of REL. So the big thing to do is like, you do multiples of your space, Cartesian multiples of your space. Well, by the way, this is not Cartesian, this is monoidal, of course. That's the confusion in the language. Cartesian product in REL is a monoidal product. It's not a Cartesian product. So that's important. So we take multiples of these spaces, and then the morphisms are just what we call spatial relations. I'll give a bunch of examples of that, what that means. And then you use the usual composition in REL, like stuff. Here are some examples of spatial relations, like on a chessboard, move right. That would be this relation. Or king's moves, that would be this relation. Or next stop in a subway, that's a relation. Or in between, or my station, and stuff like that. So there's lots of things you can have. Here, these are the Cartesian one. Higher than means the Z coordinate is more. Above means Z coordinate still more, but you want X and Y to also coincide. And you can see, you can come up with like encodings of all the words. So It's quite easy to do that, like come up with like spatial encoding and like the linguistic structure, like we saw before, the grammar, of course, that exists in REL, like you got cups and all these things hanging about there. And so what we now want to do is whether our grammatical structure, when we say a sentence which describes a spatial feature, actually translates into that spatial characterization, whether it works out. So here I've got a sentence, the pawn next to a king that a knight can capture. So, I mean, this is actually a unique thing. This happens to be a unique thing, and it's this one, the pawn next to a king that a knight can capture. Here you see it, and can capture, and there's the king. So that's a unique thing. Okay, let's see whether we get there by now starting with the above. So first we got the pawn next to a king. So we do our usual deformation. Whoop, I'm pulling out the spider like that. And then we live in a compact closed category. So we can basically transpose this wire up. Boom, and you get something like that. And then basically, let me go back. Yeah. Oh, so here. So in REL, this thing is an intersection. This thing is an intersection in REL. In vector spaces, this is like sort of convolution. Like you convolute things. In REL, this is literally intersection. So we're intersecting the pawn and this. So we can now compute what we get. So we got a king next to. So that's a king next to. And this is pawn. And we do the intersection. And we end up with 3 candidates. So that's good. So we're making progress. And the one we want is still there. So nothing went wrong. Okay, now this one. This is more tricky. That a knight can capture. So the first bit is easy. Do just some fusion. Boom, there. A knight can capture. So what's tricky about that? Think about it. It's what a knight can capture. It's not what a king can capture. It's not what a queen can capture. And this wasn't yet in our model of space. So we actually have to change our notion of space. So space shouldn't just be the representation of space itself, but also your capabilities with respect to a space. Because we are an agent in space and we've got capabilities, and each chess piece has a different capability. So we extend the basic notion of space from the space, the chessboard, and then we extend it with all the moves of all the pieces. So that's our relevant space for space of a chessboard. And then if you do that, you can get a very elegant representation of can capture. So by the way, these are relations. So these 2 wires actually correspond to the spatial, to these moves, because they're relations. They're not sort of states, they're relations. And then a beautiful thing is if you then basically, so what we're going to, so when you hear the word king, since we're in spatial realm, the only thing that's relevant about the king is the moves he can make. So we identify now king with the king's moves. So this is the word king, which is now, so let's go back to where we are. So this was a knight can capture. So this is knight's moves. We stick this in and you see this nicely becomes this. And then if you stick it in everything, all of that, then you can see that we end up effectively, this is another conjunction going on, the conjunction of this part and this part, because you got a dot there, which we conjoin this and this. We had that one, here we got that a knight can capture, and boom, we end up with the right thing. So you got the translation from this linguistic structure straight into your spatial features, which is kind of cool. Now, why was I talking about all these circuits and all that? I just wanted to show you how complicated beasts we are. Oh, what happened to you? No, this is a secret. I wanted to show you how complicated we make things. So this is how we speak. This is how we speak. Now, if you say, okay, let's try to encode the same thing in 2 dimensions as a circuit, it's this. It's the same thing. It's knight, pawn can capture next to. That's it. It has all the information there. So, but we can't speak like that, unfortunately. We can't speak, but a machine can, probably. They can talk to each other like that. Here is another example, which is even big. The ostrich next to a tree that the cheetah next to the grass can capture. This is even more complicated because this is also about a speed you can get, like your endurance. There's a lot of stuff here going on. And again, you can work this out and you get where you want. But then again, if you do these as circuits, grass, cheetah next to, ostrich tree next to, cheetah, ostrich can capture. End of story. So we need to learn to talk like that. I mean, another thing you can do is like, so our chairperson, Marta, myself, and some others, Robin Pierre Deleuze, and some others, we wrote a paper about not reasoning with space, but with other sort of conceptual categories like taste and color, smell, and all that. And you can, of course, combine all this stuff together, and which is nice. And then you can actually start talking about the cheese inside the suitcase stinks. So your space has now two kind of wires, because you got like the space component, you got like the other cognitive component, which is about smell and stuff like that. Again, you can do it like that, and you can do it like that, whatever. Not important. Well, yes, important. So, okay, so we got a nice model to reason about space and how space interact with other stuff like smell, like it stinks next to the loo. For example, you can do that. Now, I don't know what my time remaining is.
Hi, Bob. You've literally got 1 or 2 minutes left.
Oh, perfect. So this is very new work, which is you don't find in this paper, which you don't find in this paper. But what we did, the three of us, Vincent, John O'Leary, and myself, is let's not just be like in the naive way, build these circuits, but let's do it for all of English. Let's see whether we can come up with an algorithm which turns all of English into these circuits, and which was a lot of work. So the first thing we had to do to actually get a beautiful mathematical statement and all that, we had to sort of understand how much grammatical structure you need to have in order that you can actually have full expressiveness for the circuit. So we came up with a more Chomsky, this is different type of grammar, this is more a Chomsky style thing. And these dots, they correspond with these internal spiders to some extent. So we conjecture that this is the same as for people who know pre-groups plus internal wirings. And then you got also pronomial links. And now I'm just going to go to a quick animation. So sober Alice, who sees drunk Bob clumsily dance, laughs at him. First thing we do is like we get rid of these pronomial links and then start to do some wirings. And then we go away from 1 dimension into 2 dimensions. We turn some blocks in. Okay, so you end up with a circuit, and you see there's higher order stuff going on. It's not just gates anymore. There's higher order stuff going on. But it's much, well, Alice sober, Alice sees, Bob dance clumsily, Bob is drunk, Alice laughs at Bob, and so on, so on. So that's all nice. And then some magic happened. And that's the last thing I want to say today, because it's magical. So what we discovered doing that, which I never planned before in the first paper on these circuits, is that different languages, like which will have different trees because of different word orders, you know. When we went from our cognitive 2-dimensional perception to language on a line, we did rule. We had to invent bureaucracy, because you can't do this in a canonical way. You have to invent new rules. In the same way, if you go from a string diagram to like symbolic bifunctoriality definition, you have to come up with bureaucracy, brackets and all that. So you have to do the same with language. And these different languages have different conventions. So here, this is a very simple one. I really love you, je t'aime vraiment. They all become the same in circuits. So this is, of course, a simple example, but we did this for Urdu too. Urdu, I've got a new PhD student to speak Urdu. We went through Urdu language, and effectively this phenomenon stays the same. So we found a structure which is universal across languages, these circuits. Even more so, it's universal.
Hi, Bob. I'm just going to cut in. You're now cutting into your next talk time.
Oh, that's okay. That's okay, because I've got I got not much to say in there.
Okay.
No, this is actually sort of an illustration. Yeah, I'm just going to say so you see different styles here. One long sentence, a few short sentences, it all becomes the same. It all becomes the same because the meaning is the same. You want it to be the same. Okay, that's it. So this is the paper is not out. It will come out in a few weeks, but I think this is beautiful stuff. Important. Anyway, thank you.
Great, thank you, Bob. Do we have questions online or in the audience? I can't see the audience, so you'll have to maybe just manage your own. Have 1 or 2 questions and then move on to the next talk.
Hello. Hi, Bob. Have you looked at this from a logic programming type perspective? So I would say very roughly hypergraph categories are the internal language.
That's what it is.
Conjunctive prologue, and prologue language, that seems like something that is.
If I remember well, Alex Toomey and Giovanni did something like that with the conjunctive queries paper, no?
Yes.
But the thing is, if you approach it from a programming perspective like that, then you wouldn't be able to do this with categories other than, say, categories of sets and relations. You couldn't do this with vectors because the structure is so fundamentally different. Maybe there's ways to do that, but the structure is fundamentally so different. If you work with vector spaces, or I don't know, then
I would say prolog fragment if it works for every hyperlog category, and that, well, that will come up in my talk. You can
Okay. In principle, it should be possible then.
Question. When you do meaning in vector spaces, like any finite dimensional vector space, you can imagine, well, that doesn't capture all of the meaning of this word. So you could have like a sequence of vectors in higher and higher dimensional vector spaces. Have you thought about this?
I mean, that's what we're doing. Huh?
But that's what you're doing.
I mean, yeah, like when I was stenciling together different vectors, but then you have to make them interact with the grammatical structure.
Okay.
So that's what we do, because like typically in vector embeddings, everything lives in the same space. Yeah. Like a noun or a verb or what adjective, they all live in the same space. Here, not. What we do, because you see like these things have different types. This is a unary gate. This is like a higher order gate. It goes on top of another gate. So these things are very different types. So in a way, this is the two-dimensional counterpart to what you're saying. And so you're composing in tensor and both in parallel composition. So this is it.
Okay. Well, if you just have like the word drunk, right? You can have like drunk as a vector in like, you know.
Oh, so we do. So in another team, Razin, who is here, is working there. We're trying to sort of decompose conceptual categories in different ones. So they work with color and all this. And so you compose your vectors by, I mean, I did it kind of with the smell and the space. So, and they're trying to learn these conceptual categories. Razin, where is Razin? Can't see. Oh, there. We're doing this like practically, yeah, with Steve Clark. Steve Clark is actually leading that.
Okay, hi all. I'm going to move us on to Bob's next talk. So I guess you're just carrying on, Bob?
Yeah.
Yeah, I think so. I'll just be a little stricter on the timekeeping on the next one. So I'm going to give you, do you want me to give you a 5-minute warning?
I mean, if the system doesn't break down all the time, I should be well within time, because this is
all right, great. Thank you.
A little closer, like maybe the other side. Oh. Does it work? Let me see. Yeah, it works. Okay.
We remove this also.
Thank you. So in a sense, the previous talk sort of a prelude to this one. It's probably the paper with the least content that I've ever written, but so surprisingly it got accepted. But I think for an important reason it got accepted, because it's not just my paper, it's our paper. That's the point. So I want this to be participative. So it's going to be fairly short, and then I hope this to be more participative. So, okay, like I'll say something more. So, oh, hey, not anymore.
Try now.
Yeah. So this is our team in Oxford, including sabbatical visitors like Sean Majid, who's on a sabbatical visit. There's a bunch of people here in the audience. Actually, this slide is from 2 weeks ago, and it's already outdated because meanwhile we got 2 more people. But so yeah, so this is our team in Oxford, and this is the kind of stuff we do. So there's a lot of stuff we do, like we're going to hear, for example, in the next talk about this. But you see, one thing we do is basically thinking about what is compositionality. Sort of a very important subject of it. And the main point of the talk is to say that we should think a little bit more about what is compositionality, because everybody seems to assume that this is sort of a given what it is, but it is not. Oh yeah, I should say we do also a lot of outreach about diagrammatic stuff and all that sort of. Thomas the evangelist is here. He's like a professional outreach guy. Is Thomas? Oh, there's Thomas, our evangelist. Right. So the questions we consider in this composition is, what is compositionality? Can you do compositional reasoning beyond Aristotle? I mean, beyond propositional logic type stuff, because these are sort of structures we need to do now. And in particular, the key target area doing theories and tools is practical quantum computing. So in practical quantum computing, compositional stuff is becoming really big, really big. I'll show you later. And we also want to do practical compositional AI, because AI is a black box problem, as everybody knows. So we need to do something about that. But can we just say compositional in this context and without any further ado? That's the main issue. Okay, so of course we've got this journal. How can you have a journal and you don't know what the title means? It's supposed to be a bad journal and the title is not well defined as we stand. Okay, I co-started it, so it's my fault too. And I'm actually the one who pushed the name compositionality, by the way. John Byers wanted applied category theory. So what is compositionality? Okay, so there are different uses of the term. This is the paper I'm talking about now. And so the notion of compositionality you'd find most as a definition is called Frege compositionality. It started in formal linguistic, but it's been very much adopted by computer scientists too, I think. And this is what it says. So the meaning of a whole, be it like a sentence, should only depend on the meaning of its parts, say the words, and how they're fitted together. For example, the grammatical structures. So that's the meaning of compositionality. You can easily translate this to programs. The meaning of a big program should only depend on its small programs and how they are plugged together. And you can do this for many things. And now what is crucial here is the meaning flows are what I call bottom up. They go from word to sentence. So you know the word and you push them up to the sentence. Interesting. So by the way, this was not Frege who came up with this definition. This thing was much older than that, Boole and stuff like that. But I mean, people call it like that. But there is also something else, which is Frege's context principle. And it says, never ask the word of a meaning in isolated, but only in the context of a sentence. So that's kind of the opposite. That's the complete opposite. It means the meanings go down. And for example, if you got a word, we're going to see examples later. If you got a word like queen, it means nothing until you give enough context and you know whether it's a band or a bee or a chess piece or whatever. Because it doesn't have a clear meaning. And this happens a lot of the time. You don't know what the meaning of red is, whether you're actually talking about wine or steak or redneck. They're all very different. So they're very different reds. So this is what's saying. And sometimes the context is enough to disambiguate, like this Alice. It'll be pretty clear from the context very quickly about which she's talking. It's like a 3-year-old kid, then they won't be talking about cryptography, like a really geeky nerd won't be talking about Alice in Wonderland. Here it's a little bit different. This is also Alice and Alice, two Alices, but it becomes already a little bit hard to sort of disambiguate. Okay, here it becomes really hard. So these are two black metal fans. Right. Grammatically, it's very different. So this is fan, and then you got a first adjective metal, and then a first adjective black. Here you got black acting as an adjective on metal, and then the noun becomes adjectivized, becomes itself an adjective, then applies to fan. Now, so the grammatical structure depends on the meaning. And if you go to a rock concert, they say, oh, there is a black metal fan. You still don't know which of the two they are, because every drummer has a big black metal fan. So anyway, so it becomes very complicated. So you got this intertwinement of meaning and grammar even. So it makes things really complicated. And so this whole Frege thing is just dead for this stuff. It just doesn't work. And we know this from modern machine learning. Modern machine learning, you train things from the top, bottom down. You train things. And when we have been implementing natural language processing on actual quantum hardware, we do the same. We train the meanings of the gates from above. So it's all top down. That's how you train. So the whole, for people who have read the original DiscoCat papers, that's all out of the window. This bottom up stuff. It's just all out of the window. But at the time nobody was complaining about that. Now I am, and things get really worse in quantum. So in quantum you got stuff like a Bell state, and so a Bell state doesn't break down in the meaning of the parts and the way it's put together. In order to know, so the meaning of the parts have no meaning. So what I'm showing here is like I take the Bell state, I discard part of it, and what I get at the other side is noise. The parts are noise. and the structure of putting them together is the state itself. So it just doesn't work. It doesn't hold up. And you could say, quantum, that's also weird. But I mean, this community has to take this example very serious. I mean, here is a slide. So these are the companies who are now using categorical quantum mechanics, quantum companies. These are the people who have some quantum activity and are using categorical quantum mechanics in some way. You see, there's some seriously big players here, like NASA, Google, whatever. Most of all the optical quantum computing companies are pretty much here. So there's so much going. So this stuff is getting really big. So we have to take this seriously in our definitions. So another thing, which is just some advertising. So I'm also going to have a new book out with Stefano Goggioso. And this is for teenagers. This is for teenagers. So this is a quantum compositionality for teenagers. So the whole point is to make quantum much more inclusive, but at the same time, it's going to make string diagrams much more exposed to a broader audience. So since people don't, I mean, this is not like this, huh? This is not like the Dodo book. Huh? This is like this. This is like this, huge letters and stuff like that. And this stuff, this book has stuff that we didn't know at the time of the Dodo book. It has new signs in there which we didn't know at the time, which is really cool. Anyway, okay, so another thing we are doing, because kids don't read books anymore. Well, I mean, I never read books, but but we're filming the whole thing too. We just done. We have filmed the whole thing. Okay, so now I'm going to stick to this one. I'm going to go back to this one for the remainder of my talk. I'm just going to try to put down a few definitions of compositionality, which are wrong. They're inadequate, but they're completely different from Frege compositionality. So the question to the people here is, who are smarter than me, we really should think together of what is a good definition of compositionality, which encompasses Frege, which encompasses the stuff I'm going to put forward now. I mean, I know Amar has been thinking about that because Amar is working part-time for us, and I tell Amar, you need to think about compositionality. Okay, so I'm going to start from our notion of process theory in our Dodo book, and then try to sort of turn this into a notion of compositionality. So a process theory consists of systems, S represented by wires, processes P represented by boxes, with systems in S as inputs and outputs, composition of processes represented by wirings resulting in a process D. So this basically you interpret diagrams in some concrete theory. That's really what it is. That's really, you got wires, you got types, you got boxes, you got morphisms, and you compose stuff. That's really what it is. Of course, this is already very limited because I'm excluding higher order stuff already. But probably you need to go higher categorical here. That would be a first step to go higher categorical. I don't know. And now I'm going to put forward the definition, which I think is really important for us. I call this a Schrödinger compositional theory. So why Schrödinger? Schrödinger is the person in 1935 who emphasized, and for the first time, and nobody was really listening at that time, so everybody was listening to Einstein and von Neumann. Schrödinger emphasized that probably the most important thing about quantum mechanics is the fact what happens if you compose things, if you bring systems together. And categorical quantum mechanics is actually an incarnation of that idea, because we only use string diagrams, so we only use composition. So this is like you can do all of quantum mechanics just via composition. So it's very Schrödinger. Now I'm going to put some other conditions because this is completely trivial as a definition. Now what's going to come next, I know people are going to hate this because this is not maths. I say composition is non-trivial. It is the whole cannot be decomposed meaningfully. So I want to contrast with the Frege compositionality. I want to show that there is stuff which goes top down and in parallel, which you can't reduce to Cartesian structures. Say. So that's why so it's non-trivial. I mean, this is not a very nice characterization using the word not, but I couldn't come up with anything better, to be honest. And another thing which I think is important is all ingredients have clear and meaningful ontological counterparts in reality. So you can't just chop something down randomly with bits which have no meaning or no significance or whatever. That's called destruction. That's not called compositionality. So these are key ingredients. And I mean, we're working at a more subtle definition at the moment, but that's the best I can do. So, okay, this is Schrödinger compositionality. Here's a different definition. I call this Whitehead compositionality because Whitehead is the first person who was pushing process theories a long time ago. But he was basically just looking at linear processes, everything on a line. So the non-triviality definition just falls away even. So, I mean, this is just like for historical reasons that we give him a name, we give him a thing too. Here is a non-example. A non-example of Schrödinger compositional theory is our neural networks and machine learning, because we don't know what these bits are. We don't know what, we've got this bird here, we don't know what's sitting in each of these bits. They have no meaning. And that's, for example, the difference with what I was talking about before, where we understand what every box is and what it represents, these meanings. So that's the differentiation we want to make. We want to make, because people say, oh, a neural network is compositional. No, it's clearly compositional in a different way than what we are thinking about. So we have to differentiate these things. And now I'm going to go a step further in compositionality. So this is the paper we wrote. Our first paper we wrote is in 2007 about the X calculus. And I mean, this is a calculus which looks like some of the things we've seen today. But what's really special about that, and at the time when we did it, was completely not entirely anticipated. So this was a process, a lot of people were involved there. So Amar is here, Manuel Jandel is here, I think Arnie may be coming, I'm not sure. So, but basically what these people over a period of time proved is that your rewrite system is complete, that everything you can prove in Hilbert space, you can prove within your compositional theory. So that's a completely new level of compositionality, where everything is solely compositional and you do as much as you can do in your original theory. Of course, now there are more results like that. There's like, I mean, I'm just put on one paper here by Pavel, Filippo, and Fabio. Now there's like the same sort of stuff is being done for a lot of CS with the same kind of graphical calculi and all that. So it's becoming a very important discipline within the community. Here is another counterexample. So this is tensor networks, which is, for example, it's used a lot in physics too, in condensed matter, to actually make calculations possible in any way. But of course, they have nowhere near like a complete rewrite system, nor have neural networks for that way. So these are all different ways or strengths of compositionality, and somebody needs to catalog them. I'm probably not going to do that. So yeah, I think that's my summary. So why that compositionality was like the linear thing, why that came up with Schrödinger compositionality, I attribute to Schrödinger. That's where composition is non-trivial, and both of them are about ontological representations of reality. So they have all so the composition as a representation is connection with reality. And then the new level, which I think we should always aim for, is this complete compositionality, where a compositional structure does everything for you. You don't need anything anymore. You don't need an interpretation anymore. So with ZX, we don't need an interpretation in Hilbert space anymore. We do everything in ZX. For example, just to give an example, like ZX calculus is now driving quantum compiler optimization. Like quantum computers are small, very, very, very noisy. So if you want to do a quantum program on a quantum computer, you need to compress it as much as you can. And the state of the art is ZX calculus for such practical things. Error correction is important. ZX calculus is being used a lot by Google there. So this stuff, probably because of its complete properties, is very useful now. It's super useful. And they were laughing at us, like our first paper when we submitted this to a conference. They were mocking us. Literally, they were mocking us. Quantum computing conference. Now I'm laughing at all these guys. Anyway, that's kind of, so I said it was going to be, Lego compositionality. I know Amar likes this, but I'm not going to talk about this. Martha, how much time do I have?
You need to wind up now, so.
Okay, I'm not going to talk. So basically, yeah, I know. It's about relativism of compositionality, which is a completely different chapter again. It's complicated. Okay, so why not? Yeah.
Great. Thank you, Bob. Thanks. Applaud in person, online. So I guess we have time for one quick question, if there's someone in the room.
Yeah, James couldn't ask the question before, so.
So my question is about how you get the circuits from your previous talk. Sorry. How do you get the circuits from the wiring diagrams? So it seems like you're sort of using the compact closed structure to straighten out all the diagrams. Is that actually what's happening? Yeah, so
it's a bit more that's going on in these algorithms. You have to introduce new wires too, because a lot of these you have to turn vectors into endomorphic things. Mm-hmm. So you have to add something too, but you do this without actually changing the data you're dealing with. It's just a different representation of the same thing. So we're gonna bring the algorithm out in 2-3 weeks. Now, a beautiful thing which I didn't say there is, so in order to make a grammatically correct sentence, there's a lot of rules you have to follow. You've got a very complex type system, and then you have to do all these calculations with the circuits. However you plug them together, they're always meaningful. So that's a very important thing too. You don't need any complex type systems anymore. You just plug them together. I mean, they still have types. They still have types. Anything you plug together corresponds to some text. Not unique. Not unique. You can write it in many different ways, in many different languages. But yeah.
Okay, I'm going to move us on to the next talk, I'm afraid, just to, but obviously Bob will be around in the breaks and you can chat to him then. So the next talk is a demo of lambeq, I believe. Who's giving this talk? There's plenty of authors.
Yeah. I need to share my screen. You should be able to. Yes. This work? No.
Okay, great. Thank you very much, Ian. We can see the screen. So please go ahead go ahead whenever you're ready.
I mean, I'm ready, but the mic isn't.
Have to change battery.
Yeah.
Okay.
So you should put this in your
Yeah.
pocket and this is close up here. See if it works.
And Ian and whoever else is giving the talk, do you want me to give you a 5-minute warning?
Yeah, sure. Hello.
Okay, great. I will do. Thanks.
Right. Does that work? Can you hear me? Yeah. Okay.
Yeah.
Well, okay. So I might sit down for this because I need to type. I'm going to do a little software demonstration of lambeq. It won't be covering too much theory here. I'll let Bob do all the hard work with that. But so I'm just going to demonstrate how we actually use those concepts that he talked about to run some QNLP experiments using the library lambeq, which is a Python library that we're developing at Continuum. So lambeq provides all the tools to implement a QNLP pipeline that I've written here, that it takes in some sentence input and then first of all, it encodes them into diagrams, and then we perform a bit of rewriting of the diagrams before parameterizing them, and then we can train them in order to run the experiments. And it does all of that in a category theoretic, using a category theoretic approach. If we start with diagram encoding, lambeq supports multiple compositional models, which turn sentences into string diagrams. So if we start off nice and easy, we'll demonstrate the spiders reader, which uses a Frobenius spider to compose the words. So you just you can just import it, and then we say we want to turn the sentence into a diagram, and then we'll use this sentence, a simple one, just fat cats eat rats, and then we see that it composes it composes the words using a spider. Since the spider operation is commutative, this loses information about the ordering of the words. So we can call this a sort of bag of words model. Alternatively, we can also use a word sequence model, which composes the words from left to right, so that it preserves the ordering of the words. And so you can see that here. However, if we want to be even more sophisticated, we can consider the grammar of the sentence, which Bob has been talking about in his previous talks. So the way we do that is that lambeq supports a state-of-the-art parser called Bobcat, which automatically parses sentences according to its grammar and turns them into diagrams using the Disco-Cat model, which we've seen before. So if we show you what that looks like, There we go. So it joins according to grammar. So it joins the word cats with the adjective before joining it with the verb. And using that, it's pretty straightforward to just pass a whole corpus of sentences. So all we need to do is open the file, and then we just use a single method call, and then it will pass the entire corpus for us. So just do that. It's very simple to just turn all of your sentences into diagrams. And I can show you that Bobcat has no problem with handling really long sentences, such as this sentence, which has 30 words in it, and it can automatically figure out the grammar of that sentence and just turn it into a diagram for us. So once we have the diagram, in order to actually use them in an experiment, we need to turn it into a circuit that can run on quantum hardware. Using lambeq, we can do this using ansatz. I'll just demonstrate using the same sentences earlier. I'll just turn it back into a diagram for us. So in order to turn that into a circuit, we need to define the types. And we'll also import the ansatz that we will use in order to turn it into a circuit. So first we define the types. And then we just define the ansatz. We choose, in defining the ansatz, we choose how many qubits we want to represent each type with, as well as how many layers in the final diagram that we want the ansatz to use. So here we'll just use one. And then after that, we simply apply the ansatz to the diagram, which applies a functor to the diagram, turning it into a circuit. And I'll just show you what that looks like here. And there we go. So this can then run on a quantum hardware, except that we have displayed the parameters of these blocks symbolically. But later I'll show you how we use lambeq to automatically substitute some concrete parameters so that we can then evaluate the circuit using those values. But as well as running the quantum experiments using circuits, lambeq also provides tools for running classical experiments using tensor ansatz, which could be turns the diagram into a tensor network that can be evaluated classically. Here, each word becomes a tensor, and in order to define the ansatz, we have to specify the tensor dimension for each type. So in order to do that, we do it like this. So each noun becomes two-dimensional tensor, and each sentence becomes three-dimensional. And then once again, we just apply the ansatz to the diagram, which is again just a functor, like this. And this is, once we substitute concrete parameters for this, we can then evaluate it classically as a tensor network. However, before we can specify these concrete parameters, we might start running into a problem. I'll demonstrate this using another sentence that is cats eat rats on mats, and I'll just show you what that diagram looks like. We can see that in this, if we use the tensor ansatz above to turn this into a tensor network, the word on will become a 5-dimensional tensor, and the number of elements, values that we need to specify, the concrete value of this tensor will grow exponentially. As I just show here, there's your 5-dimensional tensor. In order to combat this, lambeq includes a rewriting module, which allows specifying rewrite rules on diagrams. This is done using the rewriter class. which allows us to specify the rules to apply on the diagram. These rules express a kind of prior assumption about certain word interactions with the idea that they simplify the representation of words and therefore reduces the resource usage when we're running our experiments. For example, we'll use the prepositional phrase rule, which is a standard rule that is just included in lambeq. And this turns the noun wires in the preposition on into a cap. Essentially allowing the wire that comes from cats to pass through to transparently to the word eat. This is applied again as a functor on the diagram. Pardon? Oh, hello.
So you did this one and rewrote it to the other one. How it decided that on was a binary thing.
Oh, because this ansatz was applied on this diagram, and it just turned each wire in the output of the word on here into the into a dimension of the tensor that the word gets turned into.
Okay, so I'm missing some information that lets me go from the binary.
Oh, so.
Well, why does it know that it can do that to on? That's my question.
That it can do what to on, sorry? Oh, the rewrite. So you mean, how does it know that it can rewrite the word on like this?
Yes.
Oh, I see. Because in linguistically, the word on has a specific kind of specific type here.
What does that mean? I think maybe go on.
Yeah, so it's because on is a preposition. So I think this needs to in order to then say, oh, why is on like how they decide that on has this type that can be rewritten. You kind of need to go into the kind of like how you do a linguistic parse of a sentence and decide what the types of each word is. Does that make sense? Sure. Okay. Well, we can I mean, you can talk about it afterwards if you need more information about it. Okay, yeah, I'm just demonstrating how we put all these ideas together to actually run an experiment. I understand I'm kind of skipping over some details, so I'm just kind of giving the sort of overview as to and to just kind of demonstrate that what we talk about we can actually do essentially. Sorry, so back to what I was saying. So you can see that here, if we simplify this diagram and then turn it into a tensor network or a circuit, now there are fewer wires, so the tensor will either have a smaller size, or you would need fewer qubits in order to represent the word, which helps reduce the resource usage that we need on quantum hardware in order to run our experiments. So, okay, I have some time left. So before I demonstrate the final step of training of the pipeline, which is training the actual circuits, lambeq also contains a command line interface, which can be used to perform the steps of the pipeline that I've shown you so far, in order to prepare a corpus of sentences into diagrams or circuits that we can use in training. And you simply call the program lambeq, and all you need to do is give it an input file such as some corpus that you have before you've prepared. You would specify what the ansatz is, and you specify how you want the output of the diagrams, so that then afterwards you can just import that file in order to use it in training. So something like this, and then it will just run and then save the diagrams it creates into this file. As well as doing that, it can also be used to view diagrams in the terminal. I'll just let it finish making these sentences. Yeah, the exclamation mark just because I'm running it within Jupyter. So instead of having to open a new terminal by prefixing your command with exclamation mark, Jupyter knows to send that line to the and run it in the terminal instead of as like Python code.
Okay, this is Python.
No, yeah, it's Python.
Okay.
Yeah. Okay. Right, so you can also use it to view the diagrams in terminal, just for fun, I suppose. So yeah, so I'll demonstrate the here you go. Here's a diagram. Right, I'll demonstrate the training now. We don't have enough time for me to actually do it, so I'll show you one that I ran earlier, which is for which should just only take a few, maybe like 2 minutes. And it's
Hi, Ian, just to give you a 3-minute warning.
Yeah, all right. So this runs a training for this demo. I'm just going to demonstrate what I did to train a very simple task. It's called a relative pronoun classification task. So all it does is that it predicts whether a noun phrase contains a subject-based clause, such as this one, or an object-based res clause, such as this one. This is a very toy example, and there's some more in-depth version available in our documentation that's online. So before we convert the diagrams into circuits, we remove the cups in the diagram in order to reduce the effect of post-selection when running the circuits, which we do here. And then afterwards, we will use the IQP ansatz to generate the circuits. We'll represent the noun wires with 1 qubit, and then we'll kind of just ignore the sentence wires that are generated. And then we'll turn all the diagrams into circuits. So an example of one of the training circuits is shown here. And afterwards, we create the model, which manages the parameters for optimization. It's called the NumPy model because it uses NumPy under the hood in order to represent everything. And then we'll train the parameters of the model. Well, first we define some ancillary functions, but then we define the quantum trainer, which takes in the model, some parameters for the actual training itself. And then we just run the training, and then we could demonstrate that it does a little bit of learning. This isn't the full task, so it's not very good, but it does learn a bit. Yeah, so that's everything. Just to conclude, if you want to use this for yourself to play around with it, it's really simple to install in Python just using pip. You can find more information about us on PyPy, where the Python library is hosted on GitHub, where we've got all our code is open sourced and our documentation. I just want to give my thanks to everyone who's helped work on this project.
Fantastic. Thank you very much, Ian. Do we have questions in the room? We've got time for 1 or 2 quick questions.
What's this?
Yeah, we have a couple of questions.
That's true.
Hi, Ian. So
hello.
How do you handle grammatically ambiguous sentences? Like, say, white scope versus narrow scope? Do you always pick, does Bobcat always pick one of the two?
Yes. So it does pick one that it thinks is kind of statistically more likely. However, because it also can generate multiple possible passes for each sentence, you could go in and sort of like say, and then it kind of ranks them, saying, oh, I think this is the most likely, but you can go in and say, oh, I want the other pass that you generated. However, you know, it would be kind of infeasible to do that automatically. For if you have a large corpus, it'll be hard to go in and sort of hand pick the correct path. So I guess you just have to kind of hope that it does the right thing, which I think it generally does do a pretty good job of.
Any more questions in the room?
Hi, I was wondering if you've done any benchmarks or comparisons to other NLP models.
What kind of things would you want to benchmark about it? We have run some experiments. Obviously, this, you know, it's still kind of difficult to scale this up to the kind of scales that we see with classical NLP models, simply because we don't have the resources to be able to do that with our current, I guess, technology. But we have been running. So it's really difficult to do a kind of like for like comparison, is what I'm saying. But we have yeah, exactly. So we're trying our best, but I probably still don't have, you know, a kind of satisfactory answer for you, perhaps.
Thank you.
Okay, I'm going to move us on to the next talk, please. So let's thank Ian again, and the rest of the lambeq team. So the next talk is vibrational linguistics, and who's presenting this one? Is it Fabrizio? I believe there's two presenters.
So you should, sorry.
Oh yes.
You should put this in your pocket and close if possible.
So please do go ahead whenever you're ready. Would you like a 5-minute warning?
Yeah, that would be great. Thank you.
Okay, sure thing.
Okay, so thank you. Today I'm going to talk to you about our attempt to describe linguistics with vibrations. And first, a little bit of introduction. So our attempt is totally unbiased in the sense that we do not assume any cognitive assumption on everything. So for us, a speaker will be just a functor from a semantics category to a language category. And is unbiased in the sense that our semantics category is a black box. So it is totally inaccessible, but the language category instead can be described. It can be anything ranging from a pre-group to CCG, anything you want, basically. But you may argue that this definition is quite useless because, you know, that's a black box. But how do you do that? How do you save this? Well, you define a vibration. I assume you're all familiar with the definition of vibration. Here we use discrete vibration. If you aren't, it's enough to think that thanks to the vibrations, you can build sets of objects of what's called a total category over every object of the base category, which is the bottom one. And the universal property of a vibration allows you to allows you to do this thing. So morphisms in the base category induce morphisms between the fiber sets in a contravariant manner. And you can see how an example of this is defined here. But surprisingly, there's a very deep connection between functors and vibrations, which is the factorization theorem. And it says that basically every functor can be factorized through a vibration, which means that in our situation, we now have a new category, EP, which is now compatible with the language category. And this allows us to intuitively consider concepts fibered over linguistic constituents, which can be thought of words, for example. So here's a toy example what we would do. Here are the beautiful pictures of my two cats, which I'm very proud of. On the left, you can see a concept of a sleeping cat. And what the vibration allows you to do is to split this concept into atomic concepts built over the words. So now meaning is somehow compatible with the structure of a language. So laid all the foundations here, and we're ready to see how these tools really apply to language acquisition. So a little bit of context. According to most of us, language is what defines us as human beings. Not only animals are totally incapable of producing articulated forms of language, but also Neanderthals did not have the classical right-angled vocal tract that first appeared in Homo sapiens, and it was that allowed sapiens to basically conquer the world. So it's really what defines us as human beings, but no one is born fluent. So every one of us has to learn language somehow. And how do you justify this? How do you explain this gap? Well, you need a little bit of philosophy here. I won't be too specific about this. I will just focus on the two most influential positions of the last century, Chomsky and Wittgenstein. And here the timeline is actually peculiar because Chomsky, as Wittgenstein, died in 1951, so 6 years before Syntactic Structures, which is the most influential work by Chomsky. But the majority of critics to Chomsky comes from Wittgenstein's writing. Essentially, the idea is that Chomsky was a mentalist. So he believed that language acquisition happens in the mind only. So thanks to this language acquisition device, which is entirely contained in the brain. So he did not assume any interaction with the environment. While on the other hand, Wittgenstein was what is called a behaviorist. So he believed that meaning is defined by its use, and meaning is discovered through what he called language games. Now, the definition of language games is a little bit vague, but you can imagine those as concrete examples of communications. So they concrete social activities that involve language in a crucial way somehow. Of course, our job is not to establish here is right or wrong. We are not linguists, but what we can notice is that language games by Wittgenstein are incredibly similar to our Fibrational approach. So let's play a language game. This is actually the very first that appears in a philosophical investigation by Wittgenstein. And the context is very simple. You have a builder and an assistant, and the builder is asking the assistant to pass him some types of stones. But the assistant is still learning, so he does not really know all the stones. So when the builder calls for his lab, the assistant does not understand anything at all, and he handles a beam. But now, after some training, after some attempts, the assistant understands the correction and handles the correct stone. So this can be modeled through vibrations, surprisingly. And it's nothing else but an example of vocabulary acquisition by example. So it's a method of learning language by pointing to an object. The builder is teaching the assistant the meaning of slab by pointing to a specific example of slab, to a concrete object. And let's see how we can use vibrations here. So we have two speakers. Actually, we don't have the speakers here. We have the corresponding vibrations obtained thanks to the factorization theorem. So we have P sharp and Q sharp. And suppose that for some linguistic constituent, which in this case can be the word slab, the teacher, which in this case is the builder, knows the meaning of a slab. So that means that the fiber over the word is not empty. You can see on the left, he has two different ideas of slab. And you can imagine that the bottom one is the one he's pointing at. On the other hand, the learner does not know anything at all about a slab, and his fiber is empty. But now our goal is to teach the learner, so we have to enlarge his category of semantics by, in a most natural way, by leaving the morphisms unaltered and just adding to the objects of the previous category this new object, this new image of slab, which is the bottom one, the one the builder is pointing at. Of course, we have to define the new speaker in such a way that it agrees with everything that Q already knew. So it basically will send every fiber different from the one over slab to the same one Q did, and the new to S. But now we say we're not done, because who guarantees that this function, this speaker, is a vibration? Well, the factorization theorem, intuitively, we need new concepts, new acquired meaning to be compatible with the previous. One may say that a speaker actually efficiently learns a new word when this blends well with all the other concepts. And the way we do it is constructing a vibration thanks to this. But it's not all, because vocabulary acquisition does not happen only by pointing to objects. You may say this is the most common method when you're a child, basically. But once you're an adult, it may be more common to understand new concepts by paraphrasing. So by literally finding new similar words or synonyms to say the same thing. And for that, I will leave you to Fabrizio, who will explain to you.
Hello, can you hear me? Yeah, I guess so. Thank you, Caterina. Yeah, I'm covering this second part, that is vocabulary acquisition by paraphrases. Basically, that is when you teach people like what the thing is by just describing the thing. So it's like dictionary definition of something. So let's see a simple example. We have Alice who says, oh, I adopted a cat. And Bob says, a what? Because Bob doesn't know what a cat is. And Alice says, oh, you know, a cat, one of those felines. And Bob's like, oh, you mean like a tiger? No, a cat is smaller and it comes in various colors. Mine is black. Oh, maybe I see the cat is like a lynx. Well, almost black cats are cursed. Okay, now I see. So after this dialogue, Bob has never seen a cat. He would probably not be really able to recognize a cat or to draw a realistic cat, but you know, he has a very vague idea of what a cat can be. So we want to model this. To model this, the first thing we have to do is to say what an explanation is, because that's what we're doing. Alice is explaining stuff to Bob. So what is an explanation in our setting? The first thing I have to tell you is that there is a very nice theorem that basically tells you that every time you have a discrete vibration, so as Caterina said, the functor from some category to L with some particular property, you can turn this around into a functor from L to Z. You can do this via a thing called the gradient deconstruction, that is that integral there that allows you to go in that direction, and then you can go the other way around as well. This is probably making things even more familiar with people used to DiscoCat, because in DiscoCat, traditionally, you have grammar going into the semantics. In here, we are doing the opposite. Like in vibrational linguistics, you have the semantic category that is mapped into the language, into the grammar. So with this thing, you can see that you can pretty much turn one into the other. And now what is an explanation? Well, we have a speaker, P. This is the vibration corresponding to the speaker with its category of concepts, bless you, and a language category here. And basically, now we want to explain a word. So we have a, let's say, L, that is an object of this linguistic category, and we want to give an explanation of L according to P. So what is this? It's a finite diagram. So basically just a functor from a category that has finite objects and morphisms into L, such that this limit, that is this functor composed with the vibration mapped through this nav line to a functor to set, is such that this limit is a subset of the fiber over L according to P. So what does it mean? It means that you have a finite diagram, so in this case, something like this. You are mapping it into your linguistic category. So in this case, you are picking up evil black feline. Then you are using this kind of inverted vibration, and you are mapping this to set. Every one of these concepts is basically being mapped into the fiber corresponding to it in the vibration. And now I'm in set, so I can do the limit. And I'm basically saying this limit must fall in the fiber over the word that I'm trying to explain. So it's like gluing all these concepts together must give me something that for me is a concept of the thing I want to explain. Okay, cool. You see very interestingly, and this is connected also with the stuff that Bob was talking about, you can give explanations in this way that are not grammatical. Like I can say, I hungry now, and I can still compute this thing. So I can actually speak in an ungrammatical way. I can decide to ignore grammar in a way. Okay, so what is that we can do? We have two speakers, P and Q. As before, P knows what L means. Q has no meaning for L. P as an explanation of L, that is this functor. Now, this explanation, this DL is an explanation for P, but in general not for Q, because if you compute this limit, the limit may be a non-empty set and the fiber is empty. But what can happen now is that P can actually give this explanation DL to Q. How does it do it? Well, by just altering the sentence. That is basically in these settings, altering a sentence is sharing this functor. And now Q can calculate the same limit of this functor using its own fibration here, and it can decide to include this limit in the fiber. But this is somehow unsatisfying because when you do the limit, you see, you have a limiting cone here. So you also have these legs. And if you just include the object, L hat, the tip of the limiting cone, you are missing information. On the other hand, it may be very difficult to include the whole cone because then you may not be able to define this functor. So for example, if your L is a pre-group, the only notion of morphism you have is grammatical reductions. So if you want to include the whole cone, you are actually including morphisms from nouns to nouns, and you have nothing in the language that allows you to map these morphisms to. Because in the language category, you can only do grammatical reductions and you can't reduce nouns to nouns. But we can solve this in a nice way by extending the language. So what we do is we define a quiver, or if you prefer a graph, by taking the vertices of Q to be the same of the language category, and by basically adding only as edges the corresponding limiting cone legs. So basically we say, okay, we had an edge like this, only if this gets mapped to the limit and this gets mapped to one of the feet of the cone. Now that we have this quiver Q, we want somehow to glue this to the category L. So how do we do that? Where that's quite nice. There is a junction between quivers and categories. We start with the language category seen as a quiver, as a graph. We have the quiver we just defined. They share the same object, so we have these injections. Then we calculate the push out here. Then we apply the free functor, and then we use the Q unit here, and we have this new thing where we basically just glued these cone legs to our language category. And now with this thing, we can actually define this functor from this new category to set by mapping the word L to this limit, that is the thing that Q wants to add, every other L prime to whatever we were mapping it to before, and on morphisms, T agrees with the fibration of Q and maps the new edges to the legs of the limiting cone. Then we apply the greater deconstruction, and by definition, we obtain a fibration that is the updated model of Q, of the learner Q. I think, and by the way, I'm done, but I think that the nice thing is that this shows a connection again with what Bob was talking about before. That is, there is a real interplay here between grammar and semantics. Like in learning this word, Q added new morphisms to the language that have a semantic origin. It's like even if L is a pre-group, so you only have grammatical reductions, now you have grammatical reductions plus the possibility of replacing cat with feline, for instance, in your sentences. So this means that to learn stuff, you have to also enrich the grammatical model of your language in this framework. And then this interplay becomes really clear. And I really like that, you know, independently, we basically came to similar conclusions to the ones that Bob was drawing before. So somehow everyone is converging to the same thing. And that's it. Thank you.
Great, thank you very much, Fabrizio and Caterina. Do we have questions in the room? We have plenty of time for discussion before lunch, so.
Or we can have more lunch.
Yeah, true. It's up to you as audience.
Well, thank you for the talk. It's very interesting, this category clarification of vocabulary acquisition. My question is about this vibration and cognitive construction. How do you envision that this will impact the practical implementation and learning problems regarding natural language processing?
Oh, we don't. We are literally like, when we did that, natural language processing was the least of our concerns. Basically, personally, for me, the motivation of this work was that every time I, worked in NLP models, you can have cognition models, distributional models, but one kind of constant thing is that every model you come up with, you can concoct a counterexample or a corner case of some sort in 5 seconds. So there was this ever frustrating kind of thing that there were a lot of assumptions, and that can be basically just criticized at will. It's a very slippery kind of field. It's very difficult to say, okay, this is unambiguously like this. And so that's why we basically, did this work with this idea of creating a more like solid conceptual foundation to linguistics that is not necessarily concerned with practical example. And this is basically what Caterina was talking about before. Like, we make no assumptions whatsoever on this category D here. And there is this magical theorem that says, okay, actually, even if this thing is a black box, you can get this other thing here that you can somehow describe and you can do stuff with. And by the way, this also gives us a very nice insight, again, connected with what Bob was saying before, that is, if you have morphisms in the grammar, these morphisms include functions between the fibers in the opposite direction. Now, from this, we basically came to the conclusion that for us, grammar is algebraic, meaning that you can take single constituents and merge them into sentences, for instance, but meaning is co-algebraic. Meaning is going in the other way around. Like, you are basically, there's this example. Think about a cat. Everyone thinks about a cat. Think about to swim. Very difficult. Like, what do you mean? The trick is realizing that when someone says, think about a cat, you are never thinking about a cat. You are thinking about sentences that involve cats. And then you are kind of decomposing the cat component from that sentence. And as soon as you realize that, you can do it also with swimming with every language constituent. And so again, this theorem that, it's a very old theorem, just illuminated the thing for us that probably, meaning should be co-algebraic. It should be about decomposing sentences and not composing sentences for smaller parts. So yeah, and all these is totally unapplied at the moment, but I think it gives a very nice conceptual insight of how to approach linguistics, basically.
A very quick follow-up clarification question.
Sure.
So this is for establishing the form of the vibrations, but do you have an insight into what exactly are the decompositions? What exactly you're targeting?
Well, that would depend on the structure of your linguistic category. So for instance, if L is a pre-group, you would have, for instance, if you think about the sentence, the cat sleeps, you will have the cat tensor sleeps and a morphism to the cat sleeps, the finite sentence somehow. And now the vibration is going in the opposite direction. So it's taking a meaning of the sentence, the cat sleeps, and is mapping it into a couple of a concept corresponding to the cat and a concept corresponding to sleeping. So the decomposition really depends on your grammar model, basically.
Thank you.
Okay.
Okay, so unless there are any urgent questions.
There's just one question.
Is there? Okay, great.
Sorry.
Go for it.
Thanks, very interesting work. Are you able to deal with the same word having multiple meanings in different contexts? Like if I now learn about slabs on a building site, about cats as felines, and I'll go to a maths class, then both of these words actually mean
absolutely.
Something.
They will both be in the same fiber. And now the point is, if you consider the cat sleeps, there will be all the meanings of this sentence that will, I think, involve only cats. I don't know, maybe there's a concept of sleeping category. But in any case,
This is a function. So the point is that every meaning of the sentence will be uniquely mapped to a decomposition. So I can have both categories and cats in here. The cat sleeps will hopefully only, meanings of the cat sleeps will only hit cats and not categories. So yeah, I think we can. But by the way, this is the easiest notion of fibration we could use. Then you can make it arbitrarily complicated. But for that, please ask Fosco, that is conveniently not here, about, you know, all the intricacies of the mathematics of this work. You're welcome.
Okay, any more questions in the room?
One, yeah.
Yeah, go ahead.
Yeah, so I was just wondering, your example of like giving this paraphrasis of like, you kind of assume that like this is a limit, right? Like of some diagram. But I can think of like words you might explain that feel more like a co-limit, right? Like you could say like, what's an animal, right? You could say, oh, it's it could be a cat, it could be a black cat, it could be, right? Like, and that feels more co-limit like. So is there like, can you also add sort of co-limits?
I'll be totally honest. We had the same question and we just flipped the coin. Actually, when you look at explanations, you have this thing, but you know, in my opinion, in a more like applied work, that thing shouldn't be a limit or a co-limit. That should be some kind of like machine learning thing that allows you to merge concepts. You know, like you have these machine learning algorithms that allow you to extrapolate things from a context or to merge things in a context and whatever. So in here, I mean, we took the limit because it was the most categorically convenient thing we could pick, but you can, you know, put something else that is probably more meaningful. I think it was also easier for, you know, applied category theory audience to define that thing with category theoretical concepts. But yeah, if you ask me, that shouldn't be a limit at all. That could be some more complicated thing for sure.
Thank you.
You're welcome.
In response to that, so this functor, that the embedding that comes from the factorization theorem, isn't that final or co-final functor, one of those?
Yeah, S is initial.
It doesn't introduce any new co-limits?
S is initial and Q is a fibration, if I recall correctly, I think. Or maybe S could be final. I really don't know. Basically, as soon as I knew that I could factorize that thing in that way, I completely forgot about the first part and just started reasoning about the second one.
Yes, it's interesting because I mean,
yeah,
we're doing pre-sheaves, and pre-sheaves are the free co-limit completion. So this factorization tells you that you aren't adding any co-limits.
Could be.
Which I think then this thing that you want an explanation should have to do with co-limits, because then we can interpret your pre-sheaf as the space of all possible explanations for a given sentence.
That makes sense. I have to check the mathematics also because I think that this theorem was given using op fibration, and then we flipped something and checked that it worked anyway. So now I don't remember if S is initial or final or something. We have to check the maths, but yeah, it should preserve something. And yeah, probably you're right, but we have to check the details.
Okay, hi everyone. I'm going to bring it to a close for now because we've gone into lunchtime. But of course, I guess Fabrizio, you're going to be around for the rest of the conference. So do chat in the breaks.
Cool.
Thank you. Let's thank our speakers again. Thank you.
Here,
Okay, hi. So quick recap for who didn't hear me. Apologies. I was saying that we have live note taking. We're experimenting with this conference. If you go at this address, you can access a live streaming together with lecture notes. Otherwise, you can just get the notes. Now, you're going to have to register and log in. This is done so people do not spam here. But you have something like a collaborative wiki here. Just type later and basic markup stuff. So if you like following from your laptop and like typing notes, or if you're typing notes on your own, you might try to do this collaboratively. And it's going to remain as a record for the conference. So we think it's a nice thing to have. And of course, you're not forced to, but it would be nice if you like to do this kind of things. Anyway, back to the conference. Oh, okay, have the floor.
So let's go.
Thank you.
Okay, welcome everyone for this afternoon session. The first talk is going to be given by Amar Aziz. You know, I practiced 4 years for that when I'm a PhD student. And Diana Kessler, both from Tallinn University, and Amar is also with us at Continuum part-time. And they're going to talk about data structures for topologically sound higher dimensional diagram rewriting. Floor is yours.
Okay, thank you. So good afternoon. Can you hear me? Okay. So So what I'm going to present today is joint work with Amar Hadzi-Hasanovic and also part of my PhD project. So in this talk, we'll present a computational implementation of diagrammatic sets, which are a model of higher dimensional diagram rewriting. And what I want to mention now is that we work in a line where higher dimensional diagram rewriting is coming from the theory of polygraphs. So we are interested in this because of its applications, amongst which we have the formalization of higher category theory, higher algebra, homotopy theory, or combinatorial topology. And now our model is based on an interpretation of a rewrite system as a directed cell complex. And unlike polygraphs, it has the advantage of being topologically sound. So what this means is that we can translate a directed cell complex into a topological cell complex. So we'll lose the idea of directedness. But we are also interested in diagram rewriting as a model of computation. And what I mean by this is that we want to understand diagram rewriting as an underlying mechanism of a model of computation in which the n+1 dimensional rewrites represent computations on n-dimensional data. So for this reason, we are interested in studying the algorithms and the computational complexity of the operations used to build diagrams and rewrites of diagrams, as well as showing that these algorithms, these operations admit algorithms of low degree polynomial time complexity. Okay, so the plan of this talk is that I will start by presenting the basic data structures and algorithms used to implement our shapes of diagrams and their maps. And an important result here is our traversal algorithm that solves the isomorphism problem between shapes of diagrams. Then I will introduce you the type theory for diagrammatic sets, which is built on top of this implementation that I mentioned earlier. And through this type theory, we then implement diagrammatic sets and diagrams. And I will we'll end the presentation with a demo of our tool, Revald, which will be given by my co-author, Amar. Okay, so let's start. Okay, so in the theory of diagrammatic sets, we encode the shape of a diagram with its face poset. So on this slide, we have an example of a two-dimensional string diagram together with its face poset, which is represented as a Hasse diagram. So our two-dimensional string diagram has the two-dimensional elements are represented as points, the one-dimensional elements are represented as lines, and the zero-dimensional ones are the surfaces. And also, please note that we didn't label the surfaces, the zero-dimensional elements in the string diagram. And now on the Hasse diagram representation, so each level corresponds to a dimension where the top level corresponds to the highest dimensional and it highest dimension, and it holds the elements with this highest dimension. So for example, in this case, it holds the two-dimensional element, and the bottom level corresponds to the zero-dimensional elements. So now what this phase poset does, so it tells us whether an n-dimensional element is in the boundary of an n plus one-dimensional element. And it also comes together with an orientation that says if this n-dimensional element is in the input boundary, this is represented with a pink arrow, or the output boundary represented with a blue arrow of an n-dimensional element. Okay, so we call this data structure an oriented graded poset, and we represent it with a Hasse diagram with labeled edges. So formally, a graded poset gives us the idea of a unique dimension for every element, which is the height of the element in the Hasse diagram. So this is the number of steps it takes to reach the bottom of the diagram, and this is well defined. Then an orientation on a finite poset P is an edge labeling of its Hasse diagram with values in plus or minus. In this example, minus corresponds to the pink arrows and the plus corresponds to the blue ones. And then an oriented graded poset is a finite graded poset with an orientation. Oh, and I also want to say that the pictures on this slide are produced by our tool. Okay, so we mostly work with downward closed subsets of an oriented graded poset, and this identifies subdiagrams. So a closed subset U, so a subset U of an oriented graded poset is closed if for any element in the subset, everything that's below that element is also in U. With this data, we can then give a combinatorial definition for the input and output n-dimensional boundary of a closed subset for any n. So for any n that is lower than the dimension of our subset. And this is denoted with this partial n alpha. And then we obtain a nice category whose objects are oriented graded posets and whose morphisms are maps of oriented graded posets that preserve the boundary. And again, this is for all, they preserve all the boundaries and both the input and output boundaries. Okay, we also say that a closed subset is round if for all k less than n, the intersection of the input and output k dimension equals the k-dimensional boundary equals the boundary at dimension k minus 1. Okay, now we have this category of oriented graded posets, but we don't work with all oriented graded posets. We just work with a nice, well-behaved subclass of them. And we call these well-formed shapes of diagrams, we call them regular molecules, and they are inductively defined by the following clauses. So the first one is point, which says that the oriented graded poset with one element is a regular molecule. This is also the terminal oriented graded poset. The second one is atom. So this rule lets us go one dimension higher, and it works in the following way. So given two regular molecules, U and V, if they are round, they have the same dimension, let's say n in this case, then if they're both input and output boundaries are isomorphic, then we glue them. So we glue them along these boundaries and we add an n plus one dimensional element. And this new structure is also a regular molecule whose input boundary is U and whose output boundary is V. Also note that this arrow going from U to V is just a convention that goes from U to V. Okay, and finally we have the paste rule, which takes an extra argument K, and it lets us glue regular molecules along their k-dimensional boundaries. This works in the following way. So we have U and V regular molecules, then if the output k-dimensional boundary of U is isomorphic to the input k-dimensional boundary of V, we glue them along this boundary and obtain another new regular molecule. Okay, so given this definition, we now want to implement the class of regular molecules using the following constructors. So we have the nullary constructor point and the partial binary constructors atom and paste k. And for this, we need to be able to compute the input and output k boundaries to check if a closed subset is round, to determine if two regular molecules are isomorphic, and to compute the push out of a span of inclusions. Now, the steps 1, 2, and 4, they admit algorithms of low degree polynomial time complexity. So this 1, 2, and 4 here, but the third problem, however, is not trivial. And the third problem, so the isomorphism problem extended to all oriented graded posets is equivalent to the graph isomorphism problem, whose best running time is quasi-polynomial due to Babai and is not known to be in P. But for regular molecules, we provide a polynomial time solution algorithm to their isomorphism problem, and we achieve this with our deterministic traversal algorithm that works in the following way. So given a regular molecule as an input, it outputs a unique ordering of the elements of this regular molecule. Now, you might have noticed in the example slide that we named the elements of a regular molecule or of an oriented graded posets. So we do encode these elements according to their dimension and also according to their position. So if we, in every dimension, if we order the elements according to the traversal order given by these algorithms, then we obtain a canonical form for regular molecule. And having this, then we can say that two regular molecules are isomorphic is if and only if their canonical forms are equal. Now, this is one of the main theorems of our paper, that the traversal algorithm admits an implementation running in time O and cubed log n, where n here is the number of nodes and edges in the Hasse diagram representation. In reality, this algorithm is better. So in our paper, a factor of n log n does not depend on the total number of nodes and edges in the Hasse diagram, but just on the number of nodes and edges in the dimension with the highest number of elements. Okay, so now we obtained an implementation for regular molecules and their maps, and I will continue by introducing you to diagrammatic sets and presenting you the type theory on which they are built. So we let this circle, which is called atom, be a skeleton of the full subcategory of oriented graded posets on the atoms of every dimension. So an atom here is a regular molecule with one greatest element. So this is a category of shapes. And then we get that a diagrammatic set is a presheaf on atom, and diagrammatic sets and their morphisms of presheafs form a category called atom set. Okay, now we can Yoneda embed the atom category into the category of diagrammatic sets. And we can then identify atoms and regular molecules with diagrammatic sets, and also give the definition of a diagram. So we let X be a diagrammatic set and U a regular molecule. Then a diagram of shape U in X is a morphism from the Yoneda embedded regular molecule U to X. Okay, now a diagrammatic complex is a pair formed of a diagrammatic set X and a set of generating cells curly X. And in short, it is just a cell complex in the category of diagrammatic sets. So it is, so now we can, now every cell of shape U in a diagrammatic complex is uniquely determined by a surjective map of atoms and a generating cell. And also if this map of atoms is the identity, then we get that our cell is a generating cell. So, okay, now I mentioned topological soundness at the beginning. And we have a full geometric realization functor from the category of diagrammatic sets to the category of spaces, such that if this pair of X and curly X is a diagrammatic complex, then the realization of X is a CW complex with generating cells, and every diagram of shape U becomes a cellular homotopy from U to X. Okay, I will now continue by introducing you the dependent type theory, which is built on top of a black box implementation of regular molecules and their maps. And I will present this type theory together with its semantic interpretation, which will be in blue. So we start with an infinite set of variables which correspond to the names of the generators. Then a term T is just a pair of a regular molecule U, which is the shape of T and the map from U to V, and this corresponds to diagrams. Types are either the empty set or of this form from T to S, where T and S are both terms, and they represent the input and output boundaries of a diagram. Now, if our diagram is a point, then its type is empty, for example. Then contexts are lists of typed variables, and they correspond to diagrammatic complexes. And a substitution is a list of assignments of terms to variables, and they represent maps between diagrammatic complexes. We now have three judgments. So the first one means that gamma is a well-formed context. The second one means that T is a well-formed term in context gamma, and the third that sigma is a well-formed substitution from delta to gamma. Okay, now our type theory comes together with some rules for context, terms, and substitutions, and we can then construct this syntactic category that has well-formed contexts as objects and well-formed substitutions as morphisms from the delta to gamma. We'll also define the semantic category, which is the full subcategory of the category of diagrammatic sets, and whose objects are the finite support-based diagrammatic complexes. Here, finite means that our generating set is finite, and support-based is just a technical detail that we use to encode diagrams in a simpler way. Okay, and then we get that the second main theorem of our paper is that the syntactic category is contravariantly equivalent to the category of finite support-based diagrammatic complexes. Okay. Now, as future work, we plan to study the problem of searching for a diagram within another diagram and come up with this algorithm called diagrammatic search. And this will be an important step towards achieving fully automated or assisted diagram rewriting. And then we also plan to study diagrammatic machines. So these are machines that run on a diagrammatic model of computation together with their cost model. Okay, thank you for listening. And now I will hand you over to Amar for a demo of Revalt.
Can you hear me when I speak like this? Okay, I'm gonna have to share my screen. Share here. Yes. Okay, do you see my screen? Okay, perfect.
Can you see?
Yeah, in the second part of the talk, I'm just going to give you a brief demo of the tool that we've developed, which is it's an implementation of, well, everything that Diana has been talking about and a bit more. And well, it's meant to be a kind of so this is it's a Python library, so it implements these kind of structures. And what we kind of try to convey is that, well, there's plenty of kind of applications for these kind of data structures. You have the kind of application of diagram rewriting as it's done here, and apply category theory for you know, for presenting algebraic theories diagrammatically. But there also is kind of like, thanks to this kind of topological soundness, the idea is that this can also be used to do something like combinatorial topology. So our this model of diagrammatic sets, well, kind of very briefly, it's a kind of vast generalization of things like simplicial sets or cubical sets with a much wider variety of shapes of diagrams, which means that at the same time, this model restricts to simplicial sets and cubical sets. So if somebody wants to use this to just work with simplicial or cubical things, they can also do that. So to give you just some coordinates, well, the documentation of this, well, there are some links here. Documentation is stored on this website on revolve.readthedocs.io. It contains several of these worked examples, which I try to make cover many kind of different, many of these kind of different potential applications. The source code is on GitHub if you're interested in contributing or building your own extensions on top of it. And it can be, so yeah, we've just done this pre-release just for the occasion of ACT, so it's not quite feature complete. You can expect that you'll run into bugs that we haven't discovered, but please play with it and tell us what we can do. So I'm going to just show you briefly a couple of kind of potential usages. So the main submodule here is the part that kind of implements diagrammatic sets and diagrams, and these can be used for example, to do kind of presentations of kind of algebraic or monoidal theories. And if you're familiar with the MotoP.io, the workflow for this kind of use case is very similar to what you would do in a MotoP.io, but well, it's command line, so you may like that or not. So I'm going to give you an example where we can do a presentation for example, for something. I'm just going to call it X, but something like a theory of monoids, something that's familiar to many people. So what we do is that first we create. Sorry, I have to import the library, of course. And first we're going to create an object type the set, which corresponds to an empty diagrammatic complex, if you want. And then, well, the paradigm here is that everything is a diagram. So both the kind of both our sorts and our operations and our rewrites, they're just diagrams in different dimensions. So to have something like a monoidal category, like a presentation of monoidal category or an operad, the idea is that this will be presented a bit like, you know how monoidal category is a bicategory with a single object? Well, if you know that, but that's the idea. So first of all, we have to add a single zero cell, and this command will add a zero-dimensional generator. We'll give it the name string X, and then assign the kind of the diagram that just picks that object to the variable X. And I didn't mention this, we also can visualize all these diagrams as well, in a bunch of ways, but the main one is going to be something like string diagrams. In this case, it's not super interesting because the string diagrams are just a single point. But now we're going to add a one-dimensional generator, call it A, and that's going to correspond to a sort of our theory. So okay, so now we've got a diagram which is slightly more interesting. It's got it says that this is a kind of one-dimensional thing, like you can think of it as a morphism or an edge going from X to X. And now that we have one-dimensional things, we can do some things with them. The main thing is that we can paste together diagrams. In this case, we can only paste them in a single way. So, oops, this would have to be A, not X. So that's the only thing we can do. So let's instead add some two-dimensional things which correspond to operations. So I'm going to add something called M, which will correspond to something like a multiplication. So this should be an operation which takes 2 inputs and returns 1 output. So in this command, I'm going to add M and say that its input has to be A paste A, which is like this pair of A's, and its output is going to be A. And now this should look a little more like the string diagrams that you're familiar with. And so by default, the string diagrams here go from bottom to top. So I would like a show of hands, like who here prefers the orientation of string diagrams from bottom to top? Please raise your hand. And who here prefers left to right? I think there's a majority for left to right. Who prefers top to bottom? Oh, there's
It depends for what you use. The language goes down in English, physics.
Yeah, for this demo we have to kind of choose one. Let's do left to right. I feel there was a slight majority for left to right, so I'm going to change the default. Okay, so now we've got string diagrams of the left to right. So now with these things, we can paste them in different ways. We can paste them horizontally, which will be, I'm telling them to paste M with another copy of M along the 0-dimensional boundary, which means that this is horizontal. So you got something like this. If I try to paste M and M vertically, of course, I'm going to get an error because we can't do that. So of course, this thing is doing, like in the background, it's doing kind of checks that everything is well typed. But there's another way of pasting these things, which may be useful for these kind of things. So we can give to our drawing an argument saying, please show me. So every element of the string diagram has a position, as we showed. So this is saying that M is the top dimensional element, position 0, and then we have these 1-dimensional elements in position 0, 1 to 2. So another thing that we may want to say is, okay, I want to plug an M into the 0th input of these diagrams, and I can do this with this method, 2 inputs. So I'm going to say M, 2 inputs 0, M, and I'm going to draw this, and let's see the positions again. Okay, so this is another way of pasting together things. We can also paste along multiple inputs or outputs. So I'm going to just I'm going to add another generator C, which now is going to have 1 input and 2 outputs. And we can customize things. We can say that, oh, I want this one to be drawn in white and with a black boundary. So we're going to get this. And now let's say we want to plug this kind of co-multiplication thing into 1 and 2 in this diagram, and we can do that by copying diagram and then saying that to inputs 1 and 2, for example, we want to add C. Okay, so this is how you can build diagrams. So, well, another thing that, well, at least for me, it's been useful is that all the string diagrams that this generates can also be, well, first of all, they can be customized in other ways. We can, we can change colors and things like that. Let's do it in dark blue with white wires or something like that. So we can do this, and but more importantly, everything can be outputted as TIX code. So let's do this with the option TIX equals true, and we're going to save it to the paths TIX example.tab. Okay, and now, well, I've prepared a kind of a file which imports this TIX example, so I'm going to compile it. And then you can see that this has produced pretty small here. Let's do it. Like this. And let's give it a little. Boundary, so you can see better. Okay, this is more like it. Okay, so this is another thing that you can do with this. And then I said that we can do some rewriting here. So let's add some equations to our theory. So for example, an associativity equation. So as I said, everything is diagrams, so these will also be kind of oriented equations corresponding to three-dimensional generators. And I'm going to say that I want to add something called a sock, going from, so going to be from M with another M plug-in input 0 to M with another M plug-in input 1. I'm going to use this draw boundaries. So this is now drawn the two sides of this generator that I've just added. And you can see that they correspond to an associativity equation. And now, for example, let's form some kind of bigger diagram by just adding M's. And I'm going to show the positions of all nodes in this diagram. So, okay, so I've just plugged an M into the input 0 and then plugged another M to input 0. So now say we've got this kind of diagram and we want to apply this rewrite rule. We can do it. So I'm going to call this rewrite 1. And I'm going to ask that I can rewrite the nodes in positions 0, 1, for example, by applying the rule a sock. So now when we draw this, you'll see that the rewrite itself is a three-dimensional diagram, which means that what the string diagram will show is this kind of slice of a three-dimensional thing, which tells you what two-dimensional things come in and what two-dimensional things come out. So in this case, we've got two of these M's coming in and two M's coming out and one M being left alone. So instead, if you want to see the result of this, that will have to be output of this diagram. Okay, so this is where we are. So now we can apply another associativity rule to 0, 2. I'm going to call this rev2. So this is applied to the output of rev1. So I'm applying to 0, 2, the diagram as sock, and let's see what the result is. So you see we've gotten this thing was on the left and now it's on the right, and we can do another one. Now we can apply another associativity to 1 and 2, and that's going to be applied to the outputs of rev2. And let's see. Okay, so we got this diagram, and now we can't apply any more of these associativity rewrites. But something nice we can do, so let's put all these rewrites together. I'm going to use something called diagram with layers, rev1, rev2, rev3. Okay, so that's going to put together all the rewrites we've done. And now we can we can create a little GIF animation of the sequence of rewrites which we've done. So there's going to be rewrites, all the rewrite steps. And we're going to save this to rewrite.if, and we're going to make it loop around. Yeah, that should be right, I think. Okay, this it's not going to show it immediately, so instead I have to do this in Markdown language. Let's hope this works. Okay, yeah, we've got the so they go forward and backward. I'm astounded that I still haven't run into bugs during the demo. So anyway, this is I'm going to finish very heavily. So this is one of the use cases. Well, another thing that is included is this kind of, I mean, underlying all these, there's this kind of submodule that handles shapes, and so again, the kind of main kind of ways that shapes are built is through the constructors that Diana talked about. So we can create the shape of a single point, we can create these kind of atom things, and we can paste together shapes. But there are other ways of creating shapes. For example, there's for some of the kind of named shapes of high category theory, there's kind of special constructions. So we can do things like cubes. We can do things like simplices, for example, tetrahedron. So we can do simplices on any dimension, and well, there's other kind of construction for other. There's kind of special things for optopes, for things like that. So you know, if you really like simplicial sets, you can also work with that. There's in fact, one of the notebooks is exactly about exploring kind of simplices and cubes with this, and there's kind of special methods here for constructing a simplicial set, which is just a diagrammatic set in which we keep only adding things that have simplicial shapes. Well, so for example, we can see what the boundaries of a three-dimensional oriented cube are. They look like this. So that's something, and all of these kind of come also with methods implementing various kind of maps from cube categories. For example, on the cube, we can do something called degeneracies, and we can do something called connections. So let's do something like a cube connection. Like this, and see what it looks like. This is just top-dimensional slice. That's not super interesting. So let's throw its boundaries instead. So yeah, you get like this. This is kind of using these kind of constructors, a nice way of getting complicated string diagrams with crossing wires. In fact, the picture that I used here at the beginning is an example of one of these, the representation of one of these connection maps between cubes. I think I'm out of time. So as I said, please try this. Please try to break it if you can. And if you do, please don't just be self-satisfied by file a bug report. Thank you. That's it.
Are there any questions for the speakers, please? Richie?
I was just wondering, because you talked about there's a graph between somewhere involved. I was wondering how large the graphs we handle consider like.
So what can I have the microphone? So I'm not sure if people can hear me. So what we said with Diana in relation to graph isomorphism is that the problem deciding. So what we have is that the kind of the underlying data structure of these things, these oriented graded closed sets. What we showed, if we wanted to just kind of try to solve isomorphism for oriented graded closed sets, we get something which is equivalent to solving graph isomorphism. And that's basically because isomorphism of these things is the same thing as isomorphism of these Hasse diagrams. But also just one-dimensional kind of oriented graded closed sets are enough to encode kind of all loop-free directed graphs. So in that sense, even just deciding those is kind of equivalent to deciding the isomorphic directed graphs. So in that sense, so what we do instead is just focus on finding a solution only for the ones which are, or for that are kind of very particular ones which correspond to these regular molecules, and they have all sorts of very regular properties. So in that sense, and in that case, well, we've got, for now, the kind of the best algorithm that we come up is this kind of, so we've got n cubed log n. I haven't done any kind of serious benchmarking about this kind of shape isomorphism. What I've seen is that the, let's say the trigger, like on kind of, for example, if I try to use this on like this, if I try to generate cubes, so to like things start getting kind of too slow in the sense that I don't actually get the cube, I think, in dimension 8. So I can generate a 7 cube in reasonable time, and I think I have to stop the 8 cube. So, yeah. So, but I think pretty much if you stay in humanly reasonable dimensions, you shouldn't run into too many problems.
I was just mentioning because I think I found in practice there's pretty good. I found in practice the heuristic solvers that are available, like are very very fast to handle like lots of like. Pretty important this routine that maybe you should.
So yeah, I think already with the with the cubes, it kind of with cubes the size rises kind of very quickly. I think already, yeah, I think probably already the 6 cube is in the order of thousands of kind of faces, and then yeah, you get into millions. So yeah.
Okay, is there one more last question? Yeah. Lucas?
If you go to the documentation, the first slide, yeah. So this appears to be like a weak uniton theory, like Simpson's. There are a lot of degeneracies floating around there, and in a way they don't matter, but they also matter. Do you have tools that could are able to deal with this? For example, could check whether 2 diagrams are the same modulo rewiring degeneracies.
Can I have the? So right now, kind of the degeneracies are just part of the diagram in the sense that the diagram has a given shape, and then if some of the faces are mapped to kind of lower dimensional elements, they correspond. So in a sense, like the kind of the equality problem for diagrams we solve includes the degeneracies. I agree that yeah, probably in so for now we don't have any kind of methods that allow you to ignore the degeneracies. Of course, like if, as people who definitely high categories know, there's always a kind of trade-off. So what we've got in our diagrams, we have we have this kind of in informing diagrams we have a strict associativity and strict interchange law, so instead we have this kind of roundness condition on the shapes, for which basically to satisfy this we often need to fill the diagram with some degenerate cells. So in that sense, it's probably when you're doing stuff like 2-dimensional things, it's going to be a bit of a trade-off. Like if you have some kind of theory which contains lots of units or Mallory operations or things, you may be happier with something like mod PIO, which does the opposite choice and this has weak interchange. Otherwise, if you don't have too many degeneracies going around, you
you're probably going to be happy with this.
Okay, thank Amar and Diana again. You're gonna give it there, okay?
Yes. Oh yeah. Okay, yeah, that seems. Can everybody hear me fine? Yeah. Let me just set a timer for myself. Oh yeah, thank you.
Okay, so next we got Leonowski and Fabio Zanasi from UCL. Going to talk about string diagrams for layered explanations.
Yeah, thank you, Bob. I joined the other speakers in thanking the organizers, and also thank you everybody for being in the audience, either online or right here in Glasgow. And I'm going to talk about string diagrams for layered explanations. For this audience, I hopefully don't have to explain what layered explanations are, but string diagrams are. But layered explanations is a term we came up with, so that needs a little bit of motivation. So that's what one. Huh? Where should I point to this? To yes, perfect. Yeah, so what was I saying? Yeah, I'm going to give a couple of examples so that you get a very intuitive idea of what we mean when we say an explanation. I was quite happy that the last talk in the last talk before lunch mentioned some sort of explanations. I'm not sure if this is exactly connected to that one, but we'll see. The formalism at least looked like there are some significant similarities. So the main example we have in mind is the problem of data integration in systems biology. And what do we mean by data integration in systems biology? So in biology, you have this problem, or more particularly systems biology, you have this problem that suppose an experimental result says that some drug D increases the protein production of a protein P, and suppose somebody has done an experiment. It's all fine. Statistically, you can prove there is a relation between some sort of chemical or drug D and production of a certain protein. But then you can ask yourself a question: Can you model this on a sort of more mechanistic level? So rather than just having the statistical relation, can you have a model using some mechanisms we know about the way proteins are produced within a cell? Or can you actually reproduce that? So in some sense, it's about having this more abstract level, or more empirical level, I should say, and the more concrete, more sort of principled mechanistic level at the and how the question is, how do they talk to each other? This is what I mean by data integration. Second example we have in mind is autonomous decision making. For example, I can ask why did the self-driving car, why did it make the decision to stop here? Yeah, and then you better have a good explanation. Why did it make that decision at that particular time? Okay, then sort of from more technical perspective, blame analysis of component systems. When you have some complicated engineering system with multiple components and something goes wrong, then you don't want to throw everything out. You want to ask yourself a question: which of the components is to blame in this technical sense for the failure, or perhaps there can be multiple ones. Of course, it's not guaranteed there is just one, but still, you want to ask yourself which ones are to blame for the failure of the full system.
And this is sort of related to artificial intelligence, explainable AI, big thing at the moment. And so something that's important in all of this is the right level of abstraction. So you can imagine that we can have models of cell biology at different levels of precision, and depending on the kind of questions we are asking, depending on the kind of data we have available, it's going to be different questions we will want to ask, or different explanations. The explanation will have to be provided at a different level of precision. Similarly, for the second one, it's sort of important who the explanation is given to. Is it the driver of the self-driving car? Is it the insurance company? And so on and so forth. So somehow there is not the level of abstraction is going to be dictated by the purposes we have in mind, or like why are we asking for an explanation to begin with? And so pictorially, it looks something like this. This is a picture I found on the internet, where you could imagine here you have some natural gas, and you zoom in, you see the molecules of the gas, and then you can zoom in even further to a single molecule to see the actual atomic structure of how what the molecule is made of. Of course, this picture is a major oversimplification. The important point here is why I wanted to include this picture is that it's not just a zoom in. So somehow at all of these three levels of abstraction that we are talking here, it's actually a different theory that is in question. Like here in the middle, it's probably described by some sort of ideal gas and differential equations and so on. Here we're probably getting to chemistry, possibly some quantum stuff about how electrons are exchanged, and here it's a purely phenomenological description. So it's not that there is a very nice way to go between these layers. And so what we want to model on this sort of fairly general level is precisely this going back and forth between these levels. I have some motivation for the formalism here. But actually, in order to spend a little bit more time on the examples that I want to talk about, I'm just going to stress the first one. So we really want to take these layers of abstraction and different theories that describe systems, complex systems at different levels of precision seriously. Yeah, how it looks like mathematically is something like this. How much do I want to talk about this? So basically, these are morphisms which go from left to right. I'm one of those left to right people. And inside a box, it's just usual string diagrams. You can actually point to this thing, yeah. Oh yeah, it's inside a box. It's the usual string diagrams for a monoidal category. So here, if you only live inside one box, it looks like a monoidal category, and then it's labeled. The type is always labeled with two things. The first one in this type, omega. I don't know if this is actually visible, but the first letter is omega. Second letter is alpha. Omega refers to the type of this outside box, and alpha refers to the type of the wire inside it. And then now there are two ways of compose. Of course, if I have two of these things, I can compose them internally. So inside this box over there, in a normal monoidal category, or I can put two boxes together. And then, of course, that's this rule over here for the external composition, and for the internal one, I of course have to take care that all the types match. And then I have these pants and copants, which tell that somehow you can go you can go from the external composition into the internal one, and into the other direction, you go from the internal composition into the external one. And the important things are these translations between, so these outer types, omega and tau, are going to represent different theories at different levels of abstraction. So with this black triangle and white triangle, they allow you to go one level sort of deeper, and then correspondingly one level higher. There are also some two cells, which I'm not going to talk about this in this talk, but together with those two cells, you can give this sound semantics in the pointed profunctors. And in fact, this is sort of a formalization in this computer sciencey notation way of what is known usually as the internal string diagrams. Okay, and this is what I actually want to spend more time on, is how do we use this? So here I have a chemical rule, which you can find in any standard organic chemistry textbook. You take glucose and it reacts with adenosine triphosphate to produce something that's called glucose 6-phosphate, adenosine diphosphate, and there is a free hydrogen ion hanging along there. So this is now the rule that we want to somehow explain. Like, yeah, you could maybe if you're just doing a basic chemistry exam, you can just memorize that, pass the exam, and forget about it. So, but what's going on? What's going on? Sort of one level, one abstraction level below is this sort of rule. Of course, this is still sort of fairly high abstraction in the sense I'm not really explaining what happens with the electrons and stuff like that. But this is just for the purposes of giving an example. So we represent in our monoidal category as an internal box, and so this for us is like a black box, and you could imagine that actually this black box itself could be then opened, but I'll explain that in a moment. And what an explanation then ends up looking like is like so. So this now is a morphism in a layer prop, and so each layer, what we call a layer, is this area between any two vertical black bars. So in fact, the way things are defined here, if you only stay between these two black horizontal bars, you are within a single monoidal category. And in fact, this is a fibration, so you can project down. I haven't quite figured out the details of that fibration, but it's certainly there. So why do we call this an explanation? Well, because you start from the same ingredients as in the rule we wanted to explain before, so glucose and ATP, and the end product is at the same level of precision. So in this L+, which is just compositions of English names of chemicals, and you end up with the same stuff you wanted to end up. But in between, you sort of you go via one or two levels below. So you go through something that's called partitions of molecules, and you have this as a single non-trivial generating morphism. You have this A part mol box, and now you could imagine that somebody is dissatisfied with this. Okay, yeah, you can put all of this together, but really this doesn't really explain anything because you still have this black box here. And I say sure, but then you need another theory which now explains or sort of takes further down this rule that we had before. And as soon as you do that, you can just plug it in here instead of that black box there, and you have an explanation that goes even one layer further or several layers further. So this is a modular or compositional in that sense. Right. Okay, very quickly say something about explanations of two cells, because if you have some rule, this is now for string diagrammatic electrical circuit theory. This is the rule for composing the resistors. So before we had something like that goes nicely from the objects and ends up in the object. So an explanation then took a form of one cell. Now, because I mentioned this actually has a structure of a two category, so I can also give an explanation of a two cell like this. So this rule is now a two cell. In fact, I think it's an equality. The usual composition of two resistors, and just to quickly show how it works, I'm not going to say much about this. The point is, on this hand side, on the left hand side, you start again with the two resistors composed in series, and you end up with what you want. But here again, you have to you have to make sure you pass through a lower level in order for it to count as an explanation. But because I'm not discussing two cells, I'm going to go to the next example, which is some sort of minimal concurrency theory. So imagine a fragment of the calculus of communicating systems, which just has the zero process 0. You can append an action name in front of any process. You can compose two processes in parallel. I think that's it. That's a fragment. So like a very minimal one. And then you take you quotient it at you give it like a reduction semantics by quotienting it by commutativity, associativity, then the fact that 0 is a neutral element, and possibly something else. So that's sort of, you give a very coarse semantics to it. And on the other hand, you can give it the standard labor transition system semantics. And in fact, it turns out that there's a translation. There's a nice translation from this reduction. Oh, sorry, I forgot to mention the reduction rule. So whenever x dot any process and x bar come together in the sense that they're composed using these vertical bars, whenever they come together, you can apply the reduction rule to get rid of x and x bar and just have those processes alone. Yeah, and so in a label transition system semantics, it's somehow more fundamental because there are fewer rules. You just take everything up to the largest by simulation relation, and in order to make it into a monoidal category. And the way it works, so here is the reduction rule. So the only non-trivial, the only non-isomorphism that you have. So here you have the x bar, it comes together with x, and the r just says, okay, throw away the label and its barred version, and you're just left with, well, in this example, 0, 0. So you can just take and immediately translate this diagram into the label transition system semantics. So where everything's taken, I'm taking in the label transition semantics, I'm taking everything up to the largest by simulation. So what happens is this R just gets translated to this rule, and it looks exactly. The shape of the diagram is exactly like this, except that you replace R by these rules in the label transition system. Yeah, but it turns out that in this situation we can give a different explanation, namely a counterfactual one. Now, why do I call it a counterfactual one? Here I have to talk a little bit about the two-cell structure of this. So it turns out that this is another derivation of the same rule. So yeah, if you look at this one, here I derive it at the label, at the LTS level over here, and then I use again these triangle transitions to go from this level back to this level, but essentially, not essentially, but you get exactly the same boundary, so exactly the same domain and exactly the same codomain. But this time there is no two-cell from this one back to the high level, and that's why I call it counterfactual one, because this is not the actual one which you use at the sort of coarser level semantics. Okay, and with this I wrap up. I'm going to skip the formal definitions because this will take another 10 minutes to explain. The point is you can give formal definitions of both an explanation of a one cell, an explanation of a two cell. Yeah, so future directions, data integration, I mentioned that already. You can use counterfactual reasoning to generate hypotheses. So you have some counterfactual derivation, which hopefully suggests that at the high level, if you have at the high level, you're able to derive something, but you can't derive it at the lower level, then you can use You can use this sort of reasoning in hopefully future in some sort of automated way to generate hypotheses of what lower level rules you should have in order to rederive the higher level behavior. Okay, let me not say anything about that one. Then this is like sort of a very abstract goal is to formalize scientific explanations in a useful way. Counterfactual reasoning, for example, I mentioned blame analysis in the beginning. They use a lot of that to find those faulty components. And then on a mathematical level, I'm currently in the process of figuring out in what exact way you need to construct this Grothendieck vibration that we saw in the beginning in one of the examples. And this is very much work in progress, so any other ideas are more than welcome. Thank you so much.
Thank you.
So if you go back to the example you had about ACP to ADP early on in the talk.
Yes.
So,
yeah, this one, yep.
So one thing that comes to mind is this, in the middle, you are essentially making an assumption that you only need to worry about the OH group and, or you only need to worry about certain functional groups on the different chemicals.
Yes, that's correct.
Do you have any way of being able to update the explanation if it turns out that not only the functional groups are important, but also the other factors are important?
You need to add more rules at this level.
No, what I'm talking about is, because it feels like the way that you described so far, you've made an assumption that however whatever rule this is, this black box somehow has to assume that it's only the functional groups that it matches. Is there some way of kind of generalizing this out in an extra dimension which allows you to kind of vary how, or to look at some other, to add additional parts of your chemicals in, or this is just a vague.
Okay, I'm not exactly sure how, if I understand your question correctly, but what you can always do, you can go to a more abstract language where you have more vocabulary to talk about different parts of the molecules. Is that sort of along the lines what you're thinking, or still not quite?
I think still not quite. Maybe afterwards.
Okay, yeah, maybe it's a good idea.
Thank you. It's very nice talk. So I see whenever you cross a boundary on your sort of layers, you always say from like one wire to one wire.
Yep.
Would there be a way of going, say, one wire to multiple wires, like the components making up something in the wire?
Oh, sorry. So you're saying that there would be. Oh, sorry. Press the wrong button. You mean that instead of just one unique way to get from here to here, there will be multiple ways?
So like, say, we're going from left to right, so you have one wire of glucose.
Yeah.
Then maybe you could split that into many wires, saying what makes up glucose as individual.
Oh, yeah, precisely. We didn't see any examples of that, but you precisely have these pants and copants, which allow you to deconstruct. And then you could imagine here you open one of these things, which I call a window. You open it to a lower level, but this one just floats through. I'm not interested in it. I'm only interested in some detail about glucose. Yeah, you can do that. Yeah.
Yeah, I think we have to move on. I see Wachman is waiting there. Thank you again.
Thank you. I just escaped with the mic.
Copants is such a good name.
Yes, I love that.
Just a few hours ago. Got the USB. Yeah. Do you want to? You can take that on. I think I'll get on the. Yes. Gorgeous. Thank you.
Okay, so we got Lachlan, Pete, Tiboline, Marusha again from UCL. They're going to talk about making modalities lexicon.
Yes. Great. Can you all hear me? All right. Great. Yes. We're making modalities Laxman. Got to avoid the light. I'll explain the title in a second, but just before everything, the joint work with Timo Lang and Mariner Sadazadeh, my supervisor at UCL. What's really relevant at this conference is that this is another, like, I don't know if you've seen me before. It's my third ACT talk, and it's the third one that came out of an adjoint school project. So like, we're an inspiration to you all, I hope. But it's been really fruitful. So yeah, making modalities Laxmanoidal. What does this even mean? You already saw this slide a little bit. We gave the modalities of SLLM Laxmanoidal structure. Super informative, right? And we proved that the proof theory, when you add the structure, remains intact. I'm going to make sure this makes sense. It's kind of, so this is just an abstract. It's like small results just before coffee. So hopefully we should make it through all of this and understand basically everything that we've done. So for the background, for the stuff we need to know about in order to understand the results, we've got the cut rule. I don't know how many of you have seen proof theory. I sort of hadn't until I started my PhD. This is the cut rule. I think of it as if you can prove A from gamma, and if you can prove B from sigma with an A in it, then you can prove B from sigma with a gamma in it. Here, gamma and sigma are just some lists of formulas, finite lists of formulas. Sigma with an A in it just means that A is one of the formulas, right? And then sigma of gamma is the same list of formulas, but you replace the A with the gamma. I think that's as technical of proof theory as I'm gonna get. So if you squint a little bit, it really looks like composition. Yeah, everyone nodding in agreement. I think it looks a bit like composition. Really, quite formally, it's composition in a multi-category. If sigma and gamma were just single formulas, this would be like on the nose composition of deductions or whatever you want to call it. But I'm in the logic department at UCL, or logic group, so we call it using lemmas, which is also a very important thing. So, you know, we're category theorists, we need composition, it's important for us. Logicians need it, it's important. Cut rule, super important. But the cut rule is also super annoying for this reason. So if you try to do something called proof search, don't know how many of you have heard of that. It's kind of when you start from the bottom. Wait, I can point with this. When you start from the bottom and try and go up, like you start from the conclusion and you try to see what was necessary to prove your desired conclusion. If you go from bottom to top, this A sort of comes out of nowhere, which makes proof search, i.e. the task of going from a desired conclusion to its axioms, very difficult, usually just like completely impossible. If you have the cut rule in your proof system and if you have the cut rule in your proof system, there's no way of just knowing where this A is going to come from. So that's kind of annoying. But then you have this notion of cut elimination, which is just having a proof system, but then proving that you can actually do without cut. We know and love cut, we want it for our proof theory, but formally you don't need it, you can eliminate it. And that makes proof search tractable. It means that, well, I think Girard said something about like a proof system without cut is like a car without an engine. So you like really need it to be a good proof system, but it's super annoying. So you know, you want cut, but you can eliminate it. That's quite a standard thing. So a logic that we study is lambeq calculus. You've probably seen, well, if you've heard me talk before, you've heard me talk about this before. It's this logic whose formulas are either atomic, concatenations, forward fractions, or backward fractions. These are the rules. I'm not going to go through every single rule. You'll see a categorical definition of it soon. The most important thing, I guess, is the axiom. Like any formula, from any formula, you can prove itself. That's kind of how I want to read this. And then I guess here we can describe this one. Like if you have a list of formulas where A and B are next to each other and that proves C, then you can just think of A and B as a single formula, A times B. And slightly more complicated rules for the other connectives. So that's lambeq calculus. That's the one we kind of study. Not kind of, that's the one we study. This is what it's used for. I'm not going to talk too much about what it's used for, other than it's cool to see what it's used for. Grammar. So if you set your set of atoms to be noun and sentence, N for noun, S for sentence, and we make this little dictionary, dog being a noun, likes being a transitive verb, food being a noun, you can then prove that dog likes food with these types. Dog likes food is indeed a sentence. And the rules of the lambeq calculus sort of mimic grammar, model grammar so well that this proof actually becomes like a model of a sort of, well, it's the grammar of the sentence, but mathematically. That's sort of lambeq's whole, well, not lambeq's whole contribution, but one of the, this is his first, like in the 1958 first lambeq calculus contribution, which is really cool. And then he also proved that lambeq calculus is cut-free, which is nice. So in a sense, then, we know that lambeq calculus is a category. It has the cut rule, but it has an okay, well, it's got a tractable proof search question because it's cut-free. Well, it satisfies a cut elimination theorem. People say it in many different ways. And in fact, the proof search is actually quite easy for lambeq calculus. Now, because this is applied category theory, we would rather think of it as a category. So lambeq calculus is a monoidal biclosed category. We know monoidal categories, right? We can multiply the objects and morphisms. There's a unit. It's all good. Monoidal closure is not always as popular, especially biclosure. It means that you have left internal homs and right internal homs. Maybe I can leave it at that. Maybe you can ask for clarification later. Let me know. As a category, C of the lambeq calculus, we're going to call it C of L when it's a category. The objects here are the formulas of the calculus, and the morphisms are the proofs. Which is a bit weird because, like we saw here, a proof is this tree thing, right? So what's the domain? What's the codomain? Maybe not super obvious. The domain is the left hand of the roots of the tree, and the codomain is the right hand. And what's composition? The cut rule. So C of L is indeed like it's a nice category. And this is sort of the basis of a lot of the theory of the work we've been doing at UCL and in the previous papers. So the limitations of lambeq calculus that have forced us to go to this SLLM business is that lambeq calculus, I mean, it's really good. It can pass lots and lots and lots of English, but nothing more than sentences, like we've heard from Bob earlier today as well. So, you know, going beyond sentences is kind of like the one of the many natural next steps to take when studying language using logics like this. And so we have one approach inspired by, like, I mean, it's not just us at UCL, there's a bunch of people, Jäger, Morel, Morchat, many more, who add structure to lambeq calculus in order to parse more language. So that's stuff I've talked about at last year's ACT, and there's a bunch of papers. I'll happily give you references for all of them if you want to know more. But basically, yeah, we need more complicated logics, more expressive logics to parse more than just sentences. So the logic we work with is SLLM. And if you understand why it's called SLLM, please tell me, because it's the lambeq calculus with soft sub-exponentials, which I would call like something else. But it's SLLM, we know it, we love it, it's a good logic. It's a really good logic, actually. I'll show you what it's like. So it's SLLM, it's just lambeq calculus with some more stuff. So bang, bang, the exclamation point, and nabla, defined by Kanovich, also at UCL, and some others. So that is, SLLM has the same formulas and rules as lambeq calculus, but also we've got two new formulas, two new kinds of formulas. We've got banged formulas and nabled formulas, if you will. And you, obviously, when you have new formulas, you need some new rules. Well, that's the whole point of adding new formulas. So we have some new rules that can do a little bit more than the previous lambeq calculus rule. So the most important one is up here, the top left rule, the multiplexing rule, that's known as. That's terminology from soft linear logic, I think, if you know that. And we will always read these from bottom to top. So here we're really reading that if you have an instance of bang A in whatever context, you can replace that with any number of A's. So banged formulas are reusable. It's kind of a way to think about it. And then, yeah, you can ignore almost all other rules except the structural rules. Here we see that if you have nabla A on one side, you can move it. You can permute it across other formulas. This is stuff you couldn't do in just lambeq calculus. So bang lets you reuse, bang lets you reuse, and nabla lets you move. The other structural rule just says that you can move nabla formulas the other way, right? And it turns out, it's not the point of this talk, but it turns out that adding this structure is sufficient to model references in natural language, which lets you go beyond sentence. And yeah, that's a whole other spiel. Also, yeah, this is what it looks like when you model reference. So here's Charlie sleeps, she snores, where she means Charlie in a sort of systematic way. This is, again, not the point of today's talk. I just want to show you that this logic is not just like made up for the point of this talk, it's actually very interesting, I would argue. Now, this is also previous work, but this is kind of where the crux of this paper that I'm presenting now came in. So we showed that SLLM can be thought of as a category. Again, we're going to distinguish between the logic and the category by calling the category C of SLLM. It's the same thing. The formulas are objects, the proofs are morphisms. But C of SLLM now, it's not just a monoidal biclosed category. It also has these extra structures. Remember, SLLM is lambeq with 2 extra structures, 2 extra modalities. C of SLLM is the same as the lambeq calculus, but with these 2 endofunctors, M and P, M for multiplexing, P for permuting. Remember, this is multiplexing, right? And so they're endofunctors on the syntactic category, and they come with this additional structure, a family of pi n's, a family of projectors, or you can call them what you want, but they're natural transformations from M to n copies of, or an n-fold product of the identity functor. So that's multiplexing, going from 1 to many. And then sigma here is a natural isomorphism from the permutation endofunctor times identity to identity times permutation. You can see here, you're just switching sides. Yeah, the P goes to the right on one side, and then it's a natural isomorphism, so you can go backwards. And for technical reasons, you need a co-unit for that permutation functor. Now, this is the crux. So this is all the structure you need for M and P. Like if you follow, there's a sort of machinery for, if you have a logic and you want to turn it into a category, there's many different kinds, but one machine, we follow like Mellier's categorical semantics of linear logic approach to turning sublogics of linear logics into categories. And when you crank that handle, this is all you get out. No more. And so one thing is that you don't require M or P to be compatible in some meaningful way with the monoidal product at all. So my background is category theory and like pure algebra. So I'm a bit like, oh, that's a bit gross. I mean, it's a naive like requirement that all functors between monoidal categories have some compatibility, but it would be nice if they all did, right? So naively, I was like, why don't we just make them lax monoidal? It's a logic, it's artificial, we can do stuff to it. But another more serious motivation here is that the models from previous work in terms of vector spaces did have lax monoidal structures. So it means that the logic and the model weren't actually that well in tune. There's other things as well that are, well, if you know, you know, but there are other things that could be rectified as well. But we tried fixing the model, didn't really work. So then we tried fixing the logic instead and make the logic fit the model better. And that's what this paper is. Enter monoidal SLLM. So just to remind everyone what a lax monoidal functor is, just to be like super clear about it. If you have a functor F between 2 monoidal categories, then it's lax monoidal if you can take products in the codomain category to products in the domain category in this fashion, which is awful to say out loud, but quite easy to read. M is a natural transformation that takes products in one category to products in the domain category, F of products in the domain category. And you also require this arrow from the unit in the codomain category to F of the unit of the domain category. Satisfying a bunch of equations that I don't want to talk about. They're fairly nice. And obviously, well, I hate this, obviously. And the oplax version is when you flip all the arrows. And it turns out the oplax category is like really, really horrible. I'll show you why. So these are the 2 rules corresponding to oplax monoidality of Bang and Nabla. So what we did was we had SLLM, and we added these 2 new rules to it. And when you add these 2 new rules to it and like crank that sort of category, like from logic to category handle, you end up making M and P oplax monoidal. But this is a horrible logic. It does not have, it's completely not cut eliminable because this statement can't be proven without cut. And like, yeah, it's like, so Timo, who's like a very senior proof theorist, was just like, oh, this is a horrible logic. This very immediate counterexample came to mind. And he just showed me that, yeah, immediately this resulting logic, oplax monoidal SLLM, has no future, because you can't compose basically, right? If you can't, so this statement can only be proven with cut, and we want to have a system where you can remove cut. So the two proof systems with and without cut are different now, because this can't be proven without cut. So that's bad logic. So instead we add the lax monoidal versions. And I mean, if you go back, they're just flipped, right? Lax, lax, flipped. Kind of makes sense. I hope it's sort of intuitive. So again, we read these from bottom to top. So here we go from a product in the domain to product in the codomain. The domain and the codomain category are the same in this case, but you see the functor has been sort of absorbed. And the same for nabla. And when you add these two new rules to SLLM, you end up with a new proof system. We called it monoidal SLLM. And then you have to ask these questions that we have about logics in general. Can you eliminate cut? And all the other questions. Is it decidable? Da, 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 da. And we proved that it is decidable. That's a different proof, but kind of simple. And we showed that it's cut-free, or we showed that it satisfies cut elimination. And that was done in 2 steps, kind of technical. We proved first that monoidal SLLM is equivalent to a generalized version of SLLM, and then we proved cut elimination from generalized SLLM. By generalized, I just mean that all the rules that we had that applied to like bang or nabla formulas now apply to bang or nabla lists of formulas. And by that, I use this really horrible logic notation where, like, if you have a list of formulas gamma, bang gamma is actually bang of everything in the list. So that's actually lax monoidality sort of baked into it. But so again, this is apparently a more common way of having modalities in substructural logic. And then, yeah, we proved their equivalence by showing that you can generate any or simulate any proof in one logic as in the other logic and vice versa. So the proofs are the same, or the theorems are the same. And then we showed that cut was eliminable from generalized SLM. And like, okay, this is a bit verbose. I'll just explain it. It's a proof by induction. So you have an arbitrary proof that ends in cut. Without loss of generality, it ends in cut. And you do induction on the depth of the proof. So the base case is when there's almost no depth. So that's the simplest proof you can have that ends in a cut. Then the notation, the language is that you transform it, which I don't really like, but you transform it into this proof, this much simpler proof, and it has no cut in it. Base case, success, great. Then you go through the whole really horrible case-by-case analysis. There's 12 rules in SLLM, in generalized SLLM, and then you have to prove that any combination of 2 rules followed by cut can be converted. So here's one example. Here's nabla right on the left-hand side and nabla left on the right-hand side. And then we cut along the nabla formula. And then you have to show that you can move this cut to a less complex, less complicated part of the proof, which is exactly what happens over here. Here we cut along A. So the proof, you kind of want to think there's a proof tree above here, and they're simpler than the proof tree above here and here. So the induction is looking pretty good. And I mean, it looked very good. We proved it for all the possible combinations of rules. Here's a different kind. I mean, we can get into the technicalities about the different kinds of cuts, but I've done the hard work, so you don't have to. Please ask me if you want to hear more about it, though. And so, yeah, what we've ended up with is monoidal SLLM. It's nice. It's a nice logic. It has all the properties of its sort of older brother, or whatever you want to call SLLM. So it has the proof theory that we want, but it now has this like requirement that will take us closer to, sorry, this is meant to be 1, 2 things that we did, 1, 2 things that we want to do. This takes us a step closer to finding complete models of SLLM. I mean, I should call it monoidal SLLM by now. And also something I haven't talked about at all is that it takes us closer to defining a nice graphical language. So when you have functors on your graphs, it will be nice if they're compatible with the reason you can draw them in the first place, i.e. the monoidal product. So yeah, that's work to come. That's what we did. Those are the references. Thank you all for listening. I'm done.
Thank you, everyone. Do you have a question here? So it kind of struck me when I saw you, there was no interaction between lambda and exclamation mark, and that's probably the reason of the problem.
No, that was actually a problem with, it's not in here because I didn't reference it. There was a previous logic where both bang and nabla
Oh, no, you.
Oh yeah, it's fine. There was a previous logic where both the properties of Bang and Nabla, so reuse and movement, were in the single modality, and that and another reason made the logic undecidable, so very not useful. So it was actually Karnovich who separated them. I think I gave him the idea. I'm not really sure. We were talking about it, and then all of a sudden there was this paper where he separated them, and it was really good. The separation made it a lot more tractable to prove that the logic is decidable. The derivation problem is decidable. But I did think of having a rule where you have reuse followed by movement, because in linguistic applications, any reuse is always followed by movement. You can't all of a sudden say John slept. Like that doesn't make sense. If you say John slept and slept is reused, it has to go somewhere else.
Yes, yeah.
You can say yeah. There's probably some spiders in there that make it possible, but yeah.
Okay, thank you. By the way, also they gave some alternative names there to SNLM. So
Huh?
they give some alternative names to your logic on the bottom.
Oh yeah, no, wait, what? Yeah. Oh, yeah.
All the things showed up there. Okay, thank you. Thank you again.
Thank you.
And different combinations showing up.
The weird accents. We can't speak properly. How do you turn this off? Hi, John. Can you hear me? You're muted, John.
Hi.
Hear me?
Yep, I can hear you. Can you hear me?
Oh, but you did something with it. When you disconnected. Oh, I didn't press anything. One of these has to be Scarlet and the other one has to be. Yeah, what did you do to turn the? You said we can do this. Oh, yeah, but this should be an effect. Right. You try speaking, John.
Sorry?
Yeah, but in the Zoom it wasn't indication. It was something. Yeah. John, say something again.
Hi there.
Didn't say it. But all this time it was working, right? All this time we were hearing the speakers. Yeah, I think that's it. Should we start over? Turn everything off. I mean, the Zoom is receiving the sound because you feed out to that. But okay, it's working. All right, I think we solved the problem, John.
Good.
Oh, excellent. We can hear you. So we can solve the other problem now. Would you please screen share?
Sure. Yeah. I'll do it. Sorry. Sorry. I want to share the right one. Yeah.
Okay.
Does that work?
Oh, it's black. Oh, yeah, there we go. Oh, okay, no, we'll see. Okay. Should I now go and try and steal this and see if that works? I think, yeah, you will not be able to. Try it. Yeah, that looks very nice. Should I do it? No, I don't know how to do that. I think I would suggest you make Jonah host. You make Jonah host. I think that's where it's selected by. I think it's going to take effect next time. Yeah. Yeah. Okay. Okay, great, John. See you in a bit.
Yep. Okay. Great. Sure.
So that maybe that answers your question. I don't think so. There's a camera somewhere. I don't know.
Hi, Jade. Hi, Christina.
Hi.
I see you staring at me.
Hello, everyone. Welcome to the last and final session today. Just before we start this talk, one thing I want to say is that there's going to be a community meeting on Thursday. So if there's anything you'd like to announce during that community meeting, then please let me know sometime before then. It could be a job announcement or any sort of things. But regardless, so first talk of this last session is going to be by John Bias. It's joint work with Kenny Corser and Christina Bissell-Copeland. It's called Structured Versus Decorated Coherence. So take it away, John.
Okay, great. Thanks very much for inviting me. I'm sorry I couldn't make it all the way to Glasgow. Christina is there though, so any questions you have after the talk, because later on she can certainly field. So it's about our paper, Structured versus Decorated Cospans, with Kenny Corser as well. So a question that's been on my mind for the last decade is, can mathematicians do anything to help humanity deal with a climate crisis? As you know, Europe is now in its worst heat wave for the last 200 years. But the real issue is that this is just the beginning of a much worse set of situations. This heat wave will someday be regarded as normal, and then there will be new heat waves, which are much worse than that. And so one thing that category theorists can do is to better understand networks and open systems. So life can be thought of as a very complex, hierarchical set of networks of various kinds, some rather concrete, like the veins in a leaf, many others more abstract. And these networks are ways of organizing open systems. So in thermodynamics and other subjects, an open system can be thought of as one that interacts with its surroundings. There's some type of boundary demarcating the edge of the open system, and stuff of various sorts, information, matter, energy, etc., can flow in or out through the boundary. Yeah, this is a very abstract bunch of concepts, and so that's why category theorists might be able to help understand it, because we're good at abstraction. So I was thinking about this, and I decided we should start with some rather simple examples, like electrical circuits. So your house and mine is full of electrical circuits, but you can think of open electrical circuits, that is, circuits that have some loose ends, getting them ready to hook up to other circuits. You can think of them as morphisms in a category, and sticking them together is composing them. And so a nice math question, as a warm-up for all sorts of harder questions, would be to describe the category of open electrical circuits, maybe just circuits with resistors, for example, as morphisms. So Brendan took a while to answer that question, but when he did, he answered a much better question. He came up with a general formalism for describing open systems called the theory of decorated cospans, which is part of what I want to explain today. Here's a picture. I was in Singapore at the time. Brendan first came as a kind of a visitor to the Center for Quantum Technologies where I was working. And that other guy on the left there is Blake Pollard, another student of mine who applied decorated cospans along with Brendan and me to another example, the example of Markov processes, open Markov processes. A lot of stuff happened. In 2018, Kenny Corser and I came up with another framework for describing open systems, rather similar, which we called structured cospans. And we did this because these are often simpler to work with than decorated cospans. And then Lina came to UC Riverside and helped us generalize the original theory of decorated cospans and relate it to the theory of structured cospans. Down at the bottom there are her funding agencies. And there's Christina and Kenny. So by now, structured and decorated cospans have been used to study and design also many different kinds of open systems. Open graphs are a mathematically simple example, and that's what I'll focus on just because they're easy. But more interesting ones for the purposes of applications are open Petri nets, which I worked on with Jade, open electrical circuits, open Markov processes, open dynamical systems, open Petri nets with rates, which are approximately the same thing as chemical reaction networks, and open stock flow diagrams, which I'll show you a picture of later. The last two are particularly exciting to me because those are open systems that have functors to the category of open dynamical systems. So they are ways of describing open dynamical systems. And they are both used now quite a lot in, well, not only chemistry, but also epidemiology. So an interesting twist occurred in 2020 when Patterson implemented structured cospans in algebraic Julia. There are a bunch of people working on algebraic Julia, the framework for doing category theoretic computation in Julia, which is a programming language that's supposed to be good for high-powered scientific computation. And using this system, those open Petri nets with rates, James Fairbanks and Mika Halter reconstructed some of a COVID-19 model used by the UK government. Here's a portion of this model, and this is a picture of a Petri net with rates. So this got a bunch of people excited that maybe you could use the structured cospan mathematics to actually do quite practical things. And a bunch of epidemiologists started talking to us. In 2022, Sophie Libkind, Andrew Baz, Mika Halter, and Evan Patterson, and James Fairbanks used algebraic Julia to build various models of epidemiology using open Petri nets with rates. Here, some of them are shown being composed, but they also used pullbacks and other category theoretic tricks to design big open Petri nets with rates. They have a nice paper about that. And then later, my old friend Nate Osgood and his grad student Xiaoyan Li joined the gang and really bumped it up to a higher level because they happened to be in charge of COVID modeling for the Canadian government. So they have hands-on, routine, day-to-day experience with epidemiology models. And they were the ones who argued that we should focus on open stock flow diagrams, which is a framework for modeling how entities of various kinds living in these boxes, these colored boxes called stocks, can move or along these double-edged arrows called flows from one box to another. So for example, sick patients can recover and so on. And these stock flow diagrams give you a way of describing sets of differential equations that describe the time evolution of such systems. And these are widely used by epidemiologists. But the existing software packages for working with these are not fully compositional in that what we can't do with the existing software is I build a model and then you somewhere else build a model, and then later we compose our models to form a bigger model. This is exactly what structured and decorated cospans are good for. And now we have software that does it. And in my talk on Friday, I'll talk more about that and the practicalities of that. But now I want to turn to the math of structured and decorated cospans so that you get an idea of what's really going on here. So I'm going to use the example of open graphs a whole lot. So here's a picture of an open graph. There's an input set A, an output set B, and maps from both those sets into the set of nodes of the graph. So N1 through N4 are called nodes of the graph, and then there are also edges of the graph. So what we have here is an open system of a very rudimentary sort, namely this open graph. So it consists of a graph, but it also has a kind of boundary or interfaces, namely these input and output sets A. And the point is that why work with open graphs? Well, because that's a nice way to describe how to build big graphs out of smaller ones. You can compose open graphs by gluing them end to end. So if the output set of one matches the input set of the other, you can identify them. So identify each node in the first graph with each node in the second graph if they're mapped to by the same element of B. And so you're really doing a push out there when you're sticking them together that way, and you get a bigger open graph. So it's a very intuitive process, just sticking things together. Now this composition, it's associative only up to isomorphism, because when you do a push out of graphs, you have to make up your mind how you're going to name these new elements, these new nodes. And if I call them X and X prime and you call them Y and Y prime, then your composite would just be isomorphic to mine. So if we pick a composite, just randomly pick one way to do it, that's fine and dandy, but then composition will be associative only up to isomorphism. But then that raises the question, what do we mean by isomorphism? I mean, it's sort of intuitively obvious that if I just relabeled these nodes something else, we'd get an isomorphic open graph. That's the intuition behind it. but we have to understand what category we're talking about when we talk about things being isomorphic. So the point is, there really is a category of open graphs. For example, there's a morphism from this open graph to this other open graph. Notice these actually have different, potentially different source and target sets. So what we have here is a map from A to A prime, where the points 1 and 2 are both getting mapped to the point 1 prime, and 3 is getting mapped to 3 prime. We've got a map from B to B prime that does the only thing it can. We've got a map here from this graph to this graph. So that's a map sending nodes to nodes, edges to edges, and preserving the property that preserving the structure that every edge has a source and target node. So like these two edges here are getting mapped down to one edge, and we can also map a graph into a larger graph that has extra nodes and edges. So there's a category of all open graphs, and that allows us to define this concept of isomorphism that we need for me to make sense of the idea that composition is associative up to isomorphism. So what we've got is the structure that sounds a little Baroque if you've never seen it before, but it's actually very familiar if you, after a while, you see it showing up all over the place. There are morphisms between open graphs, and composition of those morphisms is associative, but then open graphs are themselves morphisms. You can compose them, and that's associative up to isomorphism. So the structure that captures those two forms of composition is called a double category. So a double category has figures like this. They look like squares. So it has objects A, B, C, and D, and then it has vertical one morphisms, such as F and G here. Those were the functions between sets in our open graph example. But then it also has horizontal things, which I'll call one cells to distinguish them a little bit more from the vertical one morphisms. Those would be the open graphs themselves in our example. And then it has these two-dimensional things, which I'll call two morphisms, which would be a map of open graphs. In our example, would be a map of open graphs, sending this open graph to that open graph. So you can compose vertical one morphisms, and you can compose horizontal one cells. You can compose two morphisms, both vertically and horizontally. The interchange law holds that says that when you compose these two vertically and these two vertically, and then compose the results horizontally, it's the same as if you did it the other way around. That is, compose these horizontally, those horizontally, and then the whole thing vertically. Vertical composition is strictly associative and unital. Horizontal composition is only associative and unital up to isomorphism. That's a mouthful. We can certainly summarize that or state that much more efficiently using a bit more category theory, but that's the idea of a double category. So the question is, how do you get the double category of open graphs? And the key, which will lead us to handle many more examples, is to realize that an open graph is, for starters, a cospan of sets, where n is the set of nodes of the graph. But where the apex of the cospan, that is the set of nodes, is equipped with some extra structure, namely in the structure in this case of being the nodes of a graph. So we have not just a cospan of sets, but a cospan where the apex has some extra bells and whistles attached to it. And what is it? Well, it has the structure of a graph on n. So given a set n, a graph on n is a set of edges, and then two functions assigning the source and target of each edge to some node. So then an open graph is a cospan of sets together with a graph on n. So that's the paradigm of both structured and decorated cospans, is that you have a cospan, but then together with some extra structure on the apex. So how do you frame that in a general context? So there are actually two ways that we know of to equip an object of a category with extra data. So one, just for the purposes of this talk and for the term structured cospan, I'll call structuring. So the idea is that if you have a right adjoint functor, think of it as some kind of forgetful functor, you can give an object of A some extra structure by choosing an object of X that maps to it. So, putting a group structure on a set would be done in that way typically. But then there's another method which we're going to call decorating, which is that if you have some sort of map from your category A to cat, then for each object of A, you get a category F of A, and then you can decorate that object of A with an object of that category. So I want to develop both approaches and then relate them. So let's do decorating. I'm going to do that because it's harder. I've learned through many years of giving talks that people are less tired at the beginning of the talk, so you should actually do the harder stuff first, counterintuitively. So let's do the example of open graphs as a decorated cospan category. Okay, so for any finite set n, there's a category f of n of graphs on n. So here our set n is the nodes n1 through n4. Here are two different graphs, and here's a map of graphs that preserves the nodes, but can do interesting things with the edges. So it's a morphism in this category f of n. So these are graphs with a fixed set of nodes where the morphisms don't do anything to the nodes. Now, there's actually a way to assign to any finite set. Sorry, I should have said set here, not fin set. I was vacillating whether I should keep things finite or not, but I'm actually going to do all sets. So there's a map assigning to any set a category, which is the category of graphs on that set. But what kind of map is this? Well, it turns out to be a lax-monoidal pseudofunctor. That's a little bit of a jawbreaker at first. Pseudofunctor means that composition is that f preserves composition only up to a specified isomorphism that needs to satisfy some laws. We're not going to worry about that a whole lot, actually, because of shortage of time. But the interesting thing is the lax-monoidal part, namely that our functor preserves the monoidal structure up to a morphism. The monoidal structure on sets that I'm going to use is union or plus. The monoidal structure on cat that I'm going to use is Cartesian product. And so what I'm saying here is that if I take a graph on n and a graph on m, I can combine them to get a graph on the disjoint union of the sets n and m. And the way we do it is just the visually obvious way. Here's a graph on n, here's a graph on m. I just set them side by side and get a graph on n plus m. So we get this map phi, which I'll call the laxator, and it's lax. It's not an isomorphism because there are also lots of other graphs on the set n plus m besides the ones that fall apart neatly into these two pieces. So this is not an isomorphism. So in general, it turns out that given a lax monoidal pseudofunctor, you can define a decorated cospan, which is a cospan in A where the apex is equipped with the decoration in f of n, where n is that apex. So open graphs are decorated cospans where A is the category set and F maps any set to the category of graphs on that set. And then the idea is that you can compose decorated cospans. So if I have one here and another one there, where the second one starts where the first one left off, you can compose them. So you first take the two cospans, which I draw down here, and you do a push out of them. You can always think of a push out as first doing a coproduct and then a co-equalizer. And we think of it that sort of fancy way because we want to figure out how the decoration on n and the decoration on m combine to give a decoration on this push out. And so here's how it works. First, you use the laxator to take those two decorations and to turn it into a decoration on the disjoint union n plus m. And then, given that f is a functor, or at least a pseudofunctor, we can use this map C here and take f of c, and that will carry our decoration from the disjoint union to this push out. And so you can, that's the key thing, that this lax monoidality of f is what lets you compose decorated cospans and know how to deal with the decorations. So Kenny and Christina and I proved this theorem, which is a sort of souped up version of Brendan's original decorated cospan construction. So it says, suppose you have any category A that has finite colimits, and suppose you have lax monoidal pseudofunctors of the sort I've just been talking about, then you get a decorated cospan double category. So the objects will be the objects of A, the vertical morphisms will just be the morphisms in A, the horizontal one cells are going to be the decorated cospans, where the decorations make use of this functor F, and then a two morphism will be a commuting diagram in A together with a decoration morphism. So we have this decoration in f of n, and we can apply f of h to it to get a decoration in f of n prime. So these are both decorations in f of n prime, and we want a decoration morphism going from one to the other. In our example of open graphs, that would just be the sort of obvious kind of map of graphs that you need to map one open graph to another open graph. But there's a little bit more. In fact, you can tensor open graphs. If I have an open graph and another open graph, I can just set them side by side or one on top of the other in this picture. And that takes advantage of the coproducts in the category A. And so that's going to give some kind of symmetric monoidal structure to our decorated cospan double category. And so there's a souped up version of our result that handles that, which says that if you have the same hypotheses, but F here is a symmetric lax monoidal pseudofunctor, so that's the only additional hypothesis, then the decorated cospan double category we get is symmetric monoidal. I will spare you the definition of a symmetric monoidal double category because it's a little complicated, but it just means that you can tensor objects and all the various kinds of morphisms. Okay, so that was decorated cospans. It turns out that structured cospans are somewhat simpler when they actually work. And so remember, structuring is a different way of giving an object in A some extra structure. Namely, you pick a right adjoint functor from some other category X to A. So think of this as like the forgetful functor from graphs to sets. I have a set, I want to give it some extra structure, so I pick a graph whose underlying set of nodes is my set. So that's how structured cospans work. A structured cospan will be a cospan in A, but where the apex is of the form R of some object in the category X. So you should think of A as the category of objects with less structure. They form the boundary of our open system, boundaries of our open systems, and X as a category of objects with more structure. So that this is how it works in the case of open graphs here. R is the forgetful functor from graphs to sets. It picks out the nodes. But the interesting thing is that, of course, whenever you have a right adjoint, you have a left adjoint. So you also get a left adjoint going from A back to X. So using the adjointness property, you can reinterpret the structured cospan as a diagram in X going from the left adjoint applied to the feet into the apex. And this other way of thinking about it turns out to be a little bit more practical. And in particular, you can compose structured cospans simply by doing pushouts in the category X. We have to assume that category has pushouts to do that, but then it's nice and easy. So none of this fancy stuff about how you compose the decorations, which we had to do in the decorated cospan approach. So in our running example here, A is the category of sets, X is the category of graphs, and L of A, where A is some set, would be the graph with A as its set of nodes and no edges. That's the free graph. So you can think of these open graphs as in this funny way where you take these two sets here and you just turn them into graphs without any edges, and you just map them into this interesting graph here on the apex. So first, Kenny and I, and then Kenny and Christina and I proved a theorem about how to get structured cospan double categories. The second proof is much more slick and nice. So here we'll assume that both A and X have finite colimits. So remember, that means having pushouts and also coproducts, finite coproducts. And you have a left adjoint functor from A to X, then you get a structured cospan double category. So the objects are objects of A, as in the previous theorem that looked similar to this. The vertical morphisms are morphisms in A. The horizontal one cells are now the structured cospans, and the two morphisms are just commuting diagrams. All this is happening in the category X. And notice that here we automatically get symmetric monoidal as part of the result. So structured cospans are simpler, but unfortunately, not all decorated cospans can be seen as structured cospans. So initially I was hoping to get rid of the decorated cospans and just use structured ones, but it turns out that when we start doing applications, we encounter interesting examples where you need, apparently, we need to use decorated cospans. In particular, open dynamical systems, which I won't really get into here, but I will a bit on Friday, seem to need decorated cospans. And the key is that the forgetful functor from dynamical systems to finite sets has no left adjoint, which Kenny and Christina and I showed. So why I said that it seems that this is true is that there might be some, sneaky trick where you change your definition of the category of open dynamical systems or something, and maybe you could wriggle out of this problem, but we don't know how to do that yet. So this is theoretically interesting, but it's also practically important because over in algebraic Julia, various people have set up ways of manipulating and defining manipulating structured cospans. They can also do decorated cospans, but there's been more work on structured cospans. So it's now sort of a pressing issue, like, oh, how much do we need to develop the decorated cospan framework to do the practical things that we want to do, like fight disease and save the world. So this raises the question, for example, when can you take a decorated cospan category and see it as a structured cospan category? So of course, to do that, you have to relate the key ingredient for decorated cospans, which is this lax monoidal pseudo-functor from A to cat, to the key ingredient for the structured cospan category, which was this right adjoint functor from some category X to A. Now, if you stare at these two items and you think about it a while and you know some category theory, you should be reminded of the Grothendieck construction, because the Grothendieck construction is a trick for saying that whenever you have any pseudo-functor from a category to cat, you can build a new category called the integral of f, and that category comes with a functor back down to A. And it's not just any old functor, it's an especially nice kind called an op fibration. And in fact, like in our example of where R is the functor from graphs to sets, that is indeed an op fibration. And what that means, I won't go into the details of what op fibrations are, but what it means is that if I have a set with a graph on it, and then I have a map from that set to some other set, then I can carry that graph along that map and get a graph on the other set. So I can lift morphisms in A to morphisms in X in a nice way. That's the idea of an op fibration, a rough idea. So that's what you get for free whenever you have any pseudo-functor from A to cat. But we're assuming more when we're working with decorated cospans. We're assuming that F is a symmetric lax monoidal pseudo-functor, and we want more for structured cospans. We want R to be a right adjoint. The Grothendieck construction doesn't ensure that you get a right adjoint all the time. So we need to work a bit more. Well, luckily, Mike Schulman and also my former grad student, Joe Moeller, who's also there, I believe, and Christina Vasilikopoulou, proved just what we need, which is a relationship that deals with these extra complications in the Grothendieck construction. So if A is a category of finite coproducts, these three different items correspond to each other. One is symmetric lax monoidal pseudofunctors from A with its coproduct monoidal structure to cat with its product monoidal structure. The next one is pseudofunctors from A to Simon cat. So in other words, you can think of F as assigning not just a category to any object, but a symmetric monoidal category. And third, symmetric monoidal op fibrations from X, this category you build from the Grothendieck construction, to A. So let me illustrate these things in our running example. So if A is set and F is the functor, pseudo-functor sending any set to the category of graphs on it, I've already mentioned that it's lax symmetric monoidal, where the laxator sends any pair of graphs to the disjoint union. So that's one way to think about it. But in fact, each of these categories, f of n, has finite colimits, and thus it becomes symmetric monoidal using coproduct. So our pseudofunctor f can actually be thought of as a pseudofunctor from A to Simon cat. And now another thing that you notice here, which we're going to need in a second, is that F factors through Rex, the king of all categories. Now, Rex is the 2 category of categories with finite colimits. Rex stands for right exact, actually. So what I'm trying to say here is that the F of n is not just any old symmetric monoidal category. It's actually a category with finite colimits where the symmetric monoidal structure is coproduct. So it's an object in Rex, not just in Simoncat. And then the third point of view is that if you do the growth and deconstruction to this F, you get the category of graphs, and then the forgetful functor back down to sets is actually a symmetric monoidal op vibration. So these are the 3 different viewpoints on the same idea that are stated to be equivalent in these results of my friends and co-authors. So using that nice result, we were able to, well, both state and also help prove this theorem. So suppose you've got A with finite colimits and you have a symmetric lax monoidal pseudofunctor. That's just the junk you need to get a decorated cospan double category. But now, so by the result I just mentioned, that means you get a pseudofunctor from A to Simoncat. And now make an extra assumption. Suppose it factors through Rex. Suppose that the symmetric monoidal categories you get are actually categories with finite colimits. So then the symmetric monoidal double categories of decorated cospans and structured cospans both make sense, and they are in fact isomorphic. The decorated cospan category, double category you get just because you have this F here. The structured cospan one, what you have to do to get a hold of that is you do the growth and deconstruction, op vibration, but then using the extra hypotheses, one can show, and this is like the work, that this actually has a left adjoint. So now you have this left adjoint, and then that's, in other words, you show that R is a right adjoint, so that it has a left adjoint, and so you can define structured cospans. And then you still have to work further to actually prove that these 2 symmetric monoidal double categories are actually equivalent. In fact, isomorphic, very strong sense of equivalence. So that handles our case of open graphs, and it handles all the cases we know where you can describe the same situation using both structured or decorated cospans. So there are some open problems I'd like to end up with, to leave off with here. So there's the reverse question: when are decorated cospan double categories also structured cospan categories, going back? So actually, Daniel Sikala and Christina know a lot about this. So what I'm doing right now is I'm pressuring them to write their paper about this. This is a public pressure campaign to get this paper written. But we don't even with that, there are other wonderful results that they're going to write up. We haven't gotten like a necessary and sufficient conditions for when structured and decorated cospans are equivalent, I think. And then there's another twist. Sometimes even when they're not equivalent, the decorated, even when a decorated cospan double category is not equivalent to a structured cospan double category at the double category level, sometimes the corresponding categories actually are. That actually shows up for things like open Petri nets with rates. And so that's of practical importance. Well, when does it happen? Examples where it happens. And a bigger open problem is, can we develop some sort of taxonomy of the useful structured and decorated cospan double categories and maps between them? The maps between them are how we implement some different sorts of semantics of our open system modeling frameworks. So to understand this would really be developing a general theory of open systems and how you can, the syntax and semantics for them. That's sort of an open question there. That's not a very precise question at present, but there should be something general one can say about this. And finally, will someone create software that will do practical things, not just with the categories of structured and decorated cospans, which most of the work has been using just that, but also the double category. In fact, some of the work has been using the double category structure because people have been refining disease models using pullbacks, and those are pullbacks in the categories of the vertical morphisms. And so the double category approach is actually already showing up in practical context, but the software doesn't really fully reflect the double category framework. So there's a lot left to do there. Okay, thanks very much. That's it.
Thank you very much. Are there any questions in the audience? Yeah.
Can you say more about why you think a taxonomy of the useful structure decorated for simple categories would be like universal language?
I didn't hear the last little end. Why it would be
A universal language of open systems.
well, I'm exaggerating a little bit. Oh, I mean, open systems is a very general concept. So, but the point is that many different types of open systems have been described using structured and decorated cospans, and we're really just getting started. These are just some examples. I can easily crank them out. Basically, almost any language of diagrams, like electrical circuits or and many other diagrams, gives rise to a structured or decorated cospan double category. And these languages are used in different branches of science and engineering, electrical engineering, biology, genetics, and so on. And they keep, I suspect that there's like a general story of these different structured and decorated cospan categories, which are the ones that people actually need in biology and chemistry and engineering and so on, that they're not the arbitrary ones, there's something special about them. And so you could say it might be a bit like we've discovered 9 or 10 different groups, and we've discovered that like groups are cool, but we don't have like a theory of groups. And so we don't really know like, why do we like these particular groups better than some other groups? So I think there's a lot left to understand there.
Any more questions? Oh. Someone want to
Someone in the chat is saying, in my 2002
I'm afraid you'll have to speak up, or else Jade will have to repeat the question.
Can you hear me?
Now, yes.
Okay. So in the chat, someone is asking, in my 2002 PhD thesis under Luke Kaufman, I deal with decorated contraction graphs being algorithmically aligned in order to properly structure them. It seems that your problem is directly a categorical version of this.
That's interesting. What type of graphs did you say those were? I didn't quite catch that key word there, but I'll have to look into it.
Contraction graphs.
Okay. I don't know about those, so I'll have to look at those. Yeah. There should be lots of beautiful pure math examples of these categories as well. I've been sort of trying to focus in on the more applied math examples.
This was a question from Fernando Souza.
Yeah. Okay. Yeah, I'll check it out.
Yeah. Thanks.
Thanks.
So someone asked if feedback arrows are admitted, and yeah, self loops are admitted in those graphs. Okay. I can't look at the audience and see that they're like getting ready to move on. So
thanks for a very nice talk. So I want to ask, because you mentioned that you can always apply the algorithmic structure, except what you get isn't always the right answer, so you cannot always do structure constants. What I was curious about is the symmetric monoidal algorithm good enough to work with? So could you instead weaken your assumption of a structure constants, or would you lose all the simplicity that you get from the right algorithm to weaken the monoidal algorithm?
There might be something you could do, but as you guessed, that would sort of it would reduce the simplicity of the situation. So the fact that our forgetful functor R is a right adjoint lets us flip it around and think in terms of the left adjoint, and then composing the structured cospans is just as simple as composing diagrams, composing cospans in X. So we've sort of reduced the structured cospans to a special class of cospans. And so if you didn't have this left and right adjoint, then that wouldn't work. Now, it's still possible that maybe you could work with a different monoidal structure other than the co-limits or co-product monoidal structure. So we are also getting that benefit from our theorem, is that that we had a monoidal structure of a special sort. So there might be some intermediate case where you have this right adjoint, but you should think of A and X as symmetric monoidal rather than using coproducts. But I haven't really thought about that, so that could be interesting.
Okay, thank you very much.
Great.
One more round of applause.
Great, thanks.
Next speaker is online. I'm not sure who the speaker is, but the talk is called Categories of Kirchhoff Relations. And is the speaker here?
Yes, I'm there. I'm Amolak. And
Hi, Amolak. Welcome.
hi. So should I share screen? Can you see the screen now?
Yes.
Okay, so thank you for giving me this chance to speak. So the topic for my talk is the categories of Kirchhoff relations, and this is work done with Robin and with Shiroman. So I'm an electrical engineer. Robin, as some of you might know, is a mathematician, and Shiroman is a physicist. So we sort of came together to do this. And the main motivation of my work is the following. The goal is to try to come up with connections between electric circuits and quantum circuits. Okay, and to do this, what we do is we start with Lagrangian relations, and we define a subcategory of Lagrangian relations that satisfies Kirchhoff's current law. This helps in the electric circuit interpretation. On the quantum side, the connection comes from the fact that Comfort and Kissinger showed that the category of affine Lagrangian relations, which we'll come to what they exactly are isomorphic to qubit stabilizer circuits. Okay, so sort of the context of my work is what I've drawn as a picture here. So A flag rel on the right over a field of odd prime characters is equivalent to stabilizer quantum mechanics. This is what Cole showed along with Alex. What I do is I restrict my attention to per rel, Kirchhoff relations, and res rel f, which is resistor circuit. Okay, and then I study the relationship between resistor circuits, Kirchhoff relations.
It's much harder to tell how exactly.
Okay. So,
I don't know.
Seems like John Baez's mic is unmuted. Can the host mute that?
1 second. Okay, I think we're good now.
Yeah, okay, so the way I do this, and sort of the two themes in my talk are the following. I use a lot of graphical calculus, mostly graphical calculus for linear relations, and then I use parity check matrices to reason about relations. Okay, so just now I'll just go over a couple of slides about just what electric circuits are and give you some context and some sort of just general stuff about electric circuits, and then I'll come down to relations and how they can model these circuits. Okay, so here I've drawn an example of an electric circuit. The black blobs that are labeled 1 to 6 are like nodes. You can think of them as junctions or spiders also, and we'll use these terms interchangeably. The R inside the white boxes, the square boxes, are resistors. And then there's this diamond with an arrow. That's like a current source that produces some current. And then there's some voltage applied between 1 and 6, which is denoted by this plus minus V. Okay, and the general way electrical engineers study these sorts of circuits is to use Kirchhoff's current law and Kirchhoff's voltage law. Okay, so what is Kirchhoff's current law? Kirchhoff's current law is just a restatement of conservation of current. So if I apply it to say node 2 within the circuit, the statement I get is that the current coming into node 2 is the same as the current going out of node 2. Okay, so what do you get there? So you get I3, which is the current going out, is equal to the I1 plus I2, which is the current coming in. And Kirchhoff's voltage law is some sort of statement of conservation of energy for applied to electric circuits. So when I apply, and sort of the specific statement is that the algebraic sum of the voltage drops in a closed loop is 0. So if I apply, say, the Kirchhoff voltage law to the closed loop 2, 3, 4, 5, and then back to 2, the sum of the voltages will be 0. And we use both these laws to analyze and study electric circuits in electrical engineering. Okay, so the view that we'll sort of emphasize throughout the talk is that we view circuits as relations. Okay, and there'll be relations between input voltages and currents and output voltages and currents. You can also write this in terms of a matrix. Okay, and the matrix then satisfies this sort of an equation Hx is equal to 0, where X is the set of input voltages, output voltages, input currents and output currents, and this is a column vector, and H is some sort of matrix that characterizes the circuit. We'll later see that this is actually the parity check matrix. Okay, now we'll come down to relations. Okay, so first I'll talk about linear relations, and then I'll define Lagrangian relations. Okay, so linear relations, the objects are natural numbers, M and N. Okay, and one way to think of this is sort of the number of inputs and outputs to an electric circuit. The maps are linear subspaces. Composition is given by relational composition, and identity is identity relation. Okay, so one can sort of think of this as inputs and outputs to an electric circuit, but the electric circuit itself is sort of a linear relation. Okay, now the important thing here is that linear relations have this graphical calculus associated with them, and this was sort of shown by Zanasi in his thesis, and then Pavel and Zanasi wrote this paper on graphical affine algebra, where they actually apply it to electric circuits. But here we'll just sort of review this. Okay, so here I've drawn the generators for linear relations. The black blobs, the black dots, you can think of as copying. The white ones you can think of as adding. Okay, and the boxes with an k inside them are like scalar multiplication. Read these diagrams from bottom up. Okay, so we'll just go through it. So look at the first diagram, say in row 1. It has one input coming in, and then that goes into the black dot. There are two outputs coming out of that. So one way to think of this is to have some input, say x coming in. The black dot's intuition is that it copies and then gives you two copies of x as output. So you get the relation x comma xx, where x is in the field. The white dot, for some, like just some intuition for the white dot, you look at the diagram, the second picture in the second row. Okay, so that has two inputs coming in from the bottom, and then they're incident on the white node, and then you have one output. The way to think of this is that you have some input x and y coming in, the white dot adds, so you get the output x plus y. Okay, the white box with a k inside it is like scalar multiplication. So say you have x coming in from the bottom, you have this k, you multiply it by k, and you get output kx. So this defines the relation between x and kx. Okay, and if you flip the direction of the x, this k box, you multiply by the inverse. Okay, so now what you can actually do, and this is what Pavel and his co-author showed in the paper, is that you could reason about electrical elements using this calculus for linear relations. And if you want to add sources, you could have to go to affine relations, but we won't worry about that just now. So let's just do an example. Let's see how you can reason about a resistor just using this black and white generator. Okay, so here I've drawn a resistor. Okay, so that's the picture on the left. And let's read through the picture. Okay, so you have I1 and V1 as the input at the bottom. Okay, and then let's just trace these things out. So I1 goes into the black dot. Okay, one copy of I1, think of the black dot as copying, goes through to I2. The other copy goes into this R box. It gets multiplied, and it then hits this white box. Okay, there's V1 coming from the bottom and into the white box. The white box sort of acts like addition. So what you get out are these two equations, okay? And these two are actually the KCL, the Kirchhoff current and voltage law for a resistor. So you get I1 is equal to I2. That's the Kirchhoff current law for a resistor. That's just current into a resistor is the same as the current going out of a resistor. And V2 is equal to V1 plus I1R is Kirchhoff's voltage law. And for a resistor, this is like the Ohm's law. Okay, now the second picture I've drawn is a current divider. That's slightly more complicated, but it's a device that we'll need in our presentation. One, for now, the running intuition for a current divider is that it divides the current depending on these scalars. So these weights that are associated to the wires. Okay, we'll come back to what this exactly means. Okay, so now what I want to do is I want to sort of fine tune my structure to capture this, the electric circuit, and specifically to capture this current and voltage grading. Okay, and what I'll first do is basically sort of the mathematical structure that does that is Lagrangian relations. But before that, I'll just review what a symplectic form is, and that will set us up to define what Lagrangian relations are. So symplectic form is just a map from V tensor V to the field. And it's bilinear, alternating, and non-degenerate map. I denote it by omega here. And any space with such a form is called a symplectic vector space. Every symplectic vector space has a Darboux basis. So it has this, so you in the Darboux basis, you can write the vectors as some Q1 to Qn and P1 to Pn. So it has this grading. And then the symplectic inner product satisfies these properties. Now, symplectic vector spaces, remember, are always even dimensional. Okay, so now in the Darboux basis, and this is why we focus on it, you can write the symplectic form in terms of a matrix, which I'll denote as J. And this J is like a block of diagonal matrix of identity and minus identity. Okay, and then you can write the symplectic inner product, say omega of X and Y, as some sort of matrix J acting between X and Y, where J is the form. Okay, so now what are Lagrangian relations? So just to define that, we'll define what a symplectic dual is. The symplectic dual of a linear subspace of V is a symplectic, is a linear subspace U of omega, such that the symplectic inner product of U prime with U goes to 0. Okay, so one way to think of this is that the symplectic dual is some sort of linear subspace that's orthogonal with respect to the symplectic form. Okay, and then a Lagrangian subspace is this a subspace that's equal to its own symplectic dual. So for that case, U is equal to U omega. Okay, okay, so this will help us define the category of Lagrangian relations. So the objects are natural numbers and they correspond to graded vector spaces. The maps are relations where the state is Lagrangian. The identity is identity relation and composition is relational composition. So what does this mean? Sort of an easier definition, especially for a talk, is the following. So a Lagrangian relation can be graphically depicted as a linear relation V that satisfies this additional condition. Okay, and this sort of picture that I have drawn is capturing the fact that the linear relation is equal to its symplectic dual. Okay, so V is equal to V perp with these additional twists and -1 multiplications. Okay, and what is V perp exactly? V perp is the orthogonal complement of V. Okay, and the way to go from a relation to its orthogonal complement is to hit it by this perp functor from linear relations to linear relations. So it goes from linear relations to itself, but it maps every linear relation to its orthogonal complement. Okay, now using this graphical definition, you can actually show that current dividers, resistors, junctions are all Lagrangian relations. And these are the electrical elements that we are interested in. Okay, now, I've talked a little bit about linear relations a little bit about what Lagrangian relations are, told you a little bit about the graphical sort of picture. Now we'll sort of switch tacks and we'll go to matrices, okay? And we'll specifically focus on parity check matrices. And one of the reasons to do this is that the connection to especially quantum error correction becomes much easier to make once you're in the parity check picture, because in the parity check picture, in the quantum side also, there's this grading of the X and the Z, okay, which actually maps to the voltage current grading here, but we'll come to that. Okay, but that's sort of the motivation to look at parity check matrices. So any linear relation can be specified as a set of vectors, X and Y, satisfying the following equation, where H acts on the X and Y to give you 0. X and Y here again can be thought of as a set of inputs and output currents and voltages. Okay, now for linear relations, and this result is well known in coding theory, you can put H into standard form, and the standard form is identity followed by A, and the standard form is unique up to column permutation. So that's why you have this sigma that you compose with at the end. Okay, now what we showed, one of the results that we showed in our paper is that, you can define a similar standard form for a parity check for Lagrangian relations. So it's a graded matrix, it's a graded parity check matrix. And the way to think of this parity check matrix is the following. So the first row is Y, 0, identity A transpose. The second row is -A, identity 0, 0. Okay, now think of electric circuits. In electric circuits, Y corresponds to the adjacency matrix of the electric circuit. Okay, so Y is equal to Y transpose. A encodes for the connections to and from the circuit to the outside world. So they capture sort of the adjacency of those connections. Okay, and then there's this sigma S that you compose with. Sigma S is the set of symplectic permutations. So you're allowed to permute the columns, but you have to permute them in a way in which you preserve the grading. So you can permute voltages with voltages, currents with currents, but you can't intermix the grading. So there's no permutations in which you can mix the current with the voltage. Those are not allowed. So this is sort of the standard form for Lagrangian relations. Okay, now using the standard form, we'll try to define some other categories. So the first category that we'll define is the category of Kirchhoff relations. Okay, so a Lagrangian relation from N to M satisfies Kirchhoff's current law and is hence a Kirchhoff relation if for all QP and Q prime, P prime and R, the following equality holds. Now, from now on, the running intuition for Q and P and Q prime, P prime is that you can either think of Q as the position or as the voltage. Okay, think of P as either momentum or current. Okay, and then this equality that I've written down here, that Pj is equal to some primed Pk, is basically a restatement of either conservation of current or conservation of momentum. You can look at it either ways. And then the second condition is translational invariance. So if whenever lambda, which is like a scalar in the field, and QP and Q prime, P prime and R are in R, then if you translate the positions or the voltages by a constant, which is denoted by this lambda m with a vector on top. So lambda m with a vector on top is just a column vector with each entry equal to lambda, and you're translating the positions. And if you still end up in the relation and you stay within the relation, then the relation is said to be translationally invariant. Okay, and then we showed that for a state R in Lagrangian relations, the following is equivalent. R satisfies Kirchhoff's current law, R is translationally invariant. In fact, you can actually think of translational invariance as some sort of restatement of Kirchhoff's voltage law. And the way to think of that is that in an electric circuit, if you change all the reference voltages throughout the electric circuit, it makes no difference to the electric circuit because only the voltage differences matter. Okay, so you get this some sort of, I think there's some sort of special version of Noether's theorem. You can think of it like that. Okay, so now what we want to do is we want to define standard forms for Kirchhoff relations also. Okay, so the Kirchhoff relation standard form is the same as the Lagrangian standard form, except you have this additional constraint that captures Kirchhoff's current law or translational invariance. Okay, so y on 1 is 0 and a on 1 is 1. So this vector 1 is a column vector of just ones. Okay, so it's a column vector with each entry 1. And the way to think of this condition that a on 1 is equal to 1 is that you can think of sort of quantum mechanically, the way to think of it is that it's mapping the maximally mixed state to the maximally mixed state. Okay, so it's mapping the maximally disordered input to the maximally disordered output. And one way to think of this is also to think of A as being quasi-stochastic. So the rows of A have to sum to 1, but you're allowed negative entries. Okay. So now this gives us a subcategory or a subprop, which is the subprop of Kirchhoff relations. Okay. Now Kirchhoff relations do have resistor circuits in them, which is sort of the intuition that we wanted to go through with. But they also have this sort of new element, which we call ideal current dividers. Okay, and this is a physical manifestation of the quasi-stochastic condition. So the condition A on 1 is 1. The physical manifestation of this is that there are current dividers also in Kirchhoff relations. So you get the following universality theorem, that all maps in Kirchhoff relations are generated by current dividers, resistors, and junctions. Okay, and this is sort of nice because this means that, you can reason about any relation in Kirchhoff, in the Kirchhoff category, just by drawing an electric circuit comprised of resistors and current dividers and nodes. And then you can talk about the properties of the Kirchhoff relation. Okay, now, I'm an electrical engineer and sort of, we know a lot about current dividers. We know a lot about resistor circuits, but we know a lot more about resistor circuits than we know about current dividers. Okay, so a natural question coming from that perspective is, how do you get rid of the current dividers? Okay, and the way to get rid of the current dividers, sort of the formal way to do that, is to restrict A not to be fully quasi-stochastic, but to be deterministic. Okay, so that is that there's only one in each row of A. Okay, and then you get deterministic Kirchhoff relations. And in fact, this is a prop studied by Baez and Fong in their paper on Lagrangian relations. And they also sort of use this to isolate resistor circuits, but in a slightly different context. Okay, another way to isolate some more subcategories are to use the concept of power. So if you think of a relation as an electric circuit, okay, you can associate a power to an electric circuit, and that's the power consumed by the electric circuit. Okay, so the expression for power is given by this: P is equal to minus Q transpose YQ. Okay, and the relation is said to be lossless if there's no power consumed by the electric circuit. Okay, Now, so for R to be lossless, that means that Q minus Q transpose YQ must vanish. And that implies that Y must vanish. Now, in terms of an electric circuit, the way to think of Y is that it encodes for the resistors. Okay, and if Y vanishes in Kirchhoff relations, all you're left with is ideal current dividers and junctions. The adjective ideal before current dividers is there for a reason, and it is because it consumes no power, and junctions don't consume any power. So then if you define these lossless categories, and you can do this for Lagrangian relations. Here is an example, I do it for Kirchhoff relations. Any state in loss curl has Y0, so there are no resistors. That's the power consumed by the circuit goes to 0. And A on 1 is 1. Okay, so you're allowed current dividers and junctions. And this gives you sort of what lossless Kirchhoff relations are. And this is actually a universal set of generators for lossless Kirchhoff relations. Okay, and this is sort of the last main slide. This is the big picture of what I was trying to tell you about. So first we'll go row-wise through this picture, and then we'll go column-wise. Okay, so the first row is Lagrangian relations and its associated subcategories. This is where most of what Bayes did and what Cole have done is on that level. Okay, the second row is the Kirchhoff relations and its subcategories, which is what we were interested in studying. And the way to go from the first row, that's Lagrangian relations, to Kirchhoff relations, is to impose Kirchhoff's current law. Okay, and that constraint brings you down to the second row. The way to go to the third row is to impose determinism. Okay, and then that isolates resistor circuits in its associated subcategories. The first column, and we start from the left, are the lossless categories. So they are those categories that correspond to power equal to 0 for those relations. So you get lossless Lagrangian relations, lossless Kirchhoff relations, and spiders. The second column is linear categories. Okay, so that's Lagrangian relations, Kirchhoff relations, and resistor relations. The third column are affine categories. And the way to go from the linear one to affine ones, in the case of Kirchhoff relations and resistor relations, is to add active components of electric circuits, which are called sources. So a battery, for example, is a voltage source. So what you can do is you have these universal set of generators for Kirchhoff relations, and all you have to do is you have to supplement them with voltage and current sources, and you get the universal set of generators for affine Kirchhoff relations. So what I have written in the brackets here in this picture are just the universal set of generators for each of these subcategories, and this is what we prove in some detail in the paper. Remember that the quantum connections comes from the fact that affine Lagrangian relations over a field of odd prime characteristic is equal to odd prime dimensional qubit stabilizer circuits. Okay. Okay, so sort of the road ahead and stuff that we are sort of thinking about just now, firstly, our connections to qubit error correction. So what Cole did was he showed that affine Lagrangian relations exactly correspond to stabilizer circuits. But what do affine Kirchhoff relations correspond to? And the reason you want to answer this question is that affine Kirchhoff relations is exactly that categorical structure that captures the behavior of electric circuits. Okay, especially these circuits comprised of current dividers, resistors, and junctions. Okay, and so what you want to do is you want to interpret the generators as maps, say, on a Hilbert space and try and understand what they mean in terms of quantum operations. Okay, so then you'll be able to, the motivation is that then you will be able to import all these techniques you know about electrical network theory to quantum circuits. Okay, so a lot is known about electrical circuits, especially about resistor circuits, for instance, say, we know how to simplify resistor circuits. We know how to design certain resistor circuits, circuit synthesis. We also know how to, optimize electric circuits, how to analyze them. So the hope is that, under using this affine Kirchhoff structure, you'll be able to import many of these sort of simplification strategies to the quantum side. And then sort of, we talked about these parity check matrices and their standard forms. Do they correspond to any normal forms for electric circuits? And then does the interpretation on the quantum side help us sort of clean up some of the proofs for stabilizer normal forms? Yeah, that's all. Thank you.
Thank you very much. This question.
Hello, very nice talk. Can you hear me?
Yeah, I can hear you now. I can. Yeah.
I noticed you're missing out a lot of circuit elements. So I'm wondering what you would do with capacitors, inductors, memristors, even higher level ones like transistors. Do they fit into this, or what would you do with that?
Okay, so they don't get into what I have done just now, because actually I have no analog of time in the formalism I have set up. But these So Pavel and Zanasi wrote this paper on GAA, where they do actually have time, as they bring time into it by changing the ring that they're dealing over. And when they do that, you can talk about, so capacitors, inductors are dependent, like they're dependent on time. So then you can bring in time into the picture, and then you can talk about those and try and sort of understand what they mean in that context. Yeah.
Do you think they'll have a use for the quantum mechanical?
So there are some guesses to what they might mean quantum mechanically. So a capacitor, so there are these time delays that these things can do. And one way, sort of, there are these things about delayed traces in quantum mechanics. And if you can actually set up a capacitor in a similar formalism, then you hope that they model something like delayed traces or some sort of memory element.
Thanks. Any more questions? Okay, well, thank you again for your talk. The last talk will be in person. It'll be a software demo. By Christopher Brown, and it's about individual.jl. That's a Julia library for rewriting individual-based models for epidemiology.
It's going to take some time to find this.
And it might take some time to set up. So. Yeah, take your time.
Yeah, it's Google Slides.
Right.
Okay. Cool. All right.
Take it away.
Thanks, everyone. So this is, I'll be presenting some joint work. This was supposed to be Sean.
Use this one.
It should work. Okay, I didn't press anything, but I was supposed to press it. Love it. Yeah,
The mute button was.
oh, okay. Then probably. Let's check this now. Okay, yeah. I don't know where the back. Yeah, it doesn't matter. Okay, sorry about all the delays. Cool. So this is joint work with Sean Wu at the Institute for Health Metrics and Evaluation, James Fairbanks, who runs the Generalized Algebraic Techniques for Advancing Science Lab at University of Florida, and Evan Patterson and Sophie Lipkind at the Topos Institute. So I'm going to talk about epidemiology as a case study and what an individual-based model is and the intersection with ACT, which is really this theory of graph transformation, also called graph rewriting. And despite the name, it's much more general than just graphs. So what we're proposing is a very declarative way of doing this. So I want to contrast that with how individual-based models work in practice right now. So what is an IBM? So often when we're doing a simulation, we care about some sort of collective behavior. But often we can get away without representing each individual person or molecule or rabbit. And you can sort of summarize things with a single number and some average statistical properties. But sometimes you really can't get away with that kind of averaging. So certain epidemiological models that depend on an individual's antibody state will lead to some pretty discontinuous behavior that you wouldn't be able to recapture with a simple ODE. But once you need to actually implement that in software, it turns out that there's a lot more complexity involved in the implementation. And that additional complexity makes things difficult to share. It makes code difficult to modify. And it's just pretty hard to do in general. And sort of what summarizes the sort of state of how things can get, how bad things can get, is that you might have some COVID model that is going to influence policy decisions, and someone asks a question about the validity of your model and says, well, what is the model? And you'll have nothing to point to other than the code itself. That is not great because code is not really easily statically analyzed, and you don't have any sort of means of analyzing it aside from running it itself. So that's very different from having a clean mathematical formalism in addition to an implementation. So how do these things work in practice? Well, it's a quite natural thing to do if you're modeling different types of individuals, to use think of individuals as instances of some class in an object-oriented languages. So that's precisely what you can do, and it can be nice, but then these hierarchies can get very complex, and it becomes basically not impossible, but very difficult to modify these very complex hierarchies if you want to add in behavior. And moreover, your state of the world that you're modifying, that each of these individuals can change, is your general program state. And that means that there's a lot of, the system's very unconstrained what the state can be and how agents can change the state. And that means you need a lot of regression testing in general to make sure that you're not introducing bugs. So, and lastly, how the dynamics of these things work is that you'll have some sort of time step, and given the frequency of a certain event happening during that time step, you'll then fire those events and update this global state. So how we want to change how we interact with these things, and not using this object-oriented paradigm, is to use rewrite rules for our dynamics and to use C-sets for our state. So the first thing I'm going to talk about is how are we going to restrict the notion of state for an agent-based model or individual-based model, such that it's not just the general programming state, but something much more controlled. So what I have here on the left here is a attributed C-set schema. You can think of this as a database schema. Essentially, it is at least the C-set part is just a functor from some finitely presented category into set. And the attributes allow us to add non-combinatorial data to some of our objects. So the meaning of an example like this would be to say that I have a set of edges and a set of vertices with source and target functions. So that's going to be, I have a graph somewhere. And additionally, grass lives on certain vertices, and that grass has an attribute telling you how green it is. There might be sheep and wolves living on particular edges, and they have a certain energy. Things like this. So this becomes our formal model of the state that we can modify, and it has some advantages in virtue of it being much more constrained than a typical individual-based model. Moreover, because we have a lot of theory of how these attributed C-sets works, we can do things like take limits and co-limits. We have general infrastructure for finding homomorphisms and arbitrary attributes, and so querying becomes easy to declare, and the work has already been done to implement it. So we can just take advantage of a lot of the infrastructure that already existed. And so, yeah, let me talk about sort of the relationship between these different packages. So catlab.jl implements C-sets and a lot of the theory, limits, and co-limits there. So it's sort of like the backbone. Algebraic rewriting extends that with this theory of rewriting, which I'm going to explain on this slide. And then individual JL will be a much more user-facing library, which is supposed to have no category theory exposed and really allows epidemiologists and domain experts to interface with the machinery that is going on in these other libraries. So I want to explain what a rewrite rule is in this framework. So a rewrite rule is a partial morphism from some input object to an output object. And you can also think of that in terms of a monic span, where you have a monic morphism from some pattern to be replaced. We then have some non-deleted sub part of that, and we then map that into, embed that into some replacement. So what is the meaning? So let's see how this actually gets computed. If we have some state of the world, M here, then we can compute the deletion aspect of a rewrite rule by taking a push out complement. And this is our way of capturing the fact that I has been, in some sense, deleted. I think people are maybe more familiar with the idea of a push out as gluing together. And essentially, this K here is essentially making sure that we glue our new information into the correct place. So in general, a rewrite rule has a deletion and an addition step. And you can compute it purely with these categorical operations of push out complements and push outs, which are very straightforward to compute with attributed C sets. So the first decision that you need to make when you're trying to use individual.jl is to pick a C set to represent your problem. So this is a modeling decision, and I have two alternate ways that we could represent C sets for the SIR model. If we want to have a common abstraction for agent, but we also want to represent the three different types of agents. So up top, there's a sort of set of susceptible labels, infected labels, recovered labels, and those can be attached to certain agents. That has some upsides and downsides. One downside would be that perhaps we can put multiple different labels on an agent, and in this case, that might not be desirable. In other cases, it might be desirable. Down here, we're going to give each agent a unique disease state, and that disease state can have the attribute of being S, I, or R. And so these are just some alternatives, but we'll actually work with the top one just for examples. And in CatLab, you would declare such a schema just like this, where you give the generating objects and generating morphisms. And then you generate a data type, which can then efficiently represent this, as well as be used to do sorts of categorical constructions. So the basics of the SIR model would be that there's two types of things that can happen. There are infections, which are susceptible infected people interacting, informing two infected people. And there's also recovery events, where at a certain probability, infected people just recover. So what would this look like as a rewrite rule? Here's the infection rewrite rule. So the top line here is the rewrite rule. And we're saying that our pattern that we're going to match is a particular infected person and a particular susceptible person. We're going to delete the susceptible tag, and we know that we deleted it in virtue of it being in the left-hand pattern, but not in the I. And on the right-hand side, we're going to then add an infected label to the agent here. And so this is just the general rule that you define, but then at runtime during your simulation, you're going to have a particular world state, which we can call G, and that's going to have other stuff going on, such as this recovered person. But given a particular match of our rewrite rule, we can then compute our next state by first taking a push out complement and then taking a push out. So I think it's important to state that the implementation is captured by push outs and push out complements. So really, the modeler did not have to write any code to do this. You relied on some sort of core code that has been validated and tested elsewhere and has a very well-defined semantics, and the user really can just focus on their high-level model without worrying about implementation details. That's all handled automatically. And this is very different from a high-level model that has no formal connection, automatic connection to the implementation, or the opposite scenario of having purely implementation. Those are both not ideal, whereas having this automatic pipeline of declaring a high-level rewrite rule and generating an implementation is really, I think, a great balance. And so the code that you write to do this would be to just simply declare the data of this rewrite rule, which is declaring these three C sets and the data in between them. Declaring a C set is pretty straightforward. You're just essentially filling out the rows of a database. And actually, the morphisms can be found automatically, so you could specify them manually. And just to show you what recovery looks like, you have an infected person, and that gets replaced with a recovered person. I should also talk about updating the state, because if we have a time step and multiple events happen, it's unclear what you would want to do. And so let me show you what we might want to do if we have a conflict. So let's say we have this rewrite rule, and I'm going to use the partial morphism notation just to make it simpler. And I also realized it's L and R here, and it was I and O before. These are just naming conventions and reflecting the fact that multiple people contributed to these slides. So let's say we have this rewrite rule here that we also want to, but we also want to apply rewrite rule B, let's say. We can't apply these at the same time. So what we ideally would want to do, let's say we apply A first. We could apply rewrite rule B if only we had a morphism into Gn+1. But how are we going to get a morphism like that if all we have is a morphism into n? But it turns out that this partial morphism that we induced can be composed with this morphism. So you can compose a morphism and a partial morphism. Not all the time will it be a total morphism, but if it is, then we can essentially push our match forward into the next time step. If it's not a total morphism, that means, let's say this rule, the A rule says somebody dies, and the B rule says somebody gets a piece of cake. If that person who is going to get the piece of cake died, then this morphism would become partial. So this, what we interpret the fact that this is partial is the match is invalid. So we just don't execute that rewrite. So we have a pretty well automatable way of executing multiple rewrite rules, not all at once, but we can execute rewrite rules that were supposed to happen at the same time in a coherent way. So we can apply this to SIR models and get a discrete time analog of an ODE system. And we can also extend this where we give the agents an age attribute, and then we use a contact matrix that actually came from real world data that said, 40-year-olds interact with 40-year-olds more often than 80-year-olds and so on. And you can see how we get this heterogeneous behavior of different age groups having different levels of overall infection. I can also, if there's time, go through another example just to show the breadth of the sorts of individual models that we can do. This was the schema I showed before. Let me just briefly summarize this discrete Lotka-Volterra model. Wolves and sheep and grass are all on this 2D periodic grid. Wolves eat sheep, sheep eat grass. The wolves and sheep are moving, they have a direction, and they occasionally turn left or right. Otherwise, they're just like moving around randomly. And the wolves and sheep have energy. And if you move forward, you lose energy, and you split in half if you reproduce. You die if you run out of energy or you're eaten. So let's see what a rewrite rule looks like here. So this is the move forward rewrite rule, where I'm going to say I have a sheep at position at this edge. It moves forward and it loses one of its energy. This first number is sort of like the ID number, and then afterwards is the energy. We can apply this to a simulation where there's a wolf and a sheep at this position. This circle here, this position gets matched there. This circle gets matched to the position with a 4. And then this last circle gets matched to the original thing, because this is a periodic mesh. And if we execute the rewrite rule, the sheep moves forward and it has lost one of its energies. We actually don't want this rewrite rule to execute if the sheep has no energy, if only to prevent sheep from having negative energy. So we actually want to have additional machinery which has a well-defined theory called negative application conditions, where we actually, this becomes extra data in the rewrite rule, which says if your pattern, it gives another context which your pattern is embedded in, and if there exists a homomorphism into your world state, then you don't execute the rewrite match. So here we're going to say that if your sheep has 0 energy, you're not allowed to execute this. And if we were to, instead of this, we have a wolf in position 2, that would essentially have the meaning of the sheep will move forward, but it can't move forward if there's a wolf there. It wouldn't want to move there. So again, the code that looks like this, we can declare an attribute like this with a nice code to fill out the database tables. We can use variables that constrain the fact that these edges are pointing in the same direction. And that the sheep has a variable of x, and when we replace it, we have an energy of x minus 1, and now it's in position 2 instead of position 1. I think it's also interesting that there's a sort of symmetry in our schema between wolves and sheep, and we can actually encode this with a functor, an endofunctor really, on the schema. And then we can use functorial data migration to turn this entire rewrite rule from a sheep move forward rule into a wolf move forward rule. So this is just sort of advantages we get when our algorithm is being encoded combinatorially rather than just as arbitrary code. So yeah, then we can essentially run the simulation. We can have the sheep move forward. The wolf will then move forward. So this sort of interactive thing that we can do in Jupyter Notebooks is essentially allows you to step through a trajectory. Now the wolf will reproduce and to split into two wolves with half energy. And then the next step was this counter to decrease. So future work will be getting more of the common agent-based modeling or individual-based modeling that is done in epidemiology and getting more of that literature actually encoded into our framework and showing that we can essentially do the same simulations, but much cleaner. One thing that we need to work on in order to really compare to those is on the note of efficiency. So essentially when we look for morphisms into some world state, and then we look at morphisms in the next time state, the world state might be very big, but only a tiny amount has changed. So there's this sort of incremental graph matching algorithm that if we implement, then these simulations will be much, orders of magnitude faster. And then essentially, sometimes you have events that occur, need to be cached to occur in the future. Someone goes into the hospital and you say, I want that person to recover in 7 days if they don't die before. So these are sorts of features that we want to implement. So with that, I'm happy to take any questions.
Questions?
Thanks for the talk. Very nice stuff. Can you say a bit more about the implementation, how you actually do the computation you're talking about?
Yeah. So fortunately, I guess that would be the slide that shows the 3 libraries. So the implementation really is specified in algebraic rewriting as simply compute push out complement, compute push out. And so then you would be asking where do those come from? And those are implemented by catlab.jl. So is the question, how does catlab.jl implement push out complement, or is there some other question?
Yeah, that partially answers my question. So these are explicitly represented in memory graphs that you're manipulating.
Exactly. Yeah, these are basically in-memory databases. That's the data structure that we use. But
so one thing that I'm interested in is if these how do you handle rewriting when 2 rules might conflict, and if you always do it in a particular order, and if this would introduce artifacts in the simulation? Yeah,
I think that's a good question. So I think let's go to the slide that essentially has that. So yeah, as you make your time step larger, essentially you're going to have more things that could potentially conflict. So there might be a trade-off between doing things at a finer time step to have fewer conflicts and have fewer artifacts versus maybe efficiency gains that might come from a larger time step. Certainly, in cases where we do a time step and there are multiple things that could conflict, that can be then randomized. Like we don't need to pick a particular order there. But you're definitely right that at the coarse grain modeling of continuous time events being modeled discretely, that you're going to necessarily introduce some artifacts.
Great. Well, thank you, everyone. It's been a great first day, and I'll see you all tomorrow at 9 a.m. in this room. Wait.
Yeah.
Okay.
Hi, I just have a quick announcement about the conference dinner. So lots of you signed up, lots of you didn't. So today, what the numbers that we have are going to be considered final for organizational purposes. So if you still want to join the conference dinner, you can find me there at the desk. So if for whatever reason you were interested, but you don't show up, we're going to have to consider you not interested, change your mind. And if so, I know some people have been thinking about having problems with finding ATMs. Turns out one of the ATMs there doesn't work, and there's all this. there's solutions we can make. Maybe I can take some people to an ATM because we need to sort of have these numbers today. So that's all.
Thanks.
Not my best work. I forgot to say it's not. I didn't make the slides.
Yeah, that was a funny. This reflects the fact that these slides weren't contributed.